So good morning everybody and a warm welcome. I'm Payal Mukherjee here from IIT Bombay, and I can see that almost 80 plus people are here now. So before we start, we can just have an ice-breaking session, and let me know how many of you are faculty members, because we have allowed some students also on special requests who are doing learning program with us. So just you can type in the chat box saying that F for faculty and S for students, so that we can have an idea. Okay. Okay, so I can see that we have a mixed crowd here. Okay, welcome all. So all the faculty members who have joined today, so let me know whether you are teaching CFD as a part of your course curriculum, or you are here to learn the basics of OpenFOAM to apply it on the CFD that you are teaching or using it in research, or at present you are using some of the proprietary software, and whether you are here to learn OpenFOAM just for your interest or okay. Yes, teaching. Okay, so you can write just Y if you are teaching a course on CFD in your institutes. Y, okay. Okay, that's great. Okay, thanks a lot for your responses. Thanks a lot. So we have 98 now. I think we can start. It's almost 10:30. YouTube is live. Okay, so you can start the recording. ये एंटर करूँगी तो ये जाएगा ना आगे प्रेजेंटेशन. शेयर स्क्रीन नहीं है तो है. यहाँ से करूँ? ठीक है. म्यूट हूँ. म्यूट है. नहीं ये गूगल मीट ज़रा खोलो. मैं म्यूट में हूँ शायद. ठीक है. मेरा म्यूट है. कहाँ गया वो? अनम्यूट कर दो. Okay, so could you please let me know whether my screen is visible?
Yes, ma'am.
Okay, thanks a lot, Paris. So we are starting. Should I start? Okay. So very good morning and welcome to this faculty development program on CFD using OpenFOAM. Namaste to all the faculty members who have joined today. to be with us for the next 4 days. And I am Payal Mukherjee. I am working as a senior project manager at FOSSEE, IIT Bombay. Okay, and I have my team members with me. Today I have my colleague Ms. Usha Vishwanathan, who will be interacting with you in some time. I also have my team members Ivan Fernandez, Paris Palkar, Pranay Pandey, Nikhil Chidnavis, and Manjil Situla. So all of them will be there with you for the next 4 days, and we will have a lot of interactions, lot of learning, hands-on sessions, and a full-fledged complete learning program on the basics of CFD as a part of this faculty development program. So first, let me introduce FOSSEE project to you. In my slides or in my presentation, I'll speak about FOSSEE so that you know who we are and what we are doing here at IIT Bombay as a part of the FOSSEE project. And you'll also get to know what will be your benefit when you're attending this faculty development program. So the FOSSEE project was launched in the year of 2009, and we are developing this project at IIT Bombay, and FOSSEE stands for Free and Open Source Software for Education. And we envision to build the nation to empower the citizens of India through the knowledge of FOSS. And by knowledge, I particularly mean the application of FOSS, and this application actually will enable the learners to use a FOSS. Here we will talk about OpenFOAM because this is a learning program on OpenFOAM, but FOSSEE project has different verticals which cater to different streams of engineering as well as non-engineering streams of education. So when FOSSEE was launched in the year of 2009, it was called Free and Open Source Software for Engineering Education. But now it is for non-engineering branches as well. We are there for the animation students, for the statistics students, for the GIS students, and that's how we are functioning now. And this application part is very interesting because most of the education institutes, they teach software, and they examine you and they grade you and give certificates. But in FOSSEE projects, it's a very unique project in the sense that we will train the learners on the hands-on part so that you can learn and apply that software to create and to submit, to publish some mini projects, and that will be the proof that you are pro in using that software. And FOSS stands for Free and Open Source Software. We also use the term liber, and we can also call it FLOSS. So it stands for Free, Liber, Open Source Software. Okay, and this project is funded by Ministry of Education, Government of India. And one very special thing that I want to mention here is it is the only government in the entire world that is funding a project on free and open source software. Okay, and why is FOSS important? I'll just talk about it in my next slide. And this FOSSEE is a part of NME ICT, that is the National Mission on Education through ICT. And here we are trying to reach out to each and every corner of India. We are trying to empower each and every faculty, students, and whoever is enthusiastic in learning a particular software, through this training program. We are trying to, upgrade the skill set of the learners and empower and facilitate education through this, practical learning programs. Now let me talk about FOSSEE and how is FOSS useful through the learning program of FOSSEE. Okay, so as you all know, education is the base of any economic development of the world. I'm sorry, some sound disturbance was there. Okay, so I was saying that education is the base of the economic development of the world. So, each and every country would need to strengthen their education base so that their economy flourishes. Okay, and why we are saying that the knowledge of free and open source software is important, because there are some features of FOSS which actually makes it very special. The number one cause is, it is very cost effective. We can use FOSS in a legal way because it comes with licenses such as BSD and GPL, which you can use. You can download and install FOSS in your own systems free of cost legally. Okay, there is no question of any legal issues if you use FOSS. Number 2 benefits, you can modify the code and you can distribute the code. And number 4 is you can also distribute the modified code, the modified version of the code. So these 4 features actually makes FOSS very effective, and the most effective thing is the cost effectiveness, because see, the world is going through economic turbulence at present. Okay, each and every country of the world is affected by some or the other way. So we cannot afford to spend lakhs and lakhs of our money to buy expensive licenses of proprietary software. And whenever there is a chance of using alternative free and open source software, we encourage people to go for it. Okay? Why will you spend lakhs of rupees if you are getting something for free? So this cost effectiveness is very much important for both academia as well as industry. Okay. Now let me talk about the training part. So FOSSEE trains not only the teachers but also the students. For students, we have many programs like students workshop, internships, fellowships, and for teachers we have programs like this, which are for the development of the teachers, so that they can actually pass on the knowledge that they acquire to their students. Okay, and the last but very important point is academy industry collaboration that FOSSEE promotes. So FOSSEE believes that there should be a constant transfer of knowledge between academia and industry, because these two are the pillars on which any country, any economy stands. So if there is a constant flow of knowledge between the academia and industry, any economy is bound to flourish. Okay, so now these are the offerings of FOSSEE. I was just talking about all the verticals of FOSSEE, all the software that we train. So you can just browse through FOSSEE.in later on and check all these verticals. So FOSSEE is present for statistics through R, animation through Focal. Okay, we also have FreeCAD. We have hardware, free and open source hardware in the form of FLOSS Arduino and OpenPLC. We also have Scilab, Python, which are very much in use by the engineering students nowadays. We have eSIM for the electronic students, OSDAG and DWSIM for chemical engineering. Obviously, we have OpenFOAM for mechanical, chemical, aerospace. Okay, sorry, I just made a mistake. OSDAG is for steel industry, and DWSIM and OpenModelic are for chemical engineering simulations. Okay, and in this table you can just go through once. If needed, I can share this table to you later on. Here you can see the commercial equivalence of all the free and open source software that we are promoting through FOSSEE. Okay, so and you can also go through the streams that they are used for. For example, MATLAB. We have Scilab for a very popular for software which is known as MATLAB, which is used for all the streams of engineering and science. Okay, and we have more here. You can just go through this list once. I'll not spend much time explaining all this. Okay, and here I have this takeaways from FDP. So what will you gain from this FDP is, number 1, the learning will be intensive through various lectures and interactive sessions, and also the hands-on part of the training. Okay, so I would request you to please be very attentive during the hands-on learning programs, because you need to follow each and every steps very particularly. And if you have any problems, our team members are there to guide you thoroughly. Okay, and after fulfilling the attendance criteria, you will be awarded certificates. Okay, so please make sure that whenever we float the attendance sheets, please mark yourself present. Okay, so this is a very important thing, because as per our experience, some of the people are very busy in attending the workshop, and they miss out on filling the attendance sheet. But that's why I'm requesting you to please be a little bit careful when we are announcing the attendance sheet, and kindly fill it. Okay, and after this training program, you will be you will gain the knowledge to publish a research migration project at our FOSSEE website. and we also, you also have a future scope of becoming a FOSSEE faculty partner later on. Okay, after you are you have that knowledge of using OpenFOAM and guiding students to produce or to publish projects on CFD using OpenFOAM. So this we can at the end of the workshop I'll explain in detail what are the roles and responsibilities of FOSSEE faculty partner, and I'll also during the workshop you will be meeting a lot of people who are working or who are as a part of a team, they are contributing as faculty partners of FOSSEE. So here I come to the workshop norms. So I would request all of you to please mute yourselves during the lecture sessions, and so that we can avoid any kind of distractions. And also during the hands-on session, you can raise your hands, you can use the chat box. Preferably please do not talk during the hands-on sessions also, because we will be having interactive sessions later on at the end of each and every lecture session as well as the hands-on sessions. Okay, and so interaction time will be there after each of the sessions. And one very important point is that kindly maintain the decorum of this program. Please avoid using any kind of text or comments that are not acceptable. And we have a norm that we are blacklisting the participants from all the future workshops of FOSSEE if we receive any kind of offensive messages from you. This is not only for the faculty members who will be interacting with you, but also with the FOSSEE team members. Okay, so here I'll stop my presentation. I would request my colleague Ms. Usha Vishwanathan to please take over and continue the presentation.
It's the same presentation. Hello. Okay, so I will continue with the same presentation. I am working with the FOSSEE project for the past 12-13 years. So we are a group of people who are very passionate about free and open source software, and we want more colleges to start using open source software. So these are software which are legal. You don't need to pay any licensing fees for using it. It is actually free, but it is completely licensed software. So that is one thing which I want to reiterate. So no one will ask you why you are using this software. You can just freely download it and start using it. So I have to enter this one. Okay. So I will just talk about, so Payal has talked about how we are doing and what are the things which we do for promoting free and open source software. So there are a lot of activities where institutions, the faculty members of those institutions and students of those institutions can participate in. So there are a lot of activities. Currently actually there is some technical issue which is going on with our FOSSEE web page, so it is not accessible, but once it is before the workshop, the end of the workshop, you will be able to show it in one of the sessions that how to go about the FOSSEE web page. So there are a lot of activities. Once the training is over, there are a lot of activities which we are promoting where the faculty members and students of various institutions can participate. So the first thing which I want to say is that most of the students who actually come for engineering or any other degree education, most of them are not aware of the concept of free and open source software. So our team will be very much interested in doing some orientation session for the students in those institutions. So the faculty members can actually coordinate with us and we can try to arrange orientation sessions. So that is the first thing which any institute can do. Then you can migrate your labs to FOSS. So for example, if your institute is using Fluent, you can definitely think of using OpenFOAM. So our team will be helping you in migrating the proprietary lab to an open source lab. And there are a lot of activities, as I already mentioned, where the students can participate and the faculty members also can participate. So, do encourage your students to participate in them. And we are also open to conducting workshops for your students, so we can do that. So, there are a lot of activities. Definitely you can get more information about that on our web pages. So, you can just take a look at those web pages. So, I will not go any further, you can just take a look at our web pages. And apart from that, there are a lot of internships which we do all the year round. So, students can keep looking at our web page, and whenever the opportunity is open, they can apply and try to do internship with us. And these internships are very well appreciated, and a lot of students actually have taken benefits through these internships, participating in these internships. So, the benefits, most of the students, I will just say first the students, then faculty member and the institutions. So, the students of course, they will be upgrading their skill, and they already are getting more opportunities. That is, if you are more familiar with the software, your employment opportunity is also increased, and you have the access to a legal software in your system. You can take it anywhere and everywhere. Then in most of the internships, the students get an opportunity to work with some industry partner and all. There are cases where the industry people actually guide the students. So, that is actually a good exposure to the student. And of course, we whatever contribution the student does is actually recognized through, we give honorarium, and the website, one page is dedicated for them. So, all those contributions are acknowledged in various forms, and we also provide certificates for whatever work they have done. And similarly, faculty members, of course, they will upgrade their skill, and we recognize the faculty member on our web pages, and annually we can provide appreciation letter for the work which they have done. And we also have FOSSEE awards, which is conducted every year. So, in that we also shortlist the best performing faculty members, and we give them awards. So, that also the faculty member can get. And institution, of course, financially they gain a lot from using free and open source software, and NAC and NIRF credits also you can get through these activities, whatever contribution the institute students as well as the faculty members are doing. And we recognize them on our web page as a FOSSEE partner, and again during FOSSEE awards we recognize the institutions, best performing institutions also. So, I have just collated some of the testimonials from some students who have participated in our internship or events like hackathon, marathon. So, this is one from a student from IIT Chennai, and we have another person called Madhuri Kadam, who actually is an electronics engineer. She is now working in Synopsys. So, that opportunity came when she participated in one of our marathons, eSIM marathons, which is an electronic design automation tool. So, these are some of the things. So, I have just tried to collate from various fields like CFD, then chemical engineering. So, this DWSM is chemical engineering. So, we hope you people will take benefit from this workshop and start contributing to the CFD vertical of FOSSEE. So, thank you all, and best wishes for a very good workshop session. Yeah.
Okay, am I audible?
Yes, ma'am.
Okay. So we will move ahead with our first lecture session by Dr. Chandan Bose. So Dr. Chandan Bose is actually leading the CFD vertical of FOSSEE, and he is actually inspiring all the team members to put in our best efforts and guiding us through each and every steps that we are doing here. So here's a brief introduction of Dr. Chandan Bose. So he is an assistant professor at the University of Birmingham for the aerospace engineering department, and a subject expert in computational fluid structure interaction, which is called FSI. He leads the bio-inspired FSI lab at the University of Birmingham. His research group focuses on investigating various complex multiphysics problems involving coupled nonlinear interactions with primary interests in unsteady aerodynamics, nonlinear aeroelasticity, and bio-inspired fluid structure interaction problems. He has authored 23 journal articles in reputed journals and 20 plus CSI indexed conference proceedings and book chapters in the area of unsteady aerodynamics and FSI. He serves as an editor in the OpenFOAM journal, as an editorial board member in scientific reports, Springer Nature, and the Journal of Computational Sciences, Elsevier. And he is also a guest editor in the Journal of Wind Engineering and Industrial Aerodynamics of Elsevier. He co-leads the Midlands Fluid Mechanics Group in the UK. So over to you, Professor Chandan, and welcome to this session.
Hello, everyone. Am I audible?
Yes, sir.
All right. Let me first try to share my screen. All right. Please let me know if you can see my presentation.
Yes, sir.
Is it visible in the full screen?
Yes.
All right. So one drawback of using Google Meet is that when I present this, I only see the presentation. So I do not see the screen of the participants. So please let me know any of you, Paildi or Paris, if there are any questions in the chat box, because I'll not be able to see the questions. With that, hello everyone, and thank you for joining this faculty development program. And I think I thank Paildi for giving a very kind introduction to me. So I don't want to spend a lot of time on that, but just briefly again mentioning that it's my pleasure and it's a great honor to have the opportunity to lead this FOSSEE CFD team with very passionate people who believes in democratizing CFD using open source codes. Particularly OpenFOAM is our primary focus. And I'm also a visiting faculty in IIT Bombay presently. And I lead the BioFSL lab in University of Birmingham. So I started my journey with the FOSSEE team from 2020, roughly, just after my PhD when I completed from IIT Madras. And I would like to thank Professor Kannan and Professor Janani Muralidharan from IIT Bombay to bring me on team. And the primary interest from my side was to promote using of open source code, particularly in my field of expertise, which is computational fluid dynamics. So, and it's a great pleasure for last 5-6 years to work with the team and to see the impact that comes from promoting these kind of projects, guiding interns, and take the hands of our students to teach them, train them, and make them expert of this kind of field, and to let them go into the next stage. Mostly in these kind of workshops, you see me giving very technical talks, such as fluid structure interaction, dynamic meshing, and I've talked about many more, such as how to code your own solver in OpenFOAM. And I think all these videos are there in the FOSSEE YouTube channel. But this time I thought, because it's an introductory lecture, before you take a deep dive into all these technical sessions for the next 3 4 days, I thought I will take the opportunity to take a detour from the technical stuff to provoke some questions in your minds, particularly because this is a faculty development program and all of you are actually training and shaping the minds of our young talents. I thought we should at least start thinking why we should use this open source code, particularly in the field of CFD. And so with that view in my mind, my slides will be just, the sketch of what is my thought process and what I want to discuss with you. I will basically go through my thought process and express my view, which is very personal. But at the end of this, if time permits, I have prepared some of the discussion questions which I would like to, pose to you and get your views on what you think as faculty members on these challenges and the upcoming opportunities of using open source codes to democratize CFD. So I think that will be my outline. So I want to start with these thought particularly. What is this, open CFD translation loop? And how can we bridge this gap between our academic innovation with the industrial impact? Now, the word impact is very broad, but here, what we mean by impact is mostly how can we translate our knowledge to real life problems which can solve the scarcity of expertise of CFD in industry sector and broaden the limitations of real life industrial large scale problems. So this is something, a loop that should be in your mind throughout, which I will build on, is that academia gives us the liberty and flexibility to do research, to take a deep dive on a particular specialized subject to increase our knowledge, to gain insights, and which can then build into, in this particular field of computational fluid dynamics, what is our main resource is the code repository or softwares that we build. Through our knowledge, we translate our understanding of physical phenomena, which can be modeled through partial differential equation, into different discretized form of solvers, which can then give us some output or results of that particular phenomena based on the research question that we pose. Now, that code or software that comes out of our research, if we can make them open, that basically kind of serves the purpose of democratizing things. Why? I will come in more detail about it. But let's say these open source codes or open codes that comes from the academic community based on our insights and our expertise and knowledge on a particular topic. And that's not enough. And that will be the main message of this talk, that just having an open source code is not enough, because our industrial partners will not be convinced to use them unless we provide them with a validated workflow. We provide them with the verification and the validation, showing that the code produces results with a certain allowed tolerances or accuracy level of the phenomena that we are trying to predict. All right. And when we have that validated workflow of this open source code, then comes the collaboration, the effort of the community, the relationship that we build with academics and the industrial partners to then give rise to this industrial impact, which has a lot of different type of impacts that I will basically discuss throughout this talk. So just to start with this workflow in my mind, the basic, key question, that the take home message that you should carry is that open source CFD democratizes simulation only when it is wrapped in validation evidences, reproducible workflows, software quality, and community support. All right. So by software quality, I mean that it should be a well-documented code, which should not take, months and years for somebody to understand what is written in this code. And then community support, which basically is meant by building on the soldiers of the giants, which means that if somebody spends 1 year to build a software and the code, the other people should not start from scratch again. They should be able to start from that latest development to add more and more complexity to reach towards the more realistic problems. All right. So if you keep these one sentence in your mind, that will be the essence throughout the talk that I would like to express my views on and would like to discuss and get your thoughts also. So these are the key words I would like to define this particular topic on, which is to democratize CFD using open source code. One is access. So by democratize, we mean that we should have a low entry barrier, which means that we should have the access to the code and software with, of course, an open source license provided to anybody who wants to build on it. And then, of course, the capability or research extensibility, by which I mean that the code should be robust enough so that other people can build on it. The other people can plug in more complexity into it and really go towards more and more realistic and complex phenomena that we see in real life. Okay. Then the third most important pillar is trust, which is again built on the credible verification and validation, without which, computational fluid dynamics, as many experimentalists mock us, that it should not become a colorful fluid dynamics. It should actually have the trust with the proper verification and validation. And I have to stress the fact that the whole industry depends on this one pillar. They will only be able to be convinced to use your code to produce their product for, because money is involved, revenue is involved, only when you can convince them with an appropriate verification and validation. All right. Then comes the fourth, but again, one more important step, which is translation, which is upskilling of, the employees, upskilling of the engineers who will use this code and software on a day-to-day basis, and feed this code and software into the industrial workflow. And often we see that the gap lies there. We, from an academic innovation point of view, build some code and software which is very sophisticated and very accurate, but it is complicated enough or difficult enough for upskilling the employees of a big company which focuses on a large output day-to-day basis. So the steep learning curve often becomes the burden or a barrier to adopt this codes and software in the industrial workflow. So I mean, why now? I mean, why 2026 is the high time that we should start thinking about adopting open source codes and softwares, particularly in the mechanical area of mechanical, aerospace, and other chemical engineering and most of the production-based industries, is that compute is becoming more heterogeneous. That today having a big workstation is also not a luxury, but with every country, with the growth of computing facilities, CPU cluster, GPUs, and big HPC facilities, and cloud and exascale is very common in industry sector as well as academic area. So we have the power of compute to actually solve very high fidelity real life, real scale simulation. At the same time, they require portable and containerized workflows, which means that our workflow and the code or the CFD method has to be portable, has to be easy to be installed in any of these heterogeneous HPC systems. So we need to think about more on the portability side while we produce a code or we build on some CFD workflow. Same thing comes when engineering decisions need faster iteration. So this is, of course, all of you are aware that this is one of the key requirement of industry scale, that their decision has to be fast. they cannot really wait for months for a simulation to get a very fine tuned details that we would like to, be very excited in academic world and publish a journal paper with. But the big industries, they don't care about that, because they need the production, they need a lot of output day to day basis. And for iterating the design, for example, if you think about automotive industry, if they are modifying the shape of a very first generation car, they need to iterate it fast. And often that's the reason they rely on mid fidelity or low fidelity calculations with some factor of safety which is good enough for engineering decision making, right? Which is the gap that I think is persisting between an academic world of very sophisticated physics dominated decision making plus a more factor of safety driven engineering calculations. And then the research credibility needs reproducibility. Again, I would iterate it again and again, because unless our calculation can be reproduced by somebody else at somewhere in other part of the world using different HPC system and different framework with the portability, it's actually meaningless. Because, and that's the reason nowadays, all of you know that the journals, when you start publishing your research, they ask for all the codes used for producing your results, so that when somebody reads it after 10 years, they should be able to reproduce your results. And there is no ambiguity that we don't know how you produce the results, so that we do not have trust in your result. And which basically leads to a very transparent verification and validation calculations. And then skills pipelines need accessible tools. Of course, students and engineers need to see the change and test the full solver stack, which means that they need to see inside of the code. I mean, the day has gone where you just teach your students to click the buttons of a black box tool to say that, okay, if you click this option, this turbulence model comes. And at today's day, where information is so easily available, you cannot really teach them or train them, because ultimately they will go and ask some LLM and get the answers of it. So it is better when we are training the next generation to make it very transparent, to show them this is the equation we are solving and why, and this is the models we are using with these assumptions, which does not really violate or defy the physical laws. And this is how we discretize them, this is how we solve them, these are the algorithms that we are using. So our next generation of engineers need to be quite knowledgeable about this transparent workflow rather than just clicking buttons of black boxes. Now, what do I actually mean by democratizing CFD? I have already told these 4 pillars, and I want to remind you again and again that these 4 keywords, in my opinion, are the most important part of democratizing CFD using open source code. And I would be very delighted to know if you have other things in your mind. But the new thing here is the adaptability, which again is related to the reproducibility of the code, the robustness of the code, depending on this heterogeneous compute, depending on the scale of the problem, etc. Now, I think my colleagues have already told that the one of the major benefit for the industrial partners to use open source code is to break this cost barrier. And just to give you very rough numbers, that if you think about mid-tier SME to a big company, the order of money that can be saved annually for all the employees, of course, for CFD license cost starts from $50K, which is huge, and it can increase based on the scale of the company. And most of the SMEs, like 75% of the small scale industries, particularly with the Indian scenario, they actually do not use CFD just because they cannot afford this cost, and they rely on mostly low order models, reduced order models to make their calculation, and sometimes empirical results which are obtained from experiments on a very particular conditions and not valid for all the varied conditions in reality what you observed. And also the performance gap, this is again very rough number, 3 to 5 times performance gain can be achieved. You can really accelerate your open source code using GPUs and optimize the numerics with the academic insights of our CFD engineers. And for example, if we talk about OpenFOAM as one of the most popular open source CFD code, and along with it, I will give you some other examples what are available. We see a huge number of downloads and users and forking in the repository. So, which basically shows that throughout this globe, different, almost all the academic institution and almost many big to small companies have started to migrate toward open source code to break this cost barrier. Now, again, as I said, these commercial solvers are priced beyond SMEs and academic budgets, mostly, apart from, of course, premium institutes and big universities. And of course, most of the algorithms are proprietary, which you do not have access to. So you have very limited documentation or very limited knowledge of what exact algorithms are being used within these commercial tools, which of course leaves a gap in the minds of the students or trainees who are actually getting to know what CFD is about. And yes, so basically, I think this is one of the barrier that can be broken with avoiding commercial softwares and using and replacing them with open source code. And I think what I've already told also is that what I think is the persistent translation gap. For academic innovation, I think what we as academic are mostly interested are about the new physics and the models, rapid solver prototyping, publication-driven validation, expert-led operation. So, which creates a bit of lacking in the translation towards the real industrial practice, which mostly rely on robust, repeatable workflows, traceable design decisions, support quality assessment and documentation, and risk IP and certification constraints. So going ahead, we have to keep in mind that how can we fill these gaps, and I would be very happy to know your thoughts on this. Right. So open source CFDs, in my opinion, is not a single piece of code or software that we should rely on, although we are currently actually focusing mostly on OpenFOAM, which is one of the most popular open source CFD code. But in my opinion, it's an ecosystem. So in the CFD workflow, as you all know, that it's not just the solver that solves the partial differential equation, but we have the pre-processing requirement, we then have the solution, and then have the post-processing, and then have the interpretation requirement of the results, right? So I can actually break it down as solvers, macing tools, coupling for multi-physics, and mostly very important part is post-processing the results, and then a reproducible workflow that can actually give you the accessibility of the code and version control of the code, which is very important. So these are some of the examples that I brought, which are available open source. For example, OpenFOAM, SU2, Code Saturn, NEC 500, PyFR. There are n number of different open source code available. With macing, let's say GMSH, Snappy HexMesh, CFMesh, Salome, and to couple different multi-physics systems such as fluid, solid, heat transfer, magnetism, etc. We have Precise, OpenFOAM, Calculix, MBDyne, Solids for Foam. For post-processing, we have ParaView, VTK, PyVista, Jupyter, Python. So these are all open source. And in terms of version control and workflow, we have Git, containerizing using Docker, using Singularity. We have different testing, workflows such as CI/CD, which gives you unit testing, and we have HPC schedulers such as Slum, which allows you to maintain a unified, HPC workflow management throughout different heterogeneous HPC. So the key point here The translation problem is system integration, such as solver, mesh, coupling, evidence, and automation. So all of these together, if we containerize them as a package which can act in different heterogeneous HPC system, then it can translate along with the complementary documentation, upskilling of the employees of the industry, and I think that's the way to go. Now, so when we talk about the innovation stock, what can we do from the academic community, from the innovation perspective and the training perspective, right? So open source code becomes industrially useful when every layer is curated, benchmarked, and taught and trained to the next generation of the students. And I think that's where FOSSEE comes in, and we play a key role, at least in India, to train the next generation of the students on these different stacks, which creates the mindset of producing and delivering new and novel open source codes. So first comes the physical models. Without this fundamental knowledge of fluid mechanics, we cannot really go to computational fluid dynamics. So which becomes starting from the basic knowledge of mathematics, starting from what is partial differential equation, then what is the physics that we are trying to solve? Is it the turbulence dynamics? Is it multi-phase fluid mechanics? Is it fluid structure interaction? Is it aeroacoustics, for some example? So we need to understand what is the realistic physical condition and how can we model it. What is the closed form partial differential equation that we are trying to solve? Then comes the numerics, of course. How do we discretize this to convert into a series of linear equations that can be then solved? So we need to know what is the appropriate discretization schemes, what are the coupling schemes, how do we stabilize these discretization schemes, and we can use some advanced techniques such as adjoint functions, etc., for optimization and other things. Then, of course, there is a part of software engineering that all of our CFD engineers should be aware of, such as modularity. As I talked about, containerizing this whole stack into a packageable code or software. We have to know how to unit test when we do version control and keep constant changes in the code. How do we make sure that the code doesn't break, the code still works? So we have to add constant unit testing, and we have to be very updated with the release of the updated code to the community. And the fourth is one of the most important, which is verification and validation. So we have to come up with appropriate benchmark problems. We have to determine the associated numerical uncertainty with it. We have to run regression tests to, again, make sure that our benchmarks are verified and validated continuously as we make changes to our code. And then, of course, we at the end, we should have a established decision workflow, including optimization, design guidance, proper documentation, dashboards, and updated websites, and so on and so forth. So I think to make our academic knowledge of computational fluid dynamics through this open source code, it will only become industrially useful if we tick all of these points together. And that's my personal thought. Now, the next thing is to gain the industrial trust, right? So I think the central bridge here to gain the industrial trust is the evidence that our code is accurate. It can accurately predict the phenomena that the industry based on, and what the industry is trying to produce. All right. So trust requires an evidence pyramid, which, starting from the production decision, knowing the design margin, the risk, the sign off, and then come application validation, comparison with target experiments and operational data, then which boils down to canonical benchmark, for example, backward facing step, cylinder, airfoil, cavity, FSI test. So these canonical tests becomes the most simplified benchmark or validation cases for a very complex, realistic industrial case study. And then comes verification, which means that, convergence test, numerical uncertainty, regression test, etc. Then comes the quality of the code, which is the primary importance here is the documentation, reproducibility, version control, containerization, etc., etc. So the industrial adoption starts at the bottom and fails when the layer is missing. So if there is a missing link between these pyramid at any stage, that makes the case that the industry is not able to consider our open source code as trustworthy. All right. So now coming to OpenFOAM as a community platform. You all know about OpenFOAM, but because you will take a deep dive in the next 3-4 days in different case studies, different examples, hands-on exercises, I just want to remind you how OpenFOAM acts as a community platform. So you all know that it's finite volume based code, which basically makes the physics extension possible. We can extend any complexity with added equations, added partial differential equation and models to our code within OpenFOAM. The case file structure enables transparent numerical assumption. So with the boundary conditions, initial conditions, transport properties, and very structured way of giving our case parameters, makes it very transparent to know what we are actually assuming while simulating the case. The community ecosystem supports tutorials, forks, libraries, user meetings, and I will show you some example of technical committees and special interest group as a global OpenFOAM community, which are existing if you are not aware of. And then industrial uptake depends on governance, validation, and support channels. So which OpenFOAM is very well equipped with, and that's why OpenFOAM is chosen now one of the popular open source codes which is trusted by most of the industry. I would not say all, but it is piercing that transparency and requirement, and many of the small to large scale industries are now adopting OpenFOAM as their regular simulation tool. All right. So again, I mean, here, I think one disclaimer here is that OpenFOAM is very good when you actually treat it as an open source code and not like any other commercial tool. So I see that it's very fancy to write on your CV or to tell others that I'm using an open source code of OpenFOAM. I know OpenFOAM, it increases employability. But if you really want to, establish yourself in the field, you have to treat it as a code, as you have to get used to the black screens and see what is actually coded and how the equations are solved, rather than just using it as like any other black box tools without knowing what is written inside. And that's a trend that makes me worried, because even when we talk about next generation engineers, they often use OpenFOAM also like a black box, and they are not aware that they can actually look into the code and they can try to incorporate their own models. They can make their own solvers. They can modify the discretization schemes. They can add new assumptions and so on and so forth. So that's a disclaimer which you should propagate to your students probably, that because it is an open source code, it should be treated as an open source code and not as an other commercial codes. Right. So I think I will not reiterate it. I will I have already told these things, that reproducibility, robustness, traceability, usability are the main key point as any open source code. Now, what kind of academic innovation in my field are actually going on? I wanted to give you some idea that what we are actually doing as academic innovators, particularly what I'm involved in. So for example, one of the research question is that my group is now trying to address, that how can we use this open source code to solve bio-inspired FSI and morphing wing problem. We are trying to answer this research question: how do compliant wings passively regulate vortex formation under unsteady flows and the gusts? And we are using OpenFOAM precise coupling, solids for foam, and we are running this simulation in different large-scale heterogeneous HPC systems around the world, for example, in UK, in Europe, and in India also. All right. And what is the industry relevance of this problem? So I'm collaborating with different drone companies in the UK and also big companies like Airbus, where there is industrial relevance on gust mitigation, next generation of UAV design, which is unmanned aerial vehicle design and gust mitigation, and structural compliance for passive flow control. All right. So, and 3 of my PhD students are working on it with multiple industry partners. So, which basically gives you an example of how this open source workflow, code workflow can be used in realistic industrial problem. So the another problem that I normally delve with is data driven methods for open source code. So we are using multi-fidelity Bayesian optimization kind of techniques embedded in OpenFOAM, which basically gives us the power of optimizing any engineering problem based on probabilistic formulations of Bayesian optimization, which is a very old technique, but it is now reinvented using the data-driven surrogate modeling and giving you the power to optimize a very large-scale problem, getting the most optimized solution for your industry. For example, if you want to really optimize the shape and flexibility of the wing, if you want to optimize the optimize a wind turbine blade and or a propeller, understanding how many propeller blade and what sort of configuration you want, or let's say an industrial scale mixer, you can do it using this data driven methods embedding into your open source code or OpenFOAM. The other things that I'm involved with, which is vortex induced vibration. So we are trying to get very high fidelity results from this open source CFD simulations, and then building reduced order model, which can then be used in the industry for mitigating high amplitude vortex induced vibrations. So I very much focus on producing reproducible containerized workflow, which can be used by the industry, and of course, open fluid structure interaction benchmark releases, working with colleagues all over the world, finding what could be the most suitable benchmark problems for fluid structure interaction, and how can we validate our open source code results along with experimental results and other analytical results. So as faculty members, I think I would just pose this suggestion to you. How can you train the next generation of engineers in your institutions? And I think that training is the largest lever. And that's with this belief, we actually promote these kind of open source code and simulation techniques and trainings in India, particularly focusing on undergraduate and postgraduate students. And this is, in my opinion, FOSSEE's greatest contribution is that we provide this training to create this democratized CFD ecosystem, but which needs a curricula, which that's why we are trying to work with different engineering institutions to include this open source code training into their curriculum, so that regularly in a structured way the students can learn about it and they get credits for it. We provide workshops, very often workshops from beginner to advanced level of CFD knowledge using OpenFOAM. We have a very big repository of case studies and research migration validation studies, which is again to serve the purpose of gaining the trust of industrial partners that the results are accurate and they are not just colorful fluid dynamics. They can be used for realistic problem. And we provide mentorship, and along with our team members, we have many faculty partners like you who kindly provides their time to mentor the next generation of engineers to FOSSEE. So this is our appeal to you, that you promote this knowledge in your institution, promote this knowledge into among your students, and if you need any help, please reach out to FOSSEE team, and we are very happy to help in this regard. Now, this knowledge or training starts from very early undergraduate students or master students. So what can be done? I mean, this is my very personal suggestion, that you should first let them know that please see the governing equation through the cases. All right. So do not use OpenFOAM as a commercial tool, but just go into the source code, see what is coded, what is the underlying equation, and how do you rebuild it? How do you modify this equation and rebuild it and make your own solver? So that's the first step that should be started if we really want to pierce through this open source knowledge. Then, of course, if we go towards higher levels such as PhD, postdocs, you should motivate them to create more reproducible new solvers, new workflows, new benchmark studies, and contribute to the community. And one of the best way to communicate it is, of course, through journal publication, but there is a dedicated journal to OpenFOAM where it's 100% open, and all the papers contains the associated codes and reproducible workflows, which then can be used for any for addition of more complexity by anyone, and build new problems on that. And of course, that propagates through when your students graduate, they join industry. So through that, we want to create a workforce, upskilling the knowledgeable employees in the industry, which then will carry forward in the coming years the mindset of using this open source code in the industries. And in the middle, of course, RS is research software engineers. We need the help of research software engineers who are specifically trained to help us to make use of this open source code into this heterogeneous high performance computing system, because of course CFD is something that needs a lot of compute. So it is not always possible to simulate it just in our laptop. So we need to use hundreds of processors to solve it. And to optimize our code, we should also train appropriate research software engineers or HPC specialists who can create these reproducible workflow for us. So yes, so to reiterate, training is the largest lever in this pathway. So and FOSSEE is very much committed to deliver this training in open source codes and softwares. And if we really can sum up, I think the time is not much time is left. So if we really want to sum up how this industrial adaptation pathway can emerge from this academic innovation, in my way, it should be from curiosity to production without pretending that risk disappears. So this is the key thing, because again, as I said, that the industrial production is very much dependent on their workflow of mitigating the risk of loss, failure, and overestimation, etc., etc. So we have to bridge that gap through our academic insights, that it's not just for the sake of publishing a journal paper, it is to maximize the revenue of an organization. So we have to include that factor of safety in our calculation or the workflow. So there are different steps to actually allow this open source code to actually embed into the industrial workflow. But I think these are some of my suggestions, which we can start with the sandbox, which basically, you start discussing with industry partners and choose a benchmark bounded problem, which is canonical, and prove that this code works. OpenFOAM is good enough to validate a benchmark case. Then you go to the pilot stage where you compare with their internal data of industry, you quantify the cost accuracy trade-off, and make a business case to the industry that yes, OpenFOAM can be used. And then you basically create, modify it and create a reproducible workflow for them, so that it is lucrative enough for them to actually take up that workflow instead of a commercial software. And then the next stage is to scale. I mean, of course, as I said, the industry cannot wait for months to have one simulation results to see whether they should change their design and which would affect their production. They need the data, in a day or in a few hours. So for that, we need to be able to scale our open source code, which is by using HPC deployment, as I said. So we have to, run it into different heterogeneous computing platform, and we have to make sure that our code scales well for that. And of course, when all of these steps are done, then of course we have to think about the open source license. We have to think about the IP generated through it. And we have to discuss with the company that we are not violating any ethical consideration regarding uses of open source code, because this is a very bad culture that I see, particularly in India, that there are SMEs and small companies, they just take up OpenFOAM, and when they satisfy all of these, they just give a fancy name to the software and tell that that's the proprietary software of their company, without a little bit of ethical consideration of really acknowledging OpenFOAM at all. And they make money promoting that they have developed the software, which is very, very unethical. And I think that's a very crucial stage for any organization to think about. All right. So I think what, again, from my experience, what I am involved with industrial project, I think we have used open source CFD such as OpenFOAM, SU2, etc. into different sectors, such as aerospace. We have used it successfully in unmanned aerial vehicles. We have used it in renewable energy sector, in offshore wind turbine and related fluid structure interaction. We have used it in marine and biomedical, of course. And not only us, there are many, many other researchers who are using OpenFOAM into these sectors. And to name a few, there are many other sectors which these open source codes are being now adopted. So I think this is, again, I wanted to just highlight the need of GPUs and a challenge regarding the current OpenFOAM configuration, that most of the OpenFOAM code is CPU specific. But I think for the time, I will skip this, going details into it. But keep in mind that most of the OpenFOAM codes are CPU based. So there are projects going on to port these OpenFOAM codes into GPU specific code, so that we can scale it in a more larger way using GPU acceleration. So the challenges and the opportunities, I think the barriers are organizational as much as technical. So I think as I told, that the mindset of using open source code is equally a challenge as the technical difficulty and steep learning curve that we have. All right. So what still gets in the way? I think fragmentation, usability, trust, support, IP and compliances. These are some of the challenges that still exist, which stops the industry to opt for open source codes. But there are opportunities, right? So the opportunities that is coming with the growth of machine learning driven techniques and AI driven techniques are AI augmented solvers such as spins, physics informed neural networks, and surrogate models, which can reduce the time of calculation at the cost of accuracy, of course, but it can reduce the cost of computation very much. Then cloud native CFD, which is very, very interesting future direction towards it, where you can do all the calculation on cloud and you really do not need any physical hardware to do the simulation, which is a very interesting direction towards industry, and many industries are interested about it. Interpretability standards and industry academia lack of industry academia consortia, I will say, is an opportunity, because we need to build this collaboration more and more, talk more and more, convince the industrial partners through more and more rigorous verification and validation studies. So building a bridge, I think there are open communities of software governance, review, share documentation, and we have to build the bridge between the universities with the academic knowledge, with the industry, by producing use cases, data and constraints and production pool, by creating a validated science and training pipeline, and a skilled employment path towards the industry, which is closest to you, is the only way. Sorry. So I think what could be an agenda? The agenda, as I think, just to sum up, that the training is mainly one of the major lever, creating more and more benchmark and validation gallery, such as our FOSSEE case studies, research migration studies. We have hundreds of them. They can be a starting point for canonical benchmark problems to convince the industry partners. HPC ready workflow template, that is something is very premature at this stage, but we need more and more HPC ready workflow. We need industry demonstrators. We need proof of concept to convince the industrial partner, and above all, we need community. We need a big community of academic partners collaborating with industry partners together, training the next generation of engineers. Again, that is one of the motive of FOSSEE CFD team, and that's why we have created our industrial advisory team, and we try to make them collaborate and guide the students, so that the students can get both of these ideas of both of these pillars and try to identify the gaps. All right, I will skip these. These are the same thing again and again that I'm iterating. So if I think of a roadmap for the community, so what we can immediately do is in this coming year, I mean, how this is basically just to give you an idea how this community, global community, is moving towards. So currently we are trying to get a GUI wrappers for OpenFOAM, which is one of the main limitations. And I think our one branch of the FOSSEE CFD is dedicated to it, to build a graphical user interface, which will makes things much more clearer. We have to create very well trusted verification and validation benchmark suites. We have to create more open online courses and MOOCs. And in next 2 to 3 years, we will of course use the machine learning techniques, surrogate integration, which are currently already under work. If you see the case studies, many of our interns are already working on agentic AI, creating AI agent to automatically creating the case setups for OpenFOAM, etc., which would be the next goal industry-wise. And the cloud native deployment and industry consortia model. And midterm, slowly it will move towards the digital twin technology. If you are aware of digital twins, I'm not going into details, but digital twin is going to come up in all the industrial sector, and all this open source code and simulation framework will be a key pivotal point in creating digital twins of industrial products. And AI-driven maze adaptation, automatic simulations triggering global SME adoption, etc., will be midterm. I think the enabling factors here would be the open data mandates, which means that we should share our simulation data, and other experimentalists should share their experimental data for validation openly. We should have this fair simulation data and funding for developer time, which means that, of course, in a geopolitical scenario, different country, the government needs to come up and provide some budget for research into free and open source software. So in this regard, we really thank the Department of Ministry of Education, Department of India for funding this FOSSEE project. So this kind of project should be funded more and more in different countries to actually give us the resources to build this community. That's one of my view. And yes, so I think I will skip this, but this is something my thoughts again, and I would like to very much hear about your thought process on this. That for academia, I think we should publish the workflows, not only results. So I think this is very, very important. It's not just publishing journal article with the results. We need to publish to make it reproducible. We need to publish the methodologies, the codes, make it freely available so that it can be reproduced and built on. I very much thoroughly believe in this idea. And We have to train method-aware users, which means we have to upskill our students by letting them understand the underlying methodology rather than using it like a software. And we have to maintain a big repository of benchmark validation cases, and we have to collaborate co-design with industry partners. And for industry, I would say that it will be to bring real design constraint upstream, which means that to give us the industrial challenges to target for, share validation targets and data, fund maintenance, not only novelty, and embed open CFD in graduate hiring, which is already happening. It is a very important skill to be in your CV if you want to be hired in the CFD industry nowadays. So just knowing the commercial, how to use commercial tools is not good enough. For communities, of course, we have to curate documentation rigorously. We have to reduce the fragmentation across forks or different versions of the code and make the contribution pathways visible and sustain governance structure. So the future of CFD is not closed. It is open. It is opaque versus inspectable, isolated versus collaborative, and fragile versus trusted. So these are some of the challenges and opportunities that we can map into the academy and industry. So with that, I thank all of you. And the 3 takeaways from my presentation should be: open code is necessary, but not sufficient. Validation evidence and rigorous verification is the bridge. And the community is the main infrastructure in open source codes and software in creating industrial impact. All right. So I would like very much to hear from you, your views as faculty members on how do we turn open source CFD into a trusted engineering infrastructure. And if you have to add on my thoughts, I will be very much happy to discuss with you. Thank you very much. Am I still audible?
Yes, sir. Yes, sir.
All right. So,
the participants can unmute themselves and ask questions, right?
Yes.
Please give them the necessary permissions. Okay, so the floor is open for questions to Dr. Chandan Bose. You can unmute and talk to him. Otherwise, you can also use the chat box to type in your questions.
Hello, sir. Thank you, sir, for a nice presentation. Myself, Dr. Lingayagoda from Dayanasagara College of Engineering, Bangalore. I used to do some CFD consultancy project using COMSOL, and even I used to develop my postdoc in University of Perugia. I worked for 2 years co-development in OpenFOAM. But when we take the project from industry, they give the time duration for 1 week and 2 weeks. Sometimes you have to set up a solver and run for their requirement, and they don't have time also. They always, every week, every day they ask the update. And when I feel it's difficult for to do and give the work in the OpenFOAM, then I switch to even for the commercial softwares. How we can make a community to sometime work on somewhat more, industry projects are more complex one, not like simple benchmarks and all.
Yes, exactly. I mean, exactly that's what I try to propose a solution, that creating automated pipeline and creating reproducible containerized solution is the way to go. So if you think, why can you do it by using commercial software? So what's the difference? What do you feel that why it is possible using a commercial software and not by OpenFOAM? What's your thought on this?
Maybe just clicking only. Our CFD engineers also very good in that they're not aware of, they don't have patience to sit and code the sometime merging the libraries in the OpenFOAM and all.
Yes, I think the keyword is just by clicking and doing it, which is bad in terms of black box, but which also resembles with the automation, right? So we can do the same thing with OpenFOAM. With, of course, it comes with experience that we understand the code, modify, and keep it ready as a ready-to-go workflow in a containerized version, which can be given to any industry to run in any HPC system and give us the equally accurate solution. So that's the way to go, in my opinion. So that's why again and again I told that the reproducibility and containerization of the workflow, not only the code or just the flow around the cylinder on an airfoil, but it's the workflow, including the pre-processing, solution, and post-processing, all including open source software and using automation throughout through scripting, right? Such as, for example, when you actually do post processing using paraview, most of us actually use it like a software. We click it and get different things, which takes a lot of time. If you have to really do an optimization problem and automate the post processing of hundreds of simulation and extract information from that, we cannot do this because it will take months. The PhD student can possibly do it for their PhD, but not the industry people. But we can do the same thing in a more automated way by creating macros, by coding the Python script background and running it directly, submitting the simulation on HPC, which would actually do it automatically and give you all the results required. So I think your answer, to give it a short, is that it needs experience, but it is not impossible by creating an automatic reproducible workflow which can can be packaged as a software.
Thank you, sir.
Yeah, that's my opinion, I think. I think Mr. Pramod has raised his hand. Yeah, please unmute yourself and you can ask the question.
In the chat box, there was a question for you, Chandan.
Okay, I can't see the chat box. Oh, okay, now I can see. 1 minute.
So Mr. Mohammad Amir had put a question for you in the chat box.
Okay, yeah, I got it. Can we make a solver we coded community accessible after obtaining patent for it? Patent is important for our research profiles, whereas same time we would like to contribute to the open source community. So here, to give you a short thing, that softwares cannot be patented directly. So that's one thing to be aware of, but they can be licensed. So if you have really made a software and made it proprietary, you can license it, and which is equivalent to getting a patent or something, but it cannot be directly patented, but the know-how can be patented. So if you want to patent the know-how or the underlying physics of it or underlying novelty of it, you can patent it. Nobody is stopping you to do that. And you can license it, a code, once it is verified, validated, but then it is no more open source code, right? However, you can make it open source license. There are different kind of open source license, such as MIT license, GNU licenses, etc., which allows others to modify your code and build on it with some restrictions depending on what type of license it is very much advisable. Now, if you want to make money out of it by selling the licenses, then it is no more becoming open source code. But of course, if you want to build a company on it and you have to make your own revenue, you have to do that. Many people are doing it, but please be, ethically integrated in your principles. That's my only suggestion. Right. I see two hands on, Arpit, Mr. Arpit and Mr. Pramod. Please unmute yourself and ask your
Yeah, I
question.
have unmuted myself. Am I audible?
Yes.
So thank you, Professor Bose, for the wonderful lecture. I wanted to ask, like, while searching for these tutorials, you can say, or case studies, we see that there have been research labs who are using OpenFOAM for a very long time, and there is a lot of material which is available online. But one of the most common problems that we face is that because of the different versions of OpenFOAM, although you have the material, but it is always difficult to access it and use it. Um, so I have two parts of the question, like how these commercial softwares are designed in which you can still use an old version of the case files or something in the newer versions, and what is
Right.
limiting. Yeah,
Yeah.
so what
Yeah, please
what
go
is
ahead.
limiting like, is there a design, like the way in which OpenFOAM is designed, is it limiting that part, or is there something else? I just wanted to have your opinion on that.
Right. It's a very important and interesting question, and which we face again and again. The first thing, I mean, what I think, to clear your question, that the commercial software, as you said, it works with old version, etc. That's not true, right? So basically, if you see ANSYS Fluent or COMSOL or Star CCM, any of the CFD, they release their own new version every year, and also they release maybe in 6 months, like to 2026A, 2026B, something like that. So they are upgrading their code every day because they have their own research and development team. Our colleagues who are actually expert in open source coding or coding their own solver gets those jobs because they are the most expert people to update the code of an existing commercial software. But what they do is, because their company, they need to make their revenue, they do not make it accessible. They don't allow you to see what changes they are making. All right. And what allows those softwares, even the older version of those softwares, to actually be used as you want, is the version control. And they do it very well because they get paid for it. You give hundreds and thousands of dollars to them to buy the licenses, and with that money they actually hire the manpower which is needed, or software engineers who does these jobs in the back end, right? Which is to make a proper version controls software stack for each version, along with its proper installation guidelines and so on and so forth. And that's a major difference between open source codes, because open source code is community driven. Nobody pays them for it. But it comes, it forms the gap, that actually is a major gap between the academic innovation and the industrial sector, which I tried to highlight. That if you have used OpenFOAM version, a code to solve particular interest of your problem in academia with your PhD student, master student, and you just keep using that for next decade or two, even if the software has completely changed, the programming language has changed, we are so rigid that we do not want to take the risk to port our code into the newest version, because we know that something is working and we just want to train our student using those old version of this, and that will never work in real life. So that will never be used by industry. If you say the current version of OpenFOAM is in June, they're going to release version 2606 probably, and if or version 13 in the openfoam.org, and if you still say that, okay, I'm using OpenFOAM 4 or OpenFOAM 5 because 10 years back one of my students made it work and I don't want to take the risk to update it, what if it doesn't work? Because I don't care about whether it is being used in the industry or not. I just care about using that software to write papers. So that mindset needs to be changed. We have to go towards this reproducible framework of version control using GitLab or GitHub, and we have to have proper README files and installation instructions, and we have to update it and port our codes with the newest version, because with the new version what happens is new contribution comes in, new capability comes in. So if we do not do it, we just left behind. All right. So that is one way that I tried to highlight, that a proper updated documentation and CI/CD unit testing enabled version control is the way to fill this gap. I hope it answers your question.
Yeah, thank you.
Okay, Chandan, I think we should wind up this session now. Otherwise, we'll be delaying the hands-on session. So,
Yeah, yeah, sure.
more questions are obviously welcome to Professor Chandan through the email. So, Paris, could you please type in the email ID of CFD team of FOSSEE once again here, so
Yes,
that people who have more queries for Professor Chandan, they can get back to us after this session.
All right, sure. Thank
Okay.
you. Thank you,
Yeah, thanks
everyone.
to you. Thanks to you a lot. Uh, Professor Ved has already appreciated you and your lecture, so I have already thanked him. So thanks a lot to you for this lecture and being patient and taking all the questions from the participants.
No
So
worries.
yeah,
Thank you.
with this I welcome my team member Paris Palkar.
Hello.
Yes.
Uh,
Before you
am
can
I
switch on my camera and Paris's camera video so that people can see us.
so? Uh, Good morning to everyone.
So
As
over
we
to
have
you, Paris.
seen,
I'm just muting myself now.
sure,
So
sure. Uh, am I audible?
yes, Paris, you're audible.
Okay, okay.
Here is Paris Palkar, who is a team member of the CFD team of FOSSEE. So he will be taking the first hands-on session of this faculty development program. So I would request all the participants. Sorry, I got muted. Yeah, so we'll be starting our first hands-on session by Mr. Paris Palkar, who is a CFD team member of FOSSEE. And I would request all the participants to please be ready with your systems where you have installed your OpenFOAM, and please follow each and every instructions very carefully. If you have any questions, you are welcome to write in the chat box. Our other team members are there to help you, uh, in the process. And if you still have more questions, we'll have a separate Q&A session after this hands-on session. Then we can take the questions there later on. So over to you, Paris. Please carry on.
Thank you, Payal ma'am, and would like to thank Chandan sir as well for his insightful session. Uh, so, before starting today's hands-on case study, can can you people just tell me how comfortable you are with OpenFOAM? Are you are If you are using it for the first time, you can let us know in that way, so we can arrange the speed of the session likewise. So, uh, if you are beginner, still we have very things in our presentation so that you can follow. And if you are using it for the first time, as I can see, majority of the people are beginner only. So I'll keep this in mind. Also, Ivan sir is there from the FOSSEE CFD team. He has pasted an link of Google Drive where you can download the cases. Okay. Uh, Also, the team is live on YouTube as well. So Pranay is there addressing the queries of the YouTube participants who are attending this session on YouTube. The case study files are available on the YouTube as well. So if anyone is interested, they can directly use the link provided. Okay, I'll share my screen. Uh, so if you can see, this is the link that is provided by Ivan sir. If you open this, you will be taken to the day one of this workshop. In day one, today we are going with the introduction to OpenFOAM. So there is the presentation of the session as well as the case files. So whatever I'm going to do here will be replicated or is available on the presentation. You can either follow, or if you missed out on anything, the detailed comments are there in the presentation. If you face any issues, you can type it in the chat box. The team is there to help you. And with that, we are going to start today's session. So hopefully my screen is visible to everyone. So good afternoon, everyone. My name is Paris Palkar. I am working as a project research assistant at the FOSSEE CFD team, and I would like to welcome you all on the faculty development program on CFD using OpenFOAM. Before starting, I would just like you would like to introduce you with our team, Dr. Prabhu sir, who is leading the FOSSEE project. He is a professor at the Department of Aerospace Engineering, IIT Bombay. Chandan sir, Dr. Chandan Bose, sir is serving as the PI of the CFD project, and he is the visiting professor at IIT Bombay, as well as he is working as a professor at the University of Birmingham. and Payal ma'am is working as senior project manager from the FOSSEE CFD team, and whatever workshops or any sessions that we arrange are are only able to execute with the help of these people. So starting from what is CFD, we'll start from very basics. CFD stands for computational fluid dynamics, where as in we are solving fluid flow equation using computers. This software or this method is highly used in academia for and in industry as well for highly complicated problems. One thing is there that experiments are very costly, and as we are involved in some complicated problems, so that we don't need any room for error. For that, repeated experiment will increase the cost. Hence, simulation is a good way to reduce the experimental cost. There are major domains of CFD, but majorly CFD is widely used in aerospace, biomedical, automotive, pharmaceutical, or any heat exchanger industry. There are a number of industries involved in it. So first you can see the video. This is an aeroelastic flutter. This is the horizontal stabilizer going under an aeroelastic flutter, which is a common instability in fluid structure interaction. And this plot is from a IIT heart valve. Uh, it is again a coupled fluid structure interaction. So you might be wondering why CFD? So first thing, as I have addressed, that experiments are quite expensive, and people may don't have the necessary cost to repeat the experiment with different appropriate suitable conditions. Uh, there are some difficulty in measurement. So as I have worked some part in chemical industry as well, so we had to consider humidity part as well in some experiments. So we have to conduct 3 to 4 times same experiment for 3 to 4 times. With the help of simulations, you can reduce this. And again, design optimization is one part that where you can get involved to optimize a particular design of your choice. Let it be an aircraft, let it be an automotive part, or an F1 car, anything of your interest. And also, majorly, it saves time and cost as well compared to the experiments. uh, as Chandan sir has majorly shown you, where is CFD used, but I would like to show you the applications of CFD. So this was the bridge called Takuma Narrows Bridge. It was inaugurated on July 1st, 1940, and it collapsed in this 7th of November in the same year. Initially, people, scientists, and researchers were quite stunned by the phenomena that occurred, and the bridge experienced a large twisting force. It went under oscillation, and the wind speed was around 40 miles per hour. Uh, After some investigation, people came to know that the design of the bridge was a bit that had a bit issue. The bridge went under an aeroelastic flutter, which is a huge instability in FSI. So, moving next, we are going to see the live footage of this bridge. So, as you can see, no human harm was caused. Only cars and a dog died in this accident. But uh, with the onset of uh, CFD, we can tend to reduce these incidents. These are some applications used in aerospace industries. Both are these plots are from the NASA Ames Research Center. These simulations are done in using LAVA, that is NASA's in-house CFD code. LAVA stands for Launch, Ascent, and Vehicle Aerodynamics. So on my left, if you can see, this plot will be for the parachute opening on the Martian surface and how shock waves are captured for this module. And again, this is a shockwave simulation consisting of terabytes of data. So this simulation was carried out within 8 hours. So these were some plots. And now we are coming to the available CFD softwares. Chandan sir have mentioned many of the industrial ready CFD softwares, but I would like to briefly touch upon that. ANSYS Fluent is commercially and widely known to everyone who is working in the CFD domain. OpenFOAM is one. We are going to learn about it in this workshop, in this FDP. Convergent Science, again, commercial software that is used in industries for hydrodynamic flows. Star CCM is again similar to ANSYS Fluent, commercial software, has good amount of financial cost involved as well. And SU2 code, so it is developed at the Stanford University for initially main this caters mainly for compressible flows. However, SU2 code has many more capabilities for incompressible solvers as well. Uh, Now coming to OpenFOAM. So before starting this, let us understand what is OpenFOAM. So OpenFOAM stands for open part, and there is another word that is foam. So it is made up of two words differently. First is open, and the second is foam. Foam stands for field, operation, and manipulation, meaning that you can manipulate and you can make changes into the field of interest. Let us say if you have an incompressible steady state solver and you want to add a temperature parameter or temperature field into that particular solver, with the help of the C++ codes, you can do that. Again, it is not the software; it is a toolbox made up of C++ libraries, which has a broad spectrum of solver capabilities. In our hands-on session, I'll show you how many solvers that OpenFOAM has and how you can pick up a solver of your interest. Also, in OpenFOAM, we can make changes for customization. We can create any simulations of our interest, and it also supports mesh flexibility. So, if you want to work on dynamic meshing, overset meshing, we can do that. And also, OpenFOAM is it helps us to run simulation in parallel as well. So, if you want to run simulation on parallel course, you can do that. So, as you can see, the OpenFOAM project is divided into two parts. One is governed by the OpenFOAM ESI, and another is governed by the OpenFOAM Foundation. Okay, ESI, one is governed by the ESI group, and another governed by the Foundation group. So the thing is, in the ESI version, the updates are quite regular. You get an update in OpenFOAM every 6 months. So the latest OpenFOAM version is 2512. But as Chandan sir said, maybe in this week or maybe in the upcoming week, we should be expecting a 2606, a latest version from the ESI company. And the foundation group, the updates are quite irregular, meaning that we may have updates for 1 year and then we don't have any updates. But still, it is widely used as many people find it very easy to bridge their learning gap to learn OpenFOAM, as ESI might feel difficult for some people. Also, in layman terms, the ESI version is also known as the .com version, and the foundation version is known as the ORG version. Many of you might have installed 2412 and 2512. So this is from the ESI group, and version 9 and version 12, which are the most stable one as of now. So these are from the foundation group. So these are some demo case studies that I have conducted. It is just to show you. These are completely done in OpenFOAM. I haven't used any other software for even meshing it. So here I am passing cold air, and I want to cool this room. So with the help of heat transfer modules, I have done that. In time, this room will be getting cool, as you can see. This simulation is a coupled simulation where we have a 2D cylinder, a dynamic moving mesh, and we also have air particles. So if you can see, the body is moving, the cylinder is oscillating, and once the waves have started forming, the particles move themselves according to the waves. It has velocity of air, as well as we have to model the particles. So it is a coupled simulation. This is done using MPPIC solver available in OpenFOAM. And this is again a static mixer. Again, we are doing a coupled simulation here. I'm injecting some particles from this inlet, and it is being mixed, and it is deposited at the outlet. So these are some of the plots that you can use for your OpenFOAM simulation as well. You can do this as well, but the learning curve in OpenFOAM is a little bit of steep. For that, you have to just stick with us, and we'll help you out doing this. Okay. So now let us get our hands dirty by doing some actual work. Enough of the presentations and all. So I would request you all to be ready with your terminals. Yesterday we had an OpenFOAM installation session for everyone. If by any case someone has missed it, I'm showing you where you can find the installation sheet. If you can see, as Ivan sir has shared the link, in the link there are installation sheets available. You have to start from WSL. Whoever is using Windows, they have to install WSL first, and then they have to proceed with the installation of OpenFOAM 24 or OpenFOAM 9. One thing we noticed yesterday was Ubuntu 24.04 was not supporting OpenFOAM 9. For that, either you can install OpenFOAM 12, OpenFOAM 13, or you have to install it from the source. To install OpenFOAM 13, the installation sheet is available here, as well as if anyone is using Apple's Mac, the installation instructions are there in this sheet. Also, in this sheet, along with the installation, we have what are the changes that are being made in OpenFOAM 13 with respect to OpenFOAM version 7 that we previously used to have at FOSSEE CFD IIT Bombay. Okay, so if you can access this, if someone has missed their installation of OpenFOAM, please do not worry. You can attempt the installation today if you have missed. And maybe if you face any issues, you can write us an email on contact CFD. We'll definitely help you out in it. Okay. So we'll start with creating a run directory. So has everyone their OpenFOAM installed? You just let me know in the chat box. Okay, no problem. OpenFOAM 9 will work. OpenFOAM 13 and 2512 will also work. Okay. Okay, so as I can see, many of you have OpenFOAM installed. Okay, fine. So, okay, fine, OpenFOAM 9 and 2412. So keep in mind that you have to create run directories separately for OpenFOAM 9 and 2412. As I have said, these are two different versions floated by two different companies. So you have to keep in mind to create run directories for two different OpenFOAM versions. Okay. So now let me go to my terminal. And I'm zooming it a little bit. Okay. So hopefully the screen is visible. If not, then just let me know if I should zoom in a little bit. Okay. Okay. So the first command that we have to execute if someone has not created their run directory is mkdir -p foam underscore run. So now if you can see, this should be your interface. Currently I am in tilde, so this is my home. If I do ls, here is my OpenFOAM installed. My run directory is already created. I have my run directory with me. However, as this is a nested loop, even if you have created an OpenFOAM run directory, you can still follow along and try making one. It won't throw any error, so you can try it out. Okay, and just hit enter. As you can see, my system has not thrown any error. This means that either I have already an OpenFOAM run variable. So with the variables that are denoted with the variable, the dollar sign, are known as variables that are defined by OpenFOAM. Okay, so for some people who are using OpenFOAM 2412 or OpenFOAM 9, yesterday we have told them to set an alias. So if you're not able to do this, first thing you have to call the particular version. For me, I'm comfortable working with 2412, so I'm calling that. Now I have sourced my 2412 OpenFOAM version. Now I can do mkdir stands for making the directory in Ubuntu Linux, and -p stands for a nested parent nested loop. Okay, so this is a flag used along with any command that means to create a parent and nested directory. And foam run is the variable that we are going to create, or in that particular variable we are going to run our OpenFOAM cases for 5 days and in future as well. Please make sure not to run any cases irrespective of the foam run, other than the foam run directory, because if you make changes in your tutorial section, it may cause some issues and your OpenFOAM version might be cracked. Okay, so once this is done, how can you check it if your run directory is properly set or not? So for that, what you have to do is you have to write run in small. Okay, you have to write run in small. Once this is done, you have to hit enter. Okay, now first thing, I have sourced my OpenFOAM environment, that is 2412. If you are using OpenFOAM 9, you have to write OpenFOAM 9. If you are using OpenFOAM 12, you have to write OpenFOAM 12 based on whatever alias you have created. Okay, once this is done, irrespective of if you have made the run directory or you haven't created the run directory, you can execute this command. This won't throw any error. Okay, once this command is done, then you have to write run. This run command will directly redirect you where you have created your run directory in OpenFOAM. So initially I was here in my home directory where I have listed out ls. Ls stands for listing out the variables that are available in any particular folder. So in my home directory there were two folders. One was OpenFOAM and another was Snap. So my run directory is created in OpenFOAM. If you want to check, you can check it using, this will be your username, this will be the name that you are giving. OpenFOAM, this will be the username that you have set while creating a Linux username. Along with this, you will have the version of OpenFOAM you are using and your run directory. Okay, please let me know if you have created the till this part, or if we can move. Okay, so Adi, either you haven't sourced OpenFOAM 2412 or uh, you have to set an alias, and for that we have provided installation sheets, so you can have a look. Okay, so uh, yes, Kriti ma'am has also given the attendance link. Okay, Mr. Ashish, run directory is set up. Okay, okay, thank you everyone for the response. Okay, Madhu, thank you. So the run directory is set up now. Now we are going with actual implementation and copying a real case in OpenFOAM. Okay, so to list out anything in your OpenFOAM directory, or let us say I want to see what are the things available in my run directory. So what I have to do is I have to use again the command, same command ls. So ls will list out the things that are available to me in this particular directory. Okay, so as I work on OpenFOAM, so there are multiple cases. However, either some of you may see nothing, or you might be seeing one single case if you were there yesterday for the installation support session. So we tried multiple bits daily cases to be installed in the run directory. Okay, so you can do ls in your run directory to check is your run directory empty or not. This is just a way of watching Linux. We can directly do that using file manager mode as well. I will show you how you can do that in some time. Okay, please let me know if there are any issues till this. Okay, bits daily bits. Yes. So many of the people who attended yesterday, they had bits daily, as we suggested them to have one folder in their run directory. Okay. So now let us copy one case. So the command is given here. First thing, you will be in your run home folder. You have to navigate to your run directory, and once you are in your run directory, your terminal should look like this: your username with your computer name. In my case it is Paris. Now after you have set up your run directory, and cd stands for to take you into a particular folders. Let us say if I am using Windows, or I want to go in a particular file. So what I do is I'll double left click any particular folder that I want to go in Linux or in terminal. We do use this command called cd to go in particular folder. Okay, so this should eventually look like this: OpenFOAM, your name, with the respective version in your run directory. Okay, after this we have to copy a case, a tutorial file, from the tutorial section. So as I have said, OpenFOAM has set of defined variables defined. Foam run is where we run our OpenFOAM cases. Foam underscore tutorial in caps is where OpenFOAM tutorials are available. If you want to see where the tutorials are available, what you can do is you can just write TUT in your terminal, and please make sure to check the location where you are in. Now currently I am in a different location. Once I hit TUT, now I am in a different location. Okay, so there is a standard set of rule in OpenFOAM that either you can start from scratch, or to make up any case you can take the tutorials folder, and starting from tutorials you can take up the case, copy it in your run directory, make notable changes and run it according to your own convenience. Okay, now I am into this tutorials folder. I want to view what are the things available in this tutorial. So what I will do is again I'll do ls. So it will list out everything that is available in this tutorials folder. Okay, and I'll hit enter. Now if you can see, I'll zoom out my screen a little bit. Okay, it's fine. So there is all clean, all collect, all test. So these are for to test some tutorials. So there are DNS, input, output, basic, combustion, compressible, discrete methods, electromagnetics, finite area, heat transfer, incompressible, Lagrangian particles, mesh, other modules, multi-phase, pre-processing, so resources to learn more, stress analysis, and verification and validation. For this part, we are particularly interested in the incompressible part. So as I have said, if I want to go in a particular folder, what I will do is I'll write cd, and I want to go in incompressible. Okay, so I'll just write inc, and I'll hit tab key on my terminal, so it will understand what I'm trying to do. Okay, now if you can see, earlier I was still in tutorial section. I listed out what are the things available in my tutorials. I found incompressible is there. I want to go in incompressible, so I did nothing. I just I have just written cd. CD is telling the terminal that please take me to this incompressibles folder. Okay, I have written it here, and now you can see me. I am currently in the incompressible section. Okay, again I will list out everything that is available in the this folder. Again, there are multiple solvers that are available. Okay, but as of now we are going to use icofoam. So let us do it. Ico, if I just write ico and hit tab, it will understand what I'm trying to do. Okay, so I'll write cd. Now I want to go in icofoam, so I'll just write ico, and I'll hit tab key on my laptop so that the terminal will understand what I'm trying to do. Hit enter. I will do ls again. What are the things available in icofoam? Okay, so there are three cases. One is cavity, one is cavity mapping test, and another one is elbow. Okay, so I want to go into the cavity folder, so I'll do cd cavity. So yeah, if I have just written cavity, now it will understand I want to do something related to cavity, but as there are two folders with the name cavity, so either if you want to go in cavity mapping, so you have to just write M and hit tab. It will understand what you want to do. Or else if you want to just stay in the cavity folder, just hit enter. Okay. Now you can see I am currently in the cavity folder. Okay. So again I have to go into the cavity folder as there are folders in folders available here. So let's do that. And so we started from tutorials, then we went in icofoam, incompressible, then we went in icofoam, then we went in cavity folder, and again we went in cavity folder. If anyone is facing any issues, what they can do is they can directly open their OpenFOAM. Say you are in your run directory. So if you have to just write tut, you have to do explorer, explorer dot exe space. The space here is very important. Okay, you have to just write explorer dot exe dot and hit enter. Okay, so I can see this in a file manager mode. You can see basic, conversion, compressible, discrete methods, DNS, etc., etc. Uh, One approach was using terminal, and this approach is using the file manager mode. Now I want to go in the incompressible folder. I'll double click this. Again, I want to go in the icofoam folder. I'll double click it. I want to go in the cavity folder. I'll double click it, and again out of the three cavity cases, I want this particular case. Okay, that has 0, constant, and system. Okay, so what I'll do is I'll just click this part, right click it, copy it. Okay, for anyone who is not understanding, what you have to do is from your run directory, you have to just write tut. You will be redirected to the tutorials. From here, you have to just write explorer dot exe
Sorry for
space.
interrupting you. Hello.
Hmm?
Paris,
Yes,
actually, we have put the attendance link.
sure, sure.
I am putting it in the chat box once again.
Sure.
So I would request all the participants to kindly take a pause and mark yourself present on the attendance sheet. I have just put it on the chat box. I have also put it the same link on.
YouTube as well, right?
I have also put the same link on YouTube live chat. So participants who have already registered for this FDP, please mark yourselves present there as well. We are just taking 1 minute pause and we'll restart again. Thank you, Dr. Okay, I think the participants have done. So, Paris, we can continue.
Sure, sure.
Paresh,
Sharing my
Paresh,
screen. Yes.
can you increase your mic volume little bit?
Okay. 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 I have done it. Is it okay?
Yeah.
Fine. Fine. Hopefully my screen is visible.
Yes, Paris.
Okay. Thank you once. So, is everyone able to follow along till this step? Uh, you will be redirected to the tutorials part. You have to go in incompressible section. Then in IICOFOAM part, cavity, and you have to copy this first cavity folder. Once it is copied, then coming to your terminal, you have to write run. You will be again in your run directory. Hit explorer dot exe space dot. I have pasted the same command in the chat box as well. Explorer dot exe space dot. Okay, and you will be in your run directory. So just paste it here. You can paste it. Okay. If I do Control V, so it will ask me to replace it. But as I have it with me, I'm not doing it. Okay. And still, if you are facing issues with doing this, we have the case files readily available in this section, so you can directly download this case file and you can directly paste it into your run directory so that you don't face any issues. But it's a good way to understand how to copy a case. For that we are doing this. Okay. Okay, good. Fine. So now coming to the command. So we have seen how to manually copy it, as well as how to copy it from the Linux terminal. So I'll show you. So this is what it would look like if you download the cavity.zip folder in your run directory. This you will have your zip file. You have to extract it, so you will have the cavity folder as well with you. As of now, I want to go in the cavity file. So this has three folders: 0, constant, and system. Okay. If you want to copy any case particularly, so what you can do is you can do cp-r home underscore tutorials. Hit tab, it will understand on its own. Incompressible, IICOFOAM, cavity, and I want cavity again. Again, you have to give a space here. This space will mean that I want to necessarily copy this cavity file here only. Okay, so this space denotes that, and after that you have to hit a dot. Okay, so this means that the cavity file is copied, but as I have it with me, so I'm directly going to demonstrate using this. Okay, hope everyone is done till here. No issues. Okay. Uh, so what you can do is, ma'am, the link is shared for the FDP. You can have access for the presentation as well as the case. You can directly download this and paste it in your run directory. So the command is, I'm pasting it here. Just go to this. Space. Ivan sir has given the case files for today. You can check this out, and you can directly copy this command and paste it in your run directory, so that this particular folder will be installed in your it will be copied in your run folder. Okay, and also with this we have to create a touch folder. Touch is used for creating files related to paraview as well as any empty file if you want to create. So what you can do is write touch, let us say FDP. You can name it whatever you want, it's up to you. FDP dot foam. The dot foam extension is quite necessary and important. Okay, you can name it whatever you want. The dot foam extension is important. Okay, so after copying this particular cavity folder, first list out what are the things available in it. First is 0, another one is constant, and third thing is the system folder. Okay, after doing this you have to write touch, let us say FTP dot foam. Okay, I have created it, it hasn't thrown any error. I'll do ls again. So now I have 0, constant, system, as well as an FTP.form.
Paris, sorry to interrupt. Just go a little bit slow.
Okay, fine. So if you want to create, wait, I'll paste the command. Okay, using the Linux, you can use FTP.form. So just paste this command in your cavity folder. For the ones who are using OpenFOAM 9 or OpenFOAM 12, the way is a bit different. So as you can see, the tutorials were available in the USR folder. If you source OpenFOAM 9, let us say I'm sourcing OpenFOAM 9 and I am writing tutorials, so they are available in OpenFOAM 9. Okay, so there is a change in it, so please make sure you follow along. For this I am using OpenFOAM 2412. However, there is only a slight change for OpenFOAM. Okay, hopefully everyone is able to follow along till here. If yes, we'll move forward. Okay, okay, so we have done everything in this. If you are still not able to do it, do not worry. These presentations are available with you, so you can try them out on your own. And now let us understand the basic OpenFOAM case structure, what an OpenFOAM case file or a case study would look like. Okay, you might be felt overwhelming by watching all these files, but please do not worry. We will get them one by one. Okay, so as we have seen, if I do ls here, I have three folders. Okay, 0, constant, and system. So we are going to look out what every folder serves for. Okay, so this zero folder, the zeroth folder contains all the information regarding your initial as well as boundary conditions for your simulation. Also, if you are working with turbulence model, then you have to include turbulence variables as well in the zeroth folder. As we are solving partial differential equations, which needs zeroth boundary conditions, hence it is known as the zeroth folder. Okay, moving forward, we have the constant folder. In constant folder, we have information related to your geometry, that is you can paste your CAD file into it. You have information related to your mesh, if you are creating any if you either you are importing your mesh or you are developing it from scratch. So it depends on what you are doing. The constant folder will have information of both. It also has other folders like transport properties and turbulence properties. So transport properties are the fluid properties, what viscosity we are using. If we are dealing with non-Newtonian fluids, then we have to define the transport properties very carefully. Okay, and if we are dealing with turbulence that we are not going to touch today, we can fill the turbulence properties as well, which particular model we are using, which particular regime in which we are working, and on or do we want to print coefficients or not, etc., etc. And then we have the, and also the constant folder is known as the constant folder because while the total life of the simulation, properties that we have in the constant folder do not change at all, hence it is known as the constant folder. And system folder. So system folder has all the executable directories. Let us say if you want to create a mesh, you can create it with the help of block mesh. So there is a block mesh directory. Then there is a control dictionary. Control dictionary is used to control your simulation, that for how long duration you want. If you are working on a transient simulation, what delta t do you want to choose, what should be your start time, what should be your end time. Do you want to save only a last time step for saving your storage, or if you want the whole files, at how many intervals your solution should be written, everything. If you want to plot forces on a particular body, everything is denoted, or it is detailed in a detailed way described in the control directory. FE schemes and FE solutions, I'm not going to touch that. It's a bit complicated for the initial part, so we'll skip them. But keep in mind, as OpenFOAM is based on finite volume method, so FE schemes and FE solution govern which schemes we are using for pressure and velocity, and solution FE solution has the tolerance for our conversions that we have set. Okay, and these are some other files that we can include as well if we want. Okay, and there are some basic post processing tools as well. One is paraview, majority of you might be having this, and another one is the gnu plot. So if you want to install gnu plot in your terminal, you can use this command sudo apt install gnu plot -qt. It will take 5 minutes of time, it won't take much, but I would suggest not to do it now, you can do it later as well. gnu plot we generally use for plotting. If you want to plot your residuals, so you can do that using gnu plot. Okay, and okay, now coming up to the case. So if you can see, this is our cavity folder, cavity, the geometry of the cavity particular file. A closed lid is at the top wall. Okay, it is in 2D view. Okay, and we are moving the top wall or the top lid with the velocity, that is ux, with the speed of 1 meter per second. Okay, and the dimension of this, the length is 0.1 meter. I have calculated Reynolds number using this formula, and for my case right now I am using Reynolds number equals to 10. Okay, I'm repeating again, this is the geometry. The walls colored in gray are fixed walls, they are not moving, and the wall colored in black is moving in right direction with the velocity of 1 meter per second. Okay, the dimension of these length and width is 0.1 meter. Reynolds number is calculated using this formula. For my case and for yours as well, for the first case, the Reynolds number will be 10. The viscosity is mentioned here as well, but we'll see how we can modify that. Okay, and if you want to check what are the things available in your case for particular cavity case, so there will be a zeroth folder. If we go into it, close this first. So in the zeroth folder, there will be two files. One will be for pressure and another will be for velocity. Okay, this is shown here as well. In the zeroth folder, we have fields related to velocity and pressure. In the constant folder, we have files only transport properties here, as we can see, and likewise it is for system folder as well. You can see there are 6 files, and here as well there are 6 files. Okay, so this is an overview of the case structure that we are going to solve. The case structure will not change irrespective of the simulation that you are working with in OpenFOAM. If you are working with OpenFOAM, these 3 files should be there. What are these? Zeroth folder, constant folder, and system folder. If you are working with overset meshes, these 3 will be available. If you are working with some Lagrangian particle tracking, these three folders will be available. If you are working, let's say, with multi-phase simulation, again these 3 folders will be there. Yes, but there will be multiple files that are available in the folders in zeroth, constant, and system. But this is the main case structure of OpenFOAM. So you have to keep in mind while setting up any case, these 3 folders should be present. What are those? 0, constant and system. Okay, now let us create the block using block mesh, and we are meshing it as a single block. So in your terminal, uh, we have a session planned just after lunch for block mesh. So I'm not going in very detail for block mesh. This is just for you to get a feel of how to run a case study or how to run a simple case in OpenFOAM. For that, I'm showing you. So you have to just write block M capital SH. Okay, so you have to just write block mesh. I'll zoom out a little bit so that you please make sure you are in your run folder, and you will be seeing this cavity folder. Inside this cavity folder, you have to type block mesh. Okay, once you type block mesh, now you will get some output. We'll discuss about this. So it is saying that it is creating mesh from system, and there is a file called block mesh. So it is creating block mesh or a single block from this file. It is creating edges, it is defining faces, it is defining the topology as well, and also it is creating the mesh topology. If you see, there are some basic statistics that total number of how many total number of faces are there. If there are any internal faces, if we go in some complicated meshing, there are internal faces available as well. It also checks the block consistency. uh, it checks if there is any offset with this. It is creating a polymesh folder with from block mesh, so it is stored in your constant folder. As I have said, this is the mesh we are dealing with, hence it will be stored in constant. Okay, and ijk are nothing but the vectors. These are the cell size that is discretized in x, y, and z direction respectively. So this is our bounding box. What are the total number of points, total number of cells, and total number of faces available here? And again, we have patch 0, patch 1, and patch 2. What are those? Moving wall, fixed wall, front and back. So if you see this geometry, as I have said, we have three walls. First is 1, 2, and 3. These are fixed wall. These are not moving. So if you imagine a cube, so the left, right, and the bottom wall is fixed. It's not moving. Okay. The front and back wall is fixed. Okay. It is also not moving. It is 2D. And the upper lid, or we are naming it as moving wall, it has been defined here. Okay. So there are there are some things we have to tell. Okay, so please let me know if you have done till here. Okay, yes, so it might be the reason if you are using any other other open form version, so it may happen like this, Ashish sir, but it's not a big thing to worry about. Okay, 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 done till now. Okay, Dr. Ankit, fatal error. Okay, hopefully you have covered it here. Okay, the question and answers. Yes, yes, we are not dealing with cell zone here, sir. Ashish sir, we are not dealing with cell zone, particular cell zones. So this cell zone will be covered in porosity lecture. So in that it will be defined in more. Okay, now if you want to plot anything using the GNU plot, so there are two ways to run your solver. Either is, once you have done block mesh, you have to do nothing, you have to just write the name of the solver. Okay, for the ones who are using OpenFOAM 12, they may have to write foam underscore run, FOAM in small, and R capital UN in small again. Okay, so instead of icofoam, they have to run foam run, and their case files will be available under tutorials in compressible fluid, icofoam cavity case. Okay, once I hit icofoam, the simulation will start to run. Okay, I'll zoom out a little bit so you can see. uh, we have done nothing, we have just executed two commands. Okay, please just get a feel of OpenFOAM. I'll tell you what are everything in detail in using BlockMesh and Snappy Xmesh that is scheduled for after lunch. Okay, So the simulation is completely run. Okay, the simulation we are completed with the simulation. It has given me a prompt as the simulation is ended as well. Has everyone followed till here? Okay, okay, Martin. Okay, fatal error. Okay, so if anyone is using OpenFOAM 12, so they have to type this command instead of microphone. Okay, fine, 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 fine. Okay, so once this is done, uh, you can do ls. Now I have some time directories as well. Now I have 0, 0.1, 0.2, 0.3, 0.4 and 0.5 respectively. Okay, as in my control dictionary, that is under system folder, I have specifically mentioned that I want to run my simulation for 0.5 seconds only. Hence these 5 time directories have been saved. Okay, and again in that system folder, there is a way. I'll show you. So for my ease, I am particularly using VS Code, but you can use anything. It's up to you. You can use Nano, you can use Gedit, you can use Vim, or you can use Notepad as well to edit these files or to watch or to have a watch on these files. Okay. So I'm now in the system folder. I'll just show you what system folder looks like. Okay. I'm not zooming into my screen. Just hang on with me for 2 minutes. Okay. So the application name is IITFOAM. We are starting from start time, and what is the start time? It is 0, and we are ending or stopping at end time, and the end time is 0.5. Hence, I am having 5 time directories. Okay. Then my delta t, or at how many iterations I want my icofoam to solve the this solution is 0.05 time step, and these are some controls that are available. Right interval is 20. So if you see on my terminal, things are written at 0.005. Okay, so this is a very big output, and if you scroll up you have to go a bit upwards. This is a very simple simulation, so it does not take any much time. So I've just written icofoam. It has started. The time loop started from 0.05 was the first simulation iteration, and consecutively we moved with 0.01, so on and so forth till 0.05. Okay. Hopefully everyone is done till here. Okay. Now I am going to show you. No, delta t is not chosen arbitrarily. There are ways to do that, Narayan sir. I'll tell you about that in the Q&A session. Okay. If everyone is done till here, then I'll show you how you can open. So, okay, Mr. Ashish, you have to write block mesh. Okay. Use this command block mesh for executing it. Yes, yes. I'm going to take the same session in afternoon as well for snappy expression block mesh. Okay. Um, okay. So you are in system, Adi. Hence, it is not running block mesh. Okay. So if you are done till here, what you can do is you can either do explorer.exe here on your terminal. Explorer.exe. Again, I'm telling the terminal to open it in a file manager. I have it open with me. So there is a .foam file. Remember we created uh, fdp.foam. We have to just double click it. Okay. So this will take a bit time. If you can see, this is the paraview interface. Okay, I'm deleting this file for now. If you have installed paraview, what you can do is on your search bar you can directly search for paraview. Okay, and depending on the version it will prompt up and you can open it. So I have it I have it open with me, so I'm not doing it again and again. But here you can see your RAM that is being consumed. So as of now, out of available 15.2 something, my 11.9 GB is being consumed at the background. So I have my presentation open. I am running my OpenFOAM cases as well, and Google Chrome is open as well. So this that is consuming the RAM, but it's fine. But if we are doing any post processing, high quality rendering or volume extraction, so we need decent amount of RAM to render that particular plot. So how you can visualize your simulation in Paraview? So you have run your case. Now you want to visualize how you can see the plots in Paraview. For that, you have to go in the upper ribbon called File, and here there is a command called Open. Okay, you will be in the Open File box. Here, what you have to do is from the cavity folder, you can switch in between tabs using Alt tab. So right click here and just copy the address. Okay, you can click here, right click here, copy the address, go in your Paraview file, and in the name of the file, you have to just paste it and tell him to navigate. Okay, so I have ftp.foam. So the .foam files or the .vtk files, we can visualize it using Paraview. So you can click it and hit OK. So this is one way to open that. Another way is directly simply by double clicking on the FTP or the .foam file that you have created. Once done, you have to just simply hit apply, and your simulation is in front of you. Okay, so you can uh, set up these plots. Okay, so these are the legend for pressure particularly. So as this is cell finite volume method and we are particularly interested about cell centers, so there will be two things. We have zone values, the velocity zone values, cell zone values, and we have cell center values for velocity and pressure. So we basically use the cell center values. Okay, so I can visualize the velocity and I can normalize it as well. For someone who is using Paraview versions above 6, so there might not be any cell center value available. So there is a filter available in somewhere here in Paraview that tells to cell zone to center or something like that. Filter is available, so you can click on that filter and you can plot it accordingly. Okay, so this is my velocity plot. Okay, you can see the velocity 1 meter per second is increasing in the upper region and small vortices are forming. The downward velocity is almost not zero but almost near around negligible. Okay, so and if you want to visualize your mesh, so in the upper ribbon tab from surface, you have to just change from surface to surface with edges. Okay, so this is your mesh, and if you want to visualize your smooth body, from you have to switch it to solid color. Okay, so we have our 3D mesh. Again, as OpenFOAM is based on finite volume method, so we have to create a 3D model of the particular body, and then we have to scale it down to 2D. Okay, so firstly we are creating a 3D body, and then we are uh, extruding it into a unidirection for, let us say, z, negative z, or the whole z direction. This tells OpenFOAM that we are particularly not interested in solving in this z direction, but only in x and y. Okay, so this is your mesh visualization. You can change it with surface if you want. This will be your surface. Okay, if you want to visualize your mesh, you have to change the filter to surface with edges. Okay, and you can view the plots using, this is the pressure plot, this is the velocity plot. And if you want to play with the color schemes, so if you go down in the properties panel, go down in the edit section. Okay, the edit section, so there is select a color map from default presets. So there are multiple color fonts available, so you can use any one of them. Okay, these are some things. Post-processing things, this comes under post-processing. So yeah, we have a dedicated session on post-processing as well, so not going in depth. So we can take a slice maybe here in the Z direction, and if you can see, I'm just taking out a small section of this entire domain. If you can see in this Z direction, I'm taking just a small part. So only the small part is now being shown. Okay. Again, you can see your mesh, etc. here. Uh, you have to just triangulate the slice, and your mesh will be visible. However, I'm not going to show you this. My concern is to show you how you can plot vectors on this plot. Okay. So first thing, you have to load your .foam file. With the help of that, go on the upper ribbon and go for a slice filter. Okay. Once the slice is taken in the Z direction, then click on the slice and go in the filter called glyphs. Okay, there is a filter just side to the slice section called glyphs. Okay, select it, and it is asking for some values. So orientation arrays for the vectors of the particular variable we want. So that is u. Scaling array, we don't need any scaling array, and let us keep the all the values as default. So as you can see, noticeable rotational zone is visualized. Okay, in this section. Let me take my legend. Okay, and what you can do is you can keep this as solid colors, and you can change your slide to maybe velocity, so that you can plot your streamlines even properly. Okay, and again, if you want to add things up, then there are sources. You can say you can add 2D text or 3D text, or it's up to you. Annotation, if you want to say write a text, so let us say lead driven cavity, and I want it in the center. Please do not worry. These are some of the things that we can do. We have a post-processing session as well, properly post-processing session schedule. So just hang on with me, just to check, just to get a feel how OpenFOAM works. Okay. Uh, so we have seen how to plot velocity contours, pressure contours, streamlines. If you want to plot streamlines, what you can do is there is a filter here that you can take, stream tracer. It is known as stream tracer. To close other values, take the stream tracer filter, and if you can see, this is the top corner, and at the bottom there will be the another part. See, this is the bottom line. So maybe you can take this line, extend it a little bit, so you can tell that I want streamlines in this section, and just hit apply. So you can see the streamlines. Okay, and these streamlines are based on the RK method that we do in mathematics, numerical methods. So how the streamlines are plotted, it is given here. How the interpolation is done. So if you want forward interpolation, backward interpolation, or we want both included, it depends. Okay, so we have seen how to plot streamlines, vectors, and how you can save an image. So say if you want to save it as an image, what you can do is, let us do one thing. This cliff, this slice, I'll keep it as open, and the lid driven cavity, I'll change this to say 40. I want it bold. Okay, so this will be my section. Okay, I want to capture it. So how you can do that? So there is a filter for camera. Okay, here you can just click it. It will be redirected to your cavity folder. You can name it anything. Let us say velocity, or we can say vector. Okay, vector, and in which type you want to save it, PNG, JPEG, VTK. So I'm going with PNG, and here is the image resolution. If you are not sure, you can directly click here and choose the appropriate image quality. Let us say we'll go with full HD. Okay, And do you want to change the background color? Do you want transparent background, or do you want to save it in the background? Depends on the setting. As of now, let us keep everything as constant and hit OK. So hopefully it has taken a picture. I'll just refresh it, and you can see a vector dot image is generated with our lead driven cavity case. So whatever you are going to write will be displayed in this, and you can capture it. Okay. And yeah, this is a take home assignment. We have given the case files and the case presentation and the case file. So what you can do is you can check for different Reynolds number. For this case, the Reynolds number was 10, and because of that we were seeing a single recirculation zone at the center. But as we keep on increasing the Reynolds number, you can see some small vortices as well at the corners. So as the Reynolds number increases, the dominant vortices are also visible. Okay. uh, if you want to do it, so you have to do nothing but go in the constant folder, go in transport properties. As of now it has been set to 0.01 for Reynolds number 1. I have given you how to calculate Reynolds number in the formula. You have to just change the viscosity value and based on the Reynolds number, calculate the or visualize the vortices. Okay. So keep the dimension and velocity input value as constant and just change the viscosity value. Okay. You have to do nothing. You have to just change the viscosity value present in the constant uh, transport properties. Okay. So that's all from my end. Actually, I have to make it a little bit faster. But definitely after today's session as well, if we have time, I would love to take your question and answers. Okay. So if you have any questions and answers, you can post it in the chat box. Thank you. Thank you for your patience and time.
Yes, we can also take the questions through email later on.
Yes.
Whatever questions comes in your mind, or whatever while you practice later on, you might face some issues. So we will be there through email. And I think we should wind up this session now, because we will be getting late to start the session in
Yes.
the second half.
Yes, ma'am.
So it's almost 1:15 now. I think we should join back around 2:15, and I would request all the registered
Sure.
participants to join a bit early, around 2 p.m., so that because we have a capacity of 100 on Google Meet, and the rest of the participants are requested to join over YouTube. So early access will be better. Okay, so I would request all of you to join around 2 or 2:05, so that we can start at 2:15 sharp. Okay, so in the second half, we will have a lecture session by Professor Hari Krishnan of QSAT, and then we will have another hands-on session in the second half. So, winding it, yeah, thank you all for being patient, and I hope you all found these sessions useful, today's morning sessions, and I hope all of you have marked yourselves present on the attendance sheet. Okay, so taking a break now. See you in the second half after lunch at 2:15. Okay, thank you. Bye bye. Good afternoon, everybody, and welcome back. Deepa, could you please turn on my camera so that I can use my camera? So maybe from your side there is some settings. My camera and Professor Hari Krishnan's camera also. It's good afternoon, everybody.
Hello, Payal.
Ha.
Video camera you can start. There is no setting from my side.
Okay, so maybe my camera is not working. It's okay. I'll try later on. So welcome, Professor Hari Krishnan. Maybe you can switch on your video so that everybody can see you. Yes, welcome, sir. Yes, so now we will have a lecture session by Professor Hari Krishnan. And Professor Hari Krishnan is an esteemed faculty partner of the CFD team of FOSSEE, IIT Bombay. Let me first introduce him and then we will start his session. So, Dr. Hari Krishnan is an assistant professor in the Division of Mechanical Engineering at the School of Engineering, Cochin University of Science and Technology, which is known as QSAT, at Kochi, Kerala. His research interests span heat transfer, multi-phase flows, indoor air conditioning, and data-driven methods in mechanical engineering. He earned his PhD in 2019 from the Department of Mechanical Engineering at IIT Madras, where he was honored with the IIT Madras Institute Research Award for his doctoral thesis. He also holds an MTech in the Thermal Power Engineering from NIT Trichy and BTech from GEC Thrissur. Dr. Harikrishnan has an impressive publication record, including 11 peer-reviewed articles in international journals and 20 international conference presentations. Beyond his academic role, he is an executive faculty partner with the FOSSEE IIT Bombay community, where he is very actively promotes open source software like OpenFOAM. For the past 6 years, he has been instrumental in leading the OpenFOAM workshops, hands-on training sessions for students, research scholars, and faculty. Additionally, he has guided internship students and published 6 case study projects in the FOSSEE CFD repositories. Recently, he was honored with the Outstanding Contributor Award at the National FOSSEE Awards 2025 by the Ministry of Education, Government of India. So this was a brief introduction of Professor Hari Krishnan, and he is a true patron of our project. Whenever we are looking for a support, he is always there. So thanks a lot to you, Dr. Hari Krishnan, once again. And over to you. We can start your lecture now. Just to confirm, Deepak, the YouTube link is also working right now, right?
Yes, ma'am.
Okay. Fine. Then we can go ahead.
Ma'am, sir cannot unmute themselves. Okay.
Professor Hari Krishnan, you are muted, so we cannot hear you.
I guess.
No, it is muted.
Permission.
So from the eStudio team, is it muted from there?
No. I have given the permission.
Okay, Professor is writing that he doesn't have control. So how to resolve this? So Professor, you cannot unmute yourself, right? The button is disabled.
अरे मैंने कोर्स बना रखा है। अरे यार लॉग आउट
Okay, now maybe you can try once again, Dr. Harikrishnan.
Madam, Hari Krishna is not there.
Yeah, actually he has by mistake exited from the meeting. So, but the capacity is full right now, right? So should I exit and try again? In the meantime, you can make him enter.
Yes, yes.
Okay, okay.
Am I audible?
Yes.
Yes, you are audible.
Yes, yes. Thank you very much. Sorry for the inconvenience. There was a technical issue. I think we have a restriction of 100 people. Unfortunately, I was exited from the meeting. I'll just share my screen. Are you able to see my screen? Okay, thank you. So first of all, let me thank FOSSEE team for giving me an opportunity to give a lecture or session on OpenFOAM, especially related to meshing. So so before that, how many of you are already familiar with OpenFOAM? I just want to have an idea. Before this workshop, can you just say yes or no in comment box? I think most of you are familiar. Some of them are beginners. Okay, thank you. So today I will be having a session of maybe around 30 minutes. I will give a brief overview about OpenFOAM, what exactly we do in OpenFOAM in terms of meshing, basic concepts, tools, and best practices. It's close to 30-minute session. So to begin with, as I said, we will in the forenoon session, Professor Chandan and member from FOSSEE already explained or already gave a brief overview about OpenFOAM. And I hope you might have did some tutorials, cavity tutorial or some basic case in OpenFOAM. That was a hands-on session. And today I will start with that. So we'll just start with the basics of CFD, very 1 or 2 slides related to CFD and OpenFOAM, and some brief idea about OpenFOAM, followed by meshing. In meshing, I'll be discussing about what are the tools or utilities available in OpenFOAM, that is block mesh, snappy hex mesh, and other packages, like if you have mesh made from some other third-party software, how we can use that in OpenFOAM. Those things I will be discussed. And after my session, there will be hands-on session for as we see the schedule, we can see hands-on session especially related to meshing will be there after my session. Okay. So I hope you are already familiar with computational fluid dynamics. We'll start with that. So basic idea behind mathematical modeling is we essentially model physical phenomena by using mathematical equations. When we model these physical phenomena using mathematical models or mathematical equations, we essentially use assumptions. These assumptions are very, very essential when we actually see the results by using mathematical model. Assumptions in the sense sometimes we say it's a laminar flow, sometimes we say it's a turbulent flow, two-dimensional flow, one-dimensional flow, steady flow, viscous flow, in-viscous flow. All these are actually assumptions. So once we have mathematical equations, we try to solve it by using computers or manually, right? So if you talk about computational fluid dynamics, the basic governing equations behind fluid dynamics is Navier-Stokes equation. As we know, it's a partial differential equations, and computational fluid dynamics, with the help of computers, we will be actually trying to solve these partial differential equations by using certain schemes. So we generally use schemes like finite difference method. These are, you can say, discretization schemes, or these are the methods in which we solve a partial differential equations. We convert these partial differential equations into certain algebraic equations. Algebraic equations in the sense we convert a partial differential equation into a matrix equation, that is in the form of Ax is equal to b, and where x is going to be our unknown. And if you talk about fluid mechanics problem, these unknowns can be velocity, that means x component of velocity, y component of velocity, z component of velocity, or pressure, or any other parameter. And if it is a heat transfer problem, we can have these unknowns as temperatures, etc. Right? So various CFD, I'm not going into the theory behind CFD. I will just slowly move towards the meshing part. Before that, we know that various CFD packages are available. I think earlier session someone was explaining, someone from FOSSEE team was explaining about different CFD packages and what are those CFD packages. Some of the most popular like ANSYS, Fluentstar, CCM, COMSOL, Autodesk, CFD, Simulia, OpenFOAM, Jerry's, and SU2, and some other CFD packages were also there. And interestingly, you can see the right hand side, what you see in the right hand side, these are like open source softwares. We know that these commercials, the left hand side, what we see is commercial software. These are very costly. You may need to pay millions of rupees if you want to have a license, education license, or even a commercial license. So on the other hand, these open source softwares come with free of cost. Anybody can actually download, anybody can actually use. You're free to use. You can also do some sort of consultancy, freelancing, etc. Nobody is going to question you, right? So we are focusing more onto the open source part. So OpenFOAM is one of the most popular open source CFD packages available. And what are the advantages? Like free of cost, obviously free of cost, and source code modification. You can see each and every code available or within this package. C++, it is written in C++, or if some other software, it may be C program. All these codes are actually visible to us. It is easy for us to have modification of the existing code, and it is also easy for us to collaborate with a foreign partner or foreign university faculties, etc. That means, let's say I am working on a CFD project. Let's say my university is having ANSYS, but I have a collaborator who is working some other university. If you don't have an ANSYS license, he won't be able to collaborate with me properly. On the other hand, if you have an open source software, depending on open source software, it's easy for us to collaborate also. But at the same time, we have more cons also. I saw someone was commenting about cons of open source software in the previous session. So obviously there are a lot of cons, like such as lack of documentation. For example, if you see ANSYS Fluent, the official user guide contains almost 2,000 to 3,000 pages. Each and every option, step-by-step procedure is explained in a detailed way in that documentation. On the other hand, if you see OpenFOAM, the official user guide, it contains only 200 to 300 pages, and only very, very important aspects are only covered in that particular user guide. So if you are not familiar with open source software, if you are not having a group of people who is actually working in open source software, it will be very, very difficult for you to actually move forward. And second thing is no GUI, graphical user interface is not there other than post-processing. That means if you want to generate the geometry, if you want to make the case file, if you want to run the simulations, we don't have any graphical interactive graphical interface. We can actually do the things by clicking. Rather, it's a set of codes. You will find some text files. You will find some normal text files in which you need to open it, you need to modify it, then you need to run the simulation through terminals. Because of that, it is not that user friendly. And as I said earlier, the documentation is a very crucial part in terms of documentation. FOSSEE is actually IIT Bombay team is actually doing a lot of good work in documentation. For example, through case study projects, through research migration projects, through research migration projects, they are actually through students. So FOSSEE team is actually trying to document the options available in OpenFOAM that with they are trying to explain, or they are trying to make a documentation corresponding to each and every options available in OpenFOAM. I will share some of my examples. I was mentoring few students through FOSSEE, and some of the things what we did during that time I will explain the upcoming slides. So before we actually invest time in learning, okay, we understood it's free of cost, but whether, let's say we are all teachers, most of them are teachers, and you may have a doubt that whether there is an employability related to this. So obviously, compared to commercial softwares, it is not that widely accepted. But if you see companies like major companies like these are major companies, Boeing, Pfizer, GM, AMD, 3M, Magna, these companies actually started adopting. They are actually moving towards open source softwares. Similarly, you can see some young companies like startups, they are actually using. See, most of the cases startups they won't be able to afford these commercial licenses, so they are eager to explore the possibility of open source softwares, and they started adopting it. So job opportunities in these companies, obviously, if you have some skills in OpenFOAM, especially if you are trying to recommend this particular software to students, it will be useful. And as I said earlier, so we don't have actually GUI, that is graphical user interface is not there. I hope through previous section, you might have seen, those who are not familiar with OpenFOAM, we mostly do command. We actually type commands through terminal to make geometry, make mesh, run the simulations, and only for visualizing the results, we have paraform or paraview, right? So command line interface is actually used other than GUI. So initially, you may feel some difficulty if you are comfortable with ANSYS softwares, but later on, you will start really loving it because it's very easy for us to automate the cases. Those things I will explain in the later stages. So there are some startup companies, they actually develop GUIs for OpenFOAM that actually they make. These are not free softwares, like some of them are paid also. So they essentially they use OpenFOAM as their engine, and GUI is actually developed by them. So small companies, they are those who cannot afford commercial software, but they can pay some small amount. Then these companies are actually targeting those type of customers. So they generate GUI which is based on OpenFOAM. Some of them are like Simscape, Simworks, Simflow, Helix, Bluecape, etc. Okay. So that is a broad idea about CFD and CFD packages. So now let me go into the meshing part. So we know that those who are familiar with CFD already know when we talk about CFD, the first thing we should do is first we should make the geometry, right? So if the geometry is very complicated, we use some 3D modeling softwares like CATIA, SolidWorks, or Fusion 360, etc. Right? So this geometry is generated. From that geometry, what we need to do, we need to discretize the domain into small meshes. So we actually do mesh generation. Then once we generate the mesh, we'll prepare the case. We will see whether the flow is laminar. So that's what I was telling earlier. So assumptions are very, very important. So we will see whether the Reynolds number range is in the laminar range or turbulent range. And based on that, we'll select the models like laminar flow or turbulent flow, whether it is forced convection. If it is related to heat transfer, we will see whether it is a forced convection or natural convection. Based on that, we need to make settings accordingly. we need to identify the boundary conditions, etc., etc. So that is actually indicated with preparing the cases. Then we will be running the case, that is simulations are going on. After that, we will be using ParaView software for post-processing the result. So the first two parts, especially making the geometry, I won't be covering. The second part, I will be covering the second part, that is mesh generation. So what we essentially do in mesh generation, we divide these mesh into small pieces, small cells, right? So mesh convert geometry into computational cells. So this is a process in which, depending upon the architecture or depending upon the way, FDM or FPM or FPM, we have different types of elements, and algebraic equation, like partial differential equation, is converted to an algebraic equation through this process, right? And accuracy, why it is important? The accuracy, convergence, and computational cost depends heavily on the mesh quality. So as the number of cells increase, we have a number of unknowns increasing, the size of the matrix also increases. So essentially, the computational cost increases. So we need to wisely decide what type of mesh we should use, where all we should put refinement, etc. So common CFD issues caused by poor meshes are like divergence. If your mesh is not proper, it may lead to divergence or non-physical results and excessive simulation time. So in the upcoming slides, we will see what are the options available in OpenFOAM in terms of mesh generation. So one of the fundamental options available in OpenFOAM is block mesh. I hope earlier you might have did a tutorial called cavity. When you did cavity tutorial, the first command you typed is block mesh, right? Then you might have used IIFOAM if it is based on IIFOAM. Then you use paraFOAM for seeing the results. So block mesh is a fundamental meshing utility available in OpenFOAM for making mesh geometry as well as mesh for a simple geometry, simple cases. And snappy hex mesh is slightly complicated utility available in OpenFOAM. It is possible for us to actually make mesh in snappy hex mesh utility for very complicated mesh, let's say ship hull mesh, or if you want to make a mesh corresponding to external aerodynamics of a car or an aeroplane, that is possible. And very interesting thing about snappy hex mesh utility is we don't have a GUI. Everything is written in a text file. We need to identify, so it's like, as I said, slightly complicated compared to block mesh, but we have very good controls over making the mesh, making the refinement, inflation layers, etc., without a GUI. So those who are familiar with commercial CFD packages, in ANSYS itself, we have different meshing software like ICM CFD or Workbench, etc. They have very innovative, very interactive GUI available for making the geometry, making the mesh, etc. But in this case, we don't have any GUI. Rather, it's a set of text files, a simple text file, and each and every feature is actually enabled in that through some commands. And if you're comfortable with the third-party softwares like ANSYS or Insight or even other third-party softwares like HyperMesh, so it is possible for us to actually use the mesh generated in that particular software and run the simulation in OpenFOAM. For example, let's say you are trying to learn OpenFOAM, you are very comfortable with ANSYS. So to begin with, you don't need to actually make mesh in the OpenFOAM environment. Rather, you make the mesh geometry and mesh in ANSYS itself. Just convert that mesh into OpenFOAM readable format and only make the case files according to your requirement, right? So when I started learning OpenFOAM 10 year or 11 year, 12 year back, I was comfortable with ANSYS fluent. So I started using the mesh generated in ICM CFD. Then I started using same mesh in OpenFOAM. Then I learned the solver part as well as how to set up a case, etc. Then I started learning block mesh and other like snappy hex mesh utilities available in OpenFOAM. So we will start with the basic fundamental idea behind block mesh. I think after my session, you will be having a hands-on session on this block mesh and snappy hex mesh. So this will give a background of what is block mesh and snappy hex mesh, and that will help you to understand the hands-on session also. So block mesh utility, as I said, it's a utility by default. It is available in OpenFOAM. So as I said earlier, it's a simple text file. So whatever details you want to convey, whatever geometry you want to make, whatever mesh, you want to make everything is actually conveyed in a simple text file, which is indicated as block mesh dict file in system folder. So mesh file will be generated by when you type block mesh in the terminal command. So it will actually identify whether the system folder is having a directory called block mesh dict or not. If it is not there, they will say block mesh dict is not found or it's missing. And if it is there, it will go through the file and it will read the file, and based on the informations available in the block mesh dict file, we will be generating the geometry, they will be generating the mesh, etc. So basic idea is we decompose the domain into one or more hexagonal blocks, and it can be a simple rectangular block, or it can, we can have edges with lines, arcs, splines, etc. So we know that when we make a geometry, we should start with the points. So let's say we want to make a geometry, a rectangular box. What all things we need? We just need the coordinates of these vertices or points, right? So we will start with that. Then, so we will have one point here also. Then what we need to actually we need to inform them. Okay, we should connect these points in this way, right? So we are connecting these points. Right? So we have a framework or wireframe kind of structure. Now we need to make surfaces by connecting these these lines. Then we need to make a solid body, and also one more important thing, especially when we do FE or CFD, we need to identify these boundaries with some names, because boundary conditions are very important. So let's say for this as top wall or bottom wall or side walls, etc., etc. So these are the steps of operations or the sequence of operations which are required for making a geometry in block mesh. So I will start with the block mesh. So a typical block mesh file looks like this. So for example, I just opened a cavity tutorial block mesh file here. I think there is a small issue. I will show in the slide itself. Sorry. So system folder, as I said earlier, system folder contains a block mesh dict file in which we will have following information. So we will start with, first we will have some header files which indicate the version of the OpenFOAM, etc. Then we have something called convert to meters, because that actually indicate the scaling factor. If we are mentioning the coordinates in centimeters, we should keep according scaling factor here. Then we will start with the vertices. So as I said earlier, we will start with the origin. Let's say if you are trying to make a rectangular block, we'll start with origin. So here in this case, this particular block mesh dict file is actually taken from cavity tutorial. So we are in that particular tutorial, we are actually making a rectangular block with 1 unit length in x direction, 1 unit length in y direction, and 0.1 unit in the z direction. So accordingly, we will identify the coordinates. We will start with origin 0, 0, 0, which is indicated here, that is 0, 0, 0. Then here it is going to be 1, 0, 0. Then this is going to be 1, 1, 0. And then this is going to be 0, 1, 0. Right? Then next points like z direction 0.1 unit. So 0, 0, 0.1. Then 1, 0, 0.1. Then 1, 1.1. And then 0, 1.1. So now what we are going to do is we are going to give some numbers for these points, because that is required when we connect these points with a line, right? So we'll start with a number like 0. So this is 0th point, then 1, 2, etc., etc. So this particular point is actually indicated. This particular point is indicated with the number 0, then 1, point 1, 0.2, 0.3, 0.4, 0.5, and 0.6, 0.7, right? So we generated the geometry by using or by specifying the coordinates of these vertices, right? So now we are going to say we are going to connect these points 0 to 7 by using a command hex 0, 1, 2, 3, 4, 5, 6, 7. Essentially, we are making a hexagonal block by connecting all these points. And here you can see the number of cells in the x direction. So this is X direction, Y direction, and Z direction. So X direction, we have 20 number of cells. Y direction, we have 20 number of cells. Z direction, we have only 1. And if you are, then here we have another term called symbol grading, which indicates whether we need a uniform mesh or non-uniform mesh, etc. So right now, if it is a uniform mesh, then we will simply write 1, 1, 1. If you are non-uniform mesh, accordingly, we need to make changes here. So you will understand all those things when you have actually a hands-on session. So we just generated the geometry and mesh. So next task, as I said, is we need to name these boundaries, right? So for a cavity tutorials, we have actually top one is moving wall. So this particular is moving wall, and we have fixed walls like this wall, and this wall are fixed walls, and front and back is actually indicated here. So that is actually done with the help of these commands like boundary, moving wall. Then we will be specifying something called type wall, what are the boundaries, whether it is a patch or wall, etc. Then followed by faces. In faces, we will say 3, 7, 6, 2. So moving wall, we know that it is connecting these coordinates like 3, 7, 6, 2. We follow some pattern which is known as face area vector from point numbers at the face. Basically, the vector towards the vector direction we should calculate, area vector direction we should identify the point. So 3, 7, 6, 2. And if you see the fixed walls, we have 0, 4, 7, 3. Then so 0, 4, 7, 3. Then 2, 6, 5, 1. So 2, 6, 5, 1, that is a right hand side wall. Then 1, 5, 4, 0. 1, 5, 4, 0, that is bottom wall. And the last one is known as front and back, in which we can say 0, 3, 2, 1. So 0, 3, 2, 1. So that is also done. Then 4, 5, 6, 7. 4, 5, 6, 7. So with the help of indicating these vertices, we will be able to identify these surfaces with certain names like moving wall, fixed walls, front and back walls, etc. Later, when we run the simulation, when we prepare the simulation case in 0 folder, we need to provide the boundary conditions according to this name. You should not make a typo mistake, or you should not keep a space between these words, etc., such a way that there will be an issue when we actually define the boundary conditions. So here you can see W is capital. Then when you define moving wall in 0 folder, it should be also capital. So case sensitive. So by this way, we will be able to generate a mesh for a simple rectangular block, which is very straightforward. So what happens if our geometry is having some slightly curvature in one of the edges? That is also possible in block mesh. So it is possible to make edges with arc or polyline or spline kind of lines with the help of block mesh utility available in OpenFOAM. So what happens when we have a circular box or circular disc, and if you want to mesh a circular body or let's say circular disc? So in that scenario, a single block may not work, because we can say that here in these areas we have like skewed cells, which may lead to some error in the simulations, right? So in that scenario, what we do is we will still use block mesh, but we will use some different strategy. Instead of using a single block, we use multiple blocks. So in this, we use multiple blocks, in which we can say here we have a block, here we have another block, here we have one block, and here we have one block, which is known as O grid. So these kind of multiple blocks you can see. So 1, 2, 3, 4, and 5 different blocks are there. So in block, these blocks are defined separately, and we will be meshing it accordingly. So that is also possible. You can see for a circular domain or circular disk, we can say O grid method can be used. For a let's say semicircle, we can use a C grid, or like 1/4 of a circle, you can use L grid, etc. So this particular case is an example available in OpenFOAM, which is known as plate hole tutorial. So they made a rectangular block in which we have a small hole in this particular corner. So they use 1, 2, 3, 4, 5 different blocks to actually generate mesh corresponding to this particular geometry. So for slightly complicated geometries, so even with slightly complicated geometries, it is possible for us to generate mesh by using block mesh utility. This is another one, let's say 3D pipe. So we have a circular pipe. So it is possible for us to actually make geometry, make mesh in block mesh itself. And we'll also show you some of the things we did, some of my students did. So making geometry, all these geometries are actually generated by block mesh, and meshing is also done by block mesh utility available in OpenFOAM. Okay, so one point, after some point of time, you will reach a point in which a block mesh is not sufficient for you to mesh. Let's say you have a complicated geometry, you are trying to mesh a heat exchanger, or you are trying to identify external aerodynamics of a car or ship hull dynamics, etc. So the geometry itself is very complicated. Even we cannot make geometries in normal OpenFOAM interface. We may need to rely on other third-party modeling software such as CATIA or SolidWorks or any other modeling softwares, right? So in that scenario, we will use a particular utility which is known as Snappy Hex Mesh. So complicated geometries, it is still possible for us to do mesh in OpenFOAM without a GUI by using Snappy Hex Mesh utility available. So very basic idea about Snappy Hex Mesh is actually discussed here. So OpenFOAM's primary tool for generating body fitted meshes from CAD geometries. So you can make the geometry, let's say you can make the geometry in a 3D modeling software, let's say CAD softwares, Fusion or SolidWorks, CATIA, etc. And we can use that particular geometry and we can mesh it in OpenFOAM using Snappy Hex Mesh. Only thing is you should be able to get the CAD geometry in STL format or OBJ format, which start with a simple background hexagonal mesh and automatically conforms it to complex surface. So that I will explain in the next slide, and which is widely used even in industry also. I know some companies in and around Kochi and other places, they are actually using Snappy Hex Mesh for doing even commercial projects, like for industrial projects. So from automotive sector, aerospace, HVAC, marine, industrial, CFD applications, etc. So basic idea behind complicated this Snappy Hex Mesh will be explained in this slide. So let's say I wanted to do an external aerodynamic analysis of a car. So we know that the geometry of a car is very complicated. It's not a circular shape or a non-geometry. It is slightly complicated, highly complicated, right? So what we need is we need to have the STL file of that particular geometry, let's say car. Then we are worried about the external aerodynamics, right? So we should have a proper bounding box. So bounding box is actually required and object is also required, right? So now what we do is we'll start with the block mesh. So we will actually consider this bounding block and we use a simple block mesh dig file to divide this into equal number of cells in X and Y and Z directions. So that is known as background mesh. And now what we will do, we will overlap this particular STL surface over it, right? So block mesh based background mesh is generated first. Then we will identify the sharp corners available in this particular geometry. Let's say this part or other parts, etc. So that sharp corners, near the sharp corner, what we do, we split those cells into smaller and smaller pieces first. Then we will do cell splitting by surfaces. Then remaining interfaces like these flat surface, all these flat surfaces, we know that the background mesh is actually overlapping with these flat surfaces, right? Or flat surfaces. Those cells also we divide it into 2 times, 3 times, or 5 times, etc., etc. Now what we do, if you are not worried about internal cells, we will just remove these cells which is available within the geometry. So that is known as cell removal. So these small cells, we divided these boundary cells into smaller and smaller. Then we are removing the small cells which is present within the geometry. So, but one problem we have here is, you can see a staircase kind of structures are available because we have a rectangular domain here. So we need to avoid that, and we need to give refinement also near the surfaces in order to capture turbulent properties. So which is known as surface snapping and layer addition. So we will remove all these protrusions. So we map these points very near to the body or surface of that particular object, and body shape. You can see earlier case, this tire wheel, you can see stepped structure was there. When we do surface snapping, it is actually avoided. So we remove that, and we can see slightly smoother. And if you increase the number of cells in this area, we can still get a circular or semicircular shape here. So this is a basic idea behind snappy hex mesh. It may look very simple, but if you start going through the snappy hex mesh dict files, as I said earlier, block mesh command is actually executed with the help of block mesh dict file. Similarly, snappy hex mesh command is actually executed with the help of snappy hex mesh dict file. So the snappy hex mesh dict file contains huge information. So there are hundreds of options available, and it may be confusing as a beginner. So what I did in them as a part of FOSSEE activity is I was having a student. Her name is Sravani. Through her, we tried to document a very simple case. So starting with a complicated case is very, very difficult for a beginner to understand. So what we did is we actually used a simple geometry like Flopas cylinder, Flopas circular cylinder, Flopas rectangular cylinder, or Flopas some other semicircles, etc. We generated the geometry and mesh by using snappy hex mesh, and we documented it in and submitted it as a FOSSEE case study report. I will show you the report we generated as part of her internship. So this work is actually done by Sravani Kulkarni with the help of Ivan Fernandez from FOSSEE team. So we considered different geometries, and step-by-step procedure we try to document such a way that the beginner can actually understand how to make a geometry and how to make simple geometries in snappy hex mesh, how to mesh those things. So we have a rectangular domain, and we are going to impose this particular circular object within this. So then you will see it is overlapped, background mesh is there, then we subtracted, and we are doing then surface snapping, etc. Then refinement and surface snapping is also done. So step-by-step procedure is provided. Then we try to convey the different options available in this particular snappy hex mesh dict file, and we tried different geometries. We started with the circular geometry, then rectangular box, then semicircle, then slightly elongated like vertical and horizontal plates, etc. All those case files are available in our FOSSEE website. Unfortunately, I think site is down now, so it is available, and you will be able to also download those snappy hex mesh dict files and go through it. I'll show you some of the images. Or it is possible for us to give multiple refinements, so refinement zone 1, refinement box 1, box 2, etc. Refinement as per our requirement, and we will also see the mesh corresponding to other geometries. The detailed report, I think 30 plus pages are there. The main reason for considering this particular topic as our internship is we didn't find, it's still a lot of materials are available for a beginner. We didn't find a simple geometry and simple geometry and snappy hex mesh dict files available on the internet. So we thought, why don't we document it such a way that this will be useful for others, so as a beginner. And there are certain cases in which we may need the internal mesh also. For example, if you think about a heat transfer case, let's say I have a cylindrical body in which cylindrical body contains some sort of heater. So we know the heat input to the system, and we are interested to find the temperature distribution outside the cylinder. So in that scenario, we need to model this as a conjugate heat transfer. That means within the cylinder, we need to do conduction, and outside convection we need to model. So in that scenario, as I said, we need the mesh inside the cylinder also. So we also explain what to do if you want mesh within the domain also. And we will see the diagrams like rectangular box, how meshing, then other geometries, semicircle, then square, that flat plate in the horizontal direction, vertical directions, etc. Actually, the internship time, allotted time for her was 3 months, and she almost took 6 to 7 months for completing, because it was a very detailed report. So I can share this particular document in the chat box. Okay, so that is second case, that is snappy hex mesh. That means if you have a complicated geometry, still we have a tool or utility available in OpenFOAM without GUI. With the help of this, we can actually generate mesh corresponding to those cases. Okay. And suppose if you're comfortable with other third-party software, there are some third-party software such as Salomi or Gmesh or CFmesh, in which some of them are even having a GUI. So if you are comfortable with that, you can even make geometry, you can make mesh in that particular software, and you can export this into OpenFOAM environment very easily. It is not just for open source software, it is for commercial software such as ANSYS or HyperMesh, etc. I just made a screen recording corresponding to that. Especially we have a mesh which is actually in the format of .msh. So a mesh is actually generated with the help of ANSYS software and converted that into .msh format. And we just need to type a command followed by the mesh file name such a way that we can actually convert that particular mesh to OpenFOAM readable format very easily. So we have wide software support, that means ANSYS to form is available. So you just need to type ANSYS to form followed by the file name such a way that we can convert the mesh file to OpenFOAM readable format. So if you are making mesh in which is required for ANSYS software, typically, especially Fluent software, it will be having an extension .msh, right? So in that scenario, Fluent mesh to form followed by file name. We just need to type in the terminal in such a way that we can convert the existing file, which is in the .msh format, to OpenFOAM readable format. Similarly, CFX to form, then other software like the DAT format, then Gambit, Gmesh, Ideas, all these formats are available. So I will just show you a demo screen recording or how to convert a mesh, which is actually available in OpenFOAM tutorial. So this is actually tutorial, elbow tutorial. You will find a .msh file. You just need to type Fluent mesh to form followed by elbow msh. So it automatically converted that mesh into OpenFOAM readable format. Then I am actually using a paraform for visualizing the result. So that's it. You can see the mesh which is actually generated in other third-party software. It's very easy for us to actually use that software, that mesh in OpenFOAM environment. So before I wind up, so what are the best practices and common mistakes generally we do when we do CFD analysis? First thing is, especially if you are into a new domain, if you're trying to explore a new domain, so you identify a proper experimental paper, you are trying to validate it. First thing is you start with a coarse mesh. So especially students who are not familiar with that, they will start with a very fine mesh, and finally it will take sometime week or 15 days or 1 month to complete the simulation. That will be very difficult for them to do, right? So refine only when needed, and we have a utility which is known as check mesh. If you are using a third-party software, or if you are using a block mesh, or if you are using a snappy hex mesh, once the mesh is generated and mesh is actually OpenFOAM readable format, you just need to type a check mesh command such a way that it will go through the mesh and it will identify whether there are some issues. They will go through the mesh quality parameters like skewness, aspect ratio, etc. Then based on that, they will suggest, okay, this mesh is okay or this mesh is not okay. Then if it is not okay, you need to open the mesh in paraform and see whether there are some issues with the mesh within the domain or not. And perform one of the important thing is mesh independent study or grid independent study is very, very essential. And if you are talking about boundary turbulent flows, we should have proper boundary layers, y plus values, etc. That is very, very important. On the other hand, if you see the common mistakes, as I said earlier, so sometimes we start with excessive cell count. It may end up with a huge computational cost associated with the simulations, and ignoring the mesh quality warnings. Sometimes we may get unphysical results, poor CAD cleanups. If the geometry, especially the assembled geometry, you're getting some sort of assembled geometry, etc. There may be some gaps between the joints, etc. If you are not doing proper cleanup, it may end up with some meshing issues. And some people don't do mesh sensitivity analysis. That is also not recommended. And before I wind up, so now we are living in the era of AI. So even AI can be used for meshing the geometry or meshing assistance, especially for OpenFOAM based thing. So what are the things we can actually do? Generating meshing directories. So I will tell you one example. One of my students was actually making a geometry. He is comfortable with OpenFOAM and block mesh. So he made a geometry something like this, and he generated the block mesh corresponding to this particular case. So let's say I have an inlet, I have an outlet here. So now he is interested to do what happens when we have outlet here. So what he did, he used a software called Claude, and he uploaded the geometry photo, something like this, and specified the coordinates, everything, and he just uploaded this blockmetric file also, then said, I want to keep the outlet somewhere over here with so and so details, generate the blockmetric file. So within few seconds he got, and he verified it, and it was working. So we can say once we have the basic thing, basic geometry, it's easy for us to do some sort of parametric study, so faster setup time and reduced syntax errors, etc. And if you talk about debugging, so faster troubleshooting, guidance of skewness, non-orthogonality, that is cell parameters, layer issues, etc. And for learning as well as training purpose, also it is very helpful. But one of the important thing about this is AI can be your only co-pilot. You should not make it as a pilot, right? So not the pilot, it accelerates the machine workflows, but engineering judgments must remain in human hands. That is a takeaway from this particular side. So with this, I would like to end up my session. So if you are a teacher, I think most of your teachers, for teaching OpenFOAM to my students, so what I personally feel is installing OpenFOAM in Ubuntu or WSL terminal may be really annoying. Also, those who are familiar with that, you may be knowing. So when I installed OpenFOAM in my PC in long back in 2014 or 15, I almost took 1 week to install it in a Ubuntu environment. So as a beginner, especially for a student, it will be really annoying and it will be demotivating also. So I use a particular version of OpenFOAM which is known as Blue CFD. When I teach CFD to my students, like master students or PhD students, so Blue CFD, it's actually Windows friendly OpenFOAM version. You can simply download a exe file. You can just install it in Windows 10 or 11. You don't need to separately install WSL, or you don't need to download repositories, etc. So I felt as a beginner level, you can, if you're trying to teach OpenFOAM, then Blue CFD will be a better option. Or if your students are comfortable with Ubuntu, then you can go ahead with the original version of Ubuntu or WSL version of OpenFOAM, etc. Okay, with this I would like to wind up my session. So any questions? There are some questions.
Sir?
Yes.
Sir, there are some questions from YouTube.
Okay, can
so Mr. Usman is asking which is the most suitable software for meshing, Gmesh or SnappyXmesh?
So that is up to them actually. The Gmesh and SnappyXmesh both are actually good. So depending upon I am not familiar with Gmesh actually. So I don't know the learning curve required for Gmesh. But Gmesh files can be actually used in OpenFOAM environment. Yeah, next question.
Sir, one question is there in the chat box. Is Blue CFD CLI based or GUI based?
No, it is CLI based only. Only thing is in Windows installation within 10 or 15 minutes you can complete. Especially Blue CFD I recommend only for teaching purpose. If you are trying to teach CFD through some hands-on session, so you can just tell students to go to that particular website and download and install it. Within 10 minutes they will do. So when you actually double click the exe file, it will automatically install relevant repositories, relevant files, everything which are required for running Ubuntu in a Windows system. But later stage, if you want to actually run simulations on parallel and all, there are some limitations. So by that time, actually students will learn how to install it. So it in a WSL or in an Ubuntu environment, and you will be able to run it in original Ubuntu version. That's what I saw. When I teach, I will start with Blue CFD, but later on they started feeling uncomfortable with the Blue CFD. Then they will try to explore how to install original OpenFOAM in WSL or in Ubuntu, etc. Then they themselves will actually drive. No, we don't need to. So I think Vednath Madhur sir is asking whether we need some code. No, all these codes are actually available in the OpenFOAM repositories. When you install OpenFOAM, automatically CheckMesh, BlockMesh, or SnappyXmesh or FluentMesh to form all those things is actually by default it is installed. You can directly call this command and you can do the operations. Yes, it is possible for us to use .msh file. That's what I showed in that video. So that particular mesh file was elbow.msh. So that particular msh file is actually converted to OpenFOAM readable format by simply typing a command.
Sir, can you address the question by Mr. Maruti?
One second. I think Ivan already replied.
Sure.
Yeah. I'll do one thing. I will share. I thought this may be useful because when we started learning Snappy Hexmesh, I felt it was very difficult to follow. So that's why we documented the Snappy Hexmesh, especially simple geometries like circular domain, etc. So Salome, do you try it for Mac use? Yes, one of my students actually explored Salome. So Salome files, I think you need to convert that to the NSIDE format or something. Then you can use NSIDE to OpenFOAM conversion command for using that in OpenFOAM. So I shared a link. In fact, I was supposed to share the FOSSEE link. FOSSEE website is down. So once it is there, you will also find the case files corresponding to each case. That means circular domain or rectangular domains, etc. Such a way that you can download it, you can go through it, you can actually reproduce by yourself. It's not just a report. Along with that, case files are also available. So adaptive mesh refinement, in fact, I didn't actually explore it. So this is actually beginner level workshop.
Sir, one question is there on YouTube.
Yes.
How about the accuracy compared to ANSYS machine?
Accuracy wise, I didn't have a proper one-to-one comparisons, but see, during my PhD or during my PhD, I compared OpenFOAM results with experiments. That is good. So I didn't have one-to-one comparison with ANSYS or any other commercial software, but it was a 5 to 10% error with experimental results. Ultimately, we need to compare with the physical results, right? So that was 5 to 10%. So in that particular case, that was sufficient.
Sir,
Yes.
one question is there.
Yes.
Thank you for your informative session, sir. In what way it is helpful for chemistry students for research?
Chemistry. In morning also someone I saw botany. So chemistry, chemical engineering, we have a lot of opportunities. To specifically talk about chemistry, we have some scalar transport form available in OpenFOAM in which chemical reactions can be modeled. So if anything is required by using finite volume based simulations, so in fact, one of the good thing about OpenFOAM is you can make your own solvers. If you know the governing equations, or you can add the governing equations, you can modify it as per your requirement. That is one good thing about open source software. In ANSYS nowadays, user-defined functions are available, but we have some sort of limitations because it's a black box. Yes, one interesting question. If somebody have ANSYS paid version, why should he use OpenFOAM? I hope that guy might be doing PhD or studying in IITs or NITs. But if you see the institutes in other than IITs and NITs, these institutes don't have money to purchase this license. So let's say you complete your PhD from IITs, okay. But once you go out of IITs and you are not getting any reputed institute for, let's say, in that scenario, you will be handicapped. You know everything, but you don't have license. You won't be able to publish paper. In a long run, it's better to invest time and like effort and time in open source software such a way that you won't be handicapped once you come out of that institute. Because those institutes, we know huge licenses are there. When I did PhD in IIT Madras, almost 235 or more, 250 plus licenses were there, ANSYS Fluent itself. So in my university right now, we have only few licenses, 4 or 5 or maybe 10 licenses. So similarly, each and every university may not be able to afford. Nowadays, most of the commercial softwares are coming with pay like yearly based rent rather than standalone license. So sometime this year you may have fund, but next year if you are not having fund, you will be in trouble.
Yeah, so may I know Samuyala Qureshi, you're from which country? Samuyala Qureshi. Okay, okay. So do you know the cost of purchasing the license for ANSYS Fluent? So once you are graduating from your university and you are looking forward to launch your own startup probably, then it will be a huge cost for you to buy the license of ANSYS Fluent. And also for every module, they'll charge another set of licensing fees. So to avoid everything, if you have free and open source software which can serve the same purpose, why will you not learn OpenFOAM?
I can
My
yes.
answer to your question.
Yes, I can also share one thing. There's a small startup company in Kochi in which they do consultancy work for big companies like L&T and other companies. So they got some project. L&T outsourced, L&T or some other company outsourced a particular project in which they need to do FEA and CFD analysis. So they are very comfortable with FEA. They have most of the softwares available in FEA, like ANSYS and other softwares, but they don't have a license for ANSYS Fluent. That means CFD part. But they will only give project to this particular company only if they do FEA and CFD together. So in that scenario, they actually approached us and we just tried to see the problem statement and we actually did. So in fact, they outsourced to us and we did it in open source software like OpenFOAM, and they were able to come submit the project on time. So as I said, these commercial softwares, especially if you're in an enterprise or if you're in a company or a startup, a huge amount of investment is required. Okay, any other questions?
Imran Ullah has a question. So Evan may be able to take it. Can I use Blender Pro Patient specific geometry for CFD?
Yes, so Imran, Blender is good for artistic things. Like if you have, say, someone asked about a hard geometry. So in that case, if you have something fairly complex, it's good for those things which don't require that much of a dimensioning aspect. Whereas if you're doing a proper engineering problem, like if you're creating a new, say, orifice or something like that, that you require precise calculations for those, or you require a precise dimension for those. So then for that you have many other softwares, like FreeCAD is there. That's one of the freer versions. You can also make certain geometries in ANSYS, and you can also go with I think it was AnyDesk has one for modeling things, so you can check those. But those two are again paid. The free version is FreeCAD, but those are again for complex geometries which require proper dimensioning. If you have a geometry that just varies in dimensions, then you can always use Blender because that's also free.
I think there are some GUIs, some small community, even FOSSEE team is developing a GUI for block mesh, right?
We have it for Snappy as well, sir.
Oh, Snappy Xmesh also, yes. I think it's in the trial phase, right? Or
yes, I mean, sir, we can execute simple geometries. It can generate Snappy Xmesh file as well using Blender.
Yeah.
The older version can generate SnappyHex and block mesh. The newer version that will be released, I think in I think this month, end of this month or end of next month. So that has capabilities of setting up your entire case now. So the GUI team is working on that. So there'll be a new release on that. So you'll be able to set up turbulence modeling, set up entire case directories, and also do mesh using CF mesh and Snappy and Blend and block mesh. So there are 3 options now. You're not restricted to just 2.
Yeah. Hybrid model, I'm not familiar. I did, so there is a question like, can I use hybrid model DES or DDES? So I use DNS, DES, I don't know. Paris, do you have any idea?
No, sir.
Okay. Boundary element method, also I don't have any idea. See, the thing is, nobody know full. We are all trying to learn this because it's a community-based development. So some of the features are available in specific version of OpenFOAM, not in the official version. Sometimes some GitHub repositories you will find from some university in Australia or some university in Canada. So we are still learning. Some inbuilt, yes, Blue CFD. Once you install Blue CFD, it will automatically install Paraview also.
Okay, so if we don't have any more questions, we can proceed for the hands-on session. Okay, one more question from Jinu Chandran. Is there any session for GUI block mesh? No, for this FDP, we are not offering any training session for GUI. We are still developing it, and we are training our FOSSEE fellows and interns on this development. And the information is there on the resources tab of cab.fossee.in, but unfortunately we are experiencing some glitch in the technical part of FOSSEE website. So maybe now within a couple of days we'll be able to access it. Okay, so that was all about the FOSSEE GUI. Okay, so maybe we can, yeah, okay, so Evan has replied to the BEM related question.
So there is,
From Jitendra.
yeah, it is possible. It is possible. I even have a document. One of my students actually did a specific case study on time-dependent boundary conditions. How to give it in OpenFOAM. I can share that link also. It is available in the repository. It is not. If you're not finding it, you can. I can share the link also.
Yes, so after this session, will be available on contact-cfd@fossee.in. If you have any questions for Professor Harikrishnan later on, also we can, we can get in touch with him and coordinate and get back to you with the answers. Okay, so should we conclude the lecture session for this right now and move on to the hands-on part?
Yes, sir. Yes, ma'am.
Okay. Thank you so much, Professor Harikrishnan. Thanks for your support and joining and being so patient with all the answers, all the questions that you have been answering. Okay.
Thank you very much. Thank you very much.
And we have also have received a lot of appreciation on the YouTube live. So I have taken the screenshot. I'll send it to you later on.
Okay. Thank you.
Yeah, very impressive lecture. Thank you so much, Dr. Harikrishnan. Thanks. Yeah. Bye.
Bye.
So we can proceed with the hands-on part, Paris. So over to you. Okay,
Yes,
Samuel Qureshi has one more question. Can we integrate any other software with OpenFOAM for course simulation? So after taking this question, we can move ahead.
Okay. Samyulaji, what do you mean exactly by CO simulation? Sure, you can. Do you have the permission?
Can you hear me?
Yes.
Actually, in my PhD, I have to simulate perform the co-simulation, in which detailed CFD simulation is done on the ANSYS, and other part is done in the Energy Plus software. So for the one state point, one iteration, it do simulation in the Energy Plus, then it gives the input to the CFD, take the output of the CFD back to the Energy Plus. So it
Okay,
gives the
so
post
like
simulation result.
you are asking for coupled simulation, right?
Yes, yes.
Yes, coupled simulation. So from CFD, you will be sending fluid flow, and from the other software, which parameter are you expecting? Is it structural
Uh,
deformation or?
it is performance of the HVAC systems, like
Okay,
chiller systems, or what
okay.
is the energy consumption of the chiller systems, fans,
Hmm. Hmm.
or terminal units.
Hmm, 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 hmm. So, as far as FSI is concerned, na, sir, we can do that. I'm not sure about HVAC systems. So, what we
Hmm.
can do is using OpenFOAM, we can send fluid flows, and there are other open source softwares such as Calculix or Solids for Foam. So,
Hmm.
from OpenFOAM part, you are sending the fluid forces. They are being coupled with Calculix or Solids for Foam. They are also generating displacement and deformation, and they are being sent back again to OpenFOAM. And this contact is generated using a software called Precise. All the three softwares are open source, and you can check that
Okay.
out. Maybe there are other things available that you can do with Precise as well, but as far as my knowledge is concerned, I'm not sure about HVAC.
Okay. Okay. Thank you.
Thank you. Okay, so hopefully we can start. I would like to thank Professor Hari Krishnan sir for his detailed explanation about block mesh and snappy X mesh. So now we are going to do the hands-on part. Firstly, we are going to do hands-on on block mesh, and then I will demonstrate you one case study on snappy X mesh. Okay. So firstly, let me share my screen. Ivan sir has posted a link for blockmesh case files as well as snappyx case files. Uh, Hopefully my screen is visible. Okay, okay. So this is the same link, whereas we have shared the sessions in the morning. So you can go in under day one and blockmesh and snappyx mesh. So there will be two folders. One is for blockmesh and another one is for snappy. So you can open blockmesh. So there is the presentation for blockmesh as well as the cavity folder that we have copied in the morning part only. This is nothing, we have made no changes here. Okay. And apart from this, in the snappy hex mesh folder, we have added the demonstration part for snappyx mesh. And as Professor Hari Krishnan sir has said, he has worked on a detailed work on detailed case study on snappyx mesh for generating high quality meshes using different geometries. So the total case study has been uploaded here. You will find the report, the case files, and different geometry as well. So everything can be accessed through this link, as well as we have the presentation for Snappy Xmesh session as well. So you can access all three documents from Snappy Xmesh and two documents from BlockMesh. Okay. So hopefully we can start with the BlockMesh session then. Okay. Okay. So again, welcome everyone to this FDP hands-on session on structured meshing using block mesh. My name is Paris Palkar. I'm working as a research assistant at the FOSSEE CFD team IIT Bombay. Uh, I'll just briefly introduce you to our team. Dr. Prabhu sir, he is working as he's leading the FOSSEE project. Dr. Chandan sir, he is the PI of the FOSSEE CFD project. and Payal ma'am, she is working as the senior project manager in our CFD, FOSSEE CFD project. So getting to the basics first, what is block mesh? So block mesh is a mesh generation utility provided by OpenFOAM itself. So people were asking that do we have to install some other utilities while using this using block mesh or snappy x mesh? So the answer is no. Block mesh is inbuilt installed while you install OpenFOAM. So block mesh or let's say other utilities as well, snappy xmesh, toposet. So majority of the utilities are on their own installed. If you have to make some changes, you have to make some tweaks in it. What does block mesh do is it creates a structural hexahedral mesh with an aspect ratio near 1. Okay, why aspect ratio near 1? So this will be helpful for us in the snappy xmesh lecture. Okay, where is it located? So the block mesh, it is located again in the constant folder. I have told you multiple times the structure of OpenFOAM is as zeroth folder, constant folder, and the system folder, and every utility that we execute on the terminal is located inside a folder called system. Okay, so again block mesh will be defined here only. And once this utility is executed, your mesh information, okay, these two are different things. One is you're creating your body using block mesh, and the mesh information, so whatever mesh you have created, it is being stored inside constant folder in polymesh folder. Okay, so whatever be, let it be vertices, blocks, boundaries, points, edges, etc., etc. If you are working with overset cases, so you will be also involving cell zones, or if you are working with, let us say, porous boundaries, so it will be also involving cell zones. So everything is written inside polymesh, and it is not going to change throughout the simulation. So your information related to mesh is stored inside constant polymesh. And what we generally do is, the general workflow is, for complicated geometry, we club it using snappy x mesh. So first thing is we have to generate a background mesh, and then club it using snappy x mesh for generating some complicated geometries. I'll show you the example. And block mesh as in whole in general individually is used for generating some simple geometries. We do not go for very complicated geometries, as it gets very complicated, as well as with the onset of OpenFOAM automation. Now we can very easily automate block mesh for our convenience. So we are going to start from the theory part first. We have to understand how do we do naming. We are going to the theory part first, and then we'll move with the implementation part. So if you have a pen and paper, yeah, you can keep it with you. Just note down the things that I am telling you. Also, this PPT is going to be provided, so please do not worry about this. Okay. So the initial point that we define, let us say if you are taking a square or a cylinder or anything, we have to divide it into subdomains. So as Professor Hari showed, so if you want to create a pipe, you have to divide that domain into 6 parts. If you want to do a single block meshing, it's quite simpler. But if you are moving with multi-block meshing, it gets difficult as we add blocks. So for that, for an individual block, the initial point or the starting point, it is called as the zeroth point. Okay, it is considered at to be the origin, that is 0 comma 0 comma 0. It is at 0 on x, 0 on y, and 0 on z, and all the rest of all of the points are named accordingly. Again, as I told in the morning, that OpenFOAM is a finite volume based module, so we cannot generate 2D meshes directly. Firstly, we have to generate some 3D meshes, and then we have to convert them to 2D. Okay, and after this, after we have generated the points, we have to name every point inside the vertices section. I'll show you how the case structure of the block mesh dictionary looks like. And after defining the vertices, we have to name the blocks. Okay, so first thing is we are going to check the file format first. Okay, so does everyone has the case files open with them, the cavity case file? Let it be, version is not an issue. any version will do. OpenFOAM 9, 12, 25, 12, 24, 12. So version is not an issue, but is everyone having the cavity case with them? Okay. Okay. So let me take you here. Okay. Okay, sure. So again, see, like I haven't changed anything. I am using version 24.12 only. I personally feel more comfortable with 24.12. It is more up to your convenience as well as the need or the solver selections that you have. So previously, what used to happen is the Lagrangian part that I work in sometimes is better in the foundation version, like in OpenFOAM 9 or 10. So you have to switch it, but you can use one version, it's okay. So currently I am in the cavity folder. So I'm doing nothing, I'm just writing explorer.exe. So let me clear this first. Okay, so the case is cleared now. I have deleted everything that was there. uh, Let us see how does block mesh utility looks like. Okay. Should I zoom a little bit my screen? I'm just going through brief again. Then I'm going to switch to my PowerPoint. So what should I
Yes,
do?
sir, zoom little bit. It will be good for recording purpose.
Okay, okay. Hope sir it is visible now.
Yes,
Yes.
please.
So once you open any file in using OpenFOAM, let us say we have opened blockmesh dictionary. So here are some comments that we have to ignore, that the OpenFOAM version currently minus 2412. If you are using 9, so it will be shown as version 9 or something like that. And again, we have here field operation and manipulation, the full form of foam. And after that, we have the foam file. Again, what is the version? It's 2. And what is the format? It either can be binary format or an ASCII format. But here it is ASCII. And what is the class of this particular dictionary, particular file? It is a dictionary, meaning that we can execute things using this. Okay, so there are many dictionaries like toposec dictionary, surface feature extract dictionary, snappy hex mesh dictionary. So everything that we can execute using terminal comes under the dictionary. Okay, and what is the object in this dictionary? It is block mesh dict. Okay, so we generally call it as block mesh or block mesh dict. Starting from the first line, the first line is the scale. Okay, so if you want, you can add on comments as well on the on your snap on your block mesh file as well. This is written in C++. So if you just add two forward lines, forward slashes, so it will be taken as comment. Okay, so scale is the part where you define your geometry. Okay, so let us say if you are going to make a 10 meters geometry, or maybe you are not familiar with complicated dimensioning, so what you can do is uh, either you can keep it as 0.1, so it will eventually scale your geometry by 0.1. Let us say if you keep it as 10, then it will scale your geometry 10 times higher. Okay, and similarly if you have kept like this is the default setting for this particular case. So scale 0.1 is meaning that whatever points we are going to define here, eventually they will be scaled to 0.1. Okay, so scale defines geometry scaling. Okay, coming to the vertices section, so this is a very important part. uh, let me go to my PPT first, and then we will move ahead. Firstly, we are going to start with a single block meshing, meaning that we are not going to involve any multiple blocks. Only one block will be taken and it will be meshed accordingly. The length and breadth of this block, the dimensions are given here. It is 0.1 and 0.1 length and breadth. And theory, okay? So as I have said that you should always be starting from point number 0, that is at the origin. So it will come around at here. Let us say if you take a cube, so the initial point or the origin point will come here. So this will be 0 comma 0 comma 0. Then this will be point number 1, point number 2, and point number 3. Okay, this is the 3D view of the geometry. If we just project it 2D wise, so it will look like 0, 2, 3, and 4. Okay, same for the other nodes. So 0 was here, 1 was here, 2, 3. Now we are going with 4, 5, 6, and 7. So if you can see, we have 4, 5, 6, and 7. Again, this is a 3D view. And if you can see, once we are projecting it in 2D view, so this will be 4, 5, 6, and 7. Okay. So if you observe carefully, we are doing nothing. If you define one block, let us say 0, 1, 2, 3. If one area or one section is defined, we have to do nothing, but we have to just give a certain amount of thickness, and the subsequent points are being the projection of each other. So let us say you have defined 0 point with a certain thickness, it will also become your point number 4. If you have defined point number 1 with a certain thickness, it will also become your point number 5. If you have defined point number 2, then with a certain thickness, it is marked in yellow as well, and with a certain thickness it will be defined as, or it will be noted as point number 6. If you define point number 7, point number 3, the projection of point number 3 is on point number 7 with certain amount of thickness. Again, the projections have been given here. So 0's projection is on 4 with certain thickness, 1's projection is on 5 with certain thickness, 2's point number 2's projection is on point number 6 with certain thickness, and point number 3's projection is on point number 7 with certain thickness. Okay, so again, going back to the theory, if we consider the 0th point to be at 0 comma 0 comma 0, as our geometry is we want 0.1 in this section. So what we can do is, here if you can see, this will be point number 0, this will be point number 1, this will be point number 2, this will be point number 3, point number 4, but the name will be 3. And if you see, all these 4 points are similar, but with a certain thickness in the z direction, that is 0.1. We have defined it here. Okay, so this will be point number 4, this will be point number 5, this will be point number 6, and this will be point number 7. So these are numbers. There are total 8 points. Okay, I will write it here. Total points 8. So this is how we have defined the coordinates of the cuboid in the vertices section. Firstly, we told OpenFOAM that we want everything scaled down to 0.1, and then we have given the coordinates of the points that we are interested into. If you look closely, the initial 4 points, the first 4 points and the last 4 points are similar with certain amount of thickness, 0.1, 0.1, 0.1, 0.1. Okay, so this is the part. And now comes the very important part. So there are 2 practices that we can do. You can imagine the particular patch or particular body in front of you. If you see, this was the first block. Okay, I have taken this block as 1 and this block as 2. Okay, and I have kept them here only. So this is nothing but the 2D planar view of the initial blocks. Okay, so first point will be 0, 1, 2, 3, and the subsequent block will be 4, 5, 6, 7. Okay, so if we see it in 2D view, so what it will look like is 0, 1, 2, 3, 4, 5, 6, 7. So there are again two ways to name it. Okay, first thing is you always start from left bottom corner and go anti-clockwise, like against the motion of the clock. And another rule is the right hand thumb rule. Okay, so let us say, let me show you if I can. See, so uh, I hope you can see my background. So I have a book like this. Okay, and I have to now move in anti-clockwise manner. Okay, so my hand is pointing out at front, so I'll start from here. So this will be my point number 1. This is a book. I am imagining, so this is one way to define it. So I'll keep my hand like this, so my thumb is pointing outwards. So from where I'm starting to curl this, that will be my first point. So either you can name it like this, or what you can do is you can keep that particular thing in front of you. Let us say I'm keeping this particular thing in front of me, and I'll start from the left bottom part, and I'll go anti-clockwise. So let us say start from here. So it will be left for me, right for you guys, and I'll move anti-clockwise. Okay, so these are two ways in which you can define the blocks in block mesh. So this is the manner in which you can do it, and keep in mind, like I personally feel this way is very easy, rather than using the right hand thumb rule. But again, it comes to the preference and comfort of the user. Now coming to the section. So we have defined the scale, that we want to scale everything. So my point number 1, or in OpenFOAM also, I have to tell you one thing, that OpenFOAM, whatever standard value you give it now in OpenFOAM, it will consider it to be in meters. Okay, so it may have eventually happen that you have given here centimeters, you want to give it here in centimeters, but OpenFOAM will read it in meters only. So if I have given 0.1, so it will on its own understand that I want to scale it 0.1 times in meters, not in centimeters or millimeters. Okay, so keep that one thing in mind while preparing the geometry. Okay, then coming to the blocks section. So here, as I have said, the initial 4 parts were defined and the other 4 parts were also defined. So we have clubbed them, and in the initial part, the first part, we define the name or coordinates of the rectangular box. Okay, so till this part is done. After that, we are moving with another bracket. Okay, so this is something very useful. So this is nothing but your discretization of cells in each direction. Okay, so what I have done is I have discretized my x direction in for 20 times. My y direction is discretized, or it is being divided 20 times, and my z direction, as this is a 2D simulation, I'm just using one cell in the z direction for it. Okay, uh, so this is done, and simple grading. So let us say if you want some finer mesh around any region, so for that you can use simple grading. You can use positive simple grading, negative simple grading as well. There is multi-grading available as well, but we are not going into it. So if you have understood till here, what we have done is we have written the scale, to define the geometry. Then we have the vertices or the points, total 8 points. Okay, then we have defined the points. Then we have to name the hexahedral blocks in the blocks section. So first part is defining the blocks, so we have to just name point number 0, 1, 2, 3, 4, 5, 6, 7 in this way. And we have to discretize. So let us say I want to divide my x direction in 20 equal parts. So for this I am giving 20. I want my region to be divided into y direction to be divided into 20 equal parts. So I'll give it as 20, and subsequently for z as well. And again, simple grading is applied, 1 1 1. So we are not giving any grading for to refine the mesh. Okay, as of now there are no edges here. We are not doing anything related to curve geometries. If there was any C-shaped domain for an airfoil or maybe external aerodynamic case, so we have to include some information here as well. Okay, so this is the block. So let us understand carefully what are these block section. So the first part is the hexahedral block that we name it in the anti-clockwise manner. Okay, so this will be 0, 1, 2, 3, 4, 5, 6, 7. So I have done that here. Then this is the discretization I want in x, y, z, and x, y, and z respectively. So I want 20 in x, 40 in y, and 1 in z according to this PPT. Okay, and simple grading, as of now we have kept it 1. So it just helps to cluster up cells at a particular direction. So if you have given positive grading, so it will cluster up cell in the positive x direction. If you have given negative cell grading, so it will cluster up cells in negative z direction. Okay, and again, a value different from 1 will add grading to the edge, and it will also cluster more cells at the end. Okay, if you just keep it as 1 1 1, it will be forming a uniform mesh. Okay, so this is the part. This is grading in positive x-axis, so cells are quite clustered up here in this region. Okay, for positive simple grading in x-axis, and again for negative grading, so the cells are clustered more around the edges of negative x-axis. Okay, and now coming to defining patches. Okay, so we have defined the scale, vertices, blocks. We don't have edges as of now, and coming to the boundary. Okay, so what we can do is we can open this part and we can visualize it. I'm going to delete this both. Okay, so if you can see in an isometric view, so in this properties tab, if I just take out the fixed walls, 3 walls will come. Okay, it's not visible as of now. So the only 3 walls will come. Okay, this downward wall and the right bottom wall. Okay, and after that, likewise, front and back empty, this patch, empty patch, and the moving wall, it will be applied. As I have cleared this case, hence it is not showing anything. So let me do one thing. I'll just run block mesh, and then I'll create a foam.foam file. Okay, fine. So this is the foam.foam file. And now if I extract my fixed walls, so see, only the bottom 3 patches, as I have showed it in the morning's PPT as well. This patch, and this patch, only these patches are visible. Okay, then let us say we'll move to wall. So in wall, the bottom wall and upper wall and side walls are also included. Okay, let's check the empty patches. So empty patches is front and back, meaning that we are not solving anything in the z direction. Okay, if you can see the Z direction, so this is the front and back patches, and these will be similar. Front and back patches will be similar as they are empty. And if we select the moving wall patch, so the upper patch or the upper lid will be shown. See, okay. Now coming to the naming, so I want to do a naming of these blocks. So how do I do that? So what to do is key, let us say you are using an external aerodynamic case, let us say, and uh, you are using an external aerodynamic case and you want to define inlet or outlet. So again, as I have said, either you can start from anti-clockwise manner and define the patch here, or you can use the right hand thumb rule. So from wherever, now if I keep it exactly in the front, so it will start from 9, so the patch will be 9, 11, 10 and 8. Both nomenclature schemes are okay, they do not have any issues, but it is just a way of convenience. Okay, so let us see how the block mesh is defined here. So the first patch is moving wall. Okay, and the type is wall. If we are applying boundary conditions that are related to wall, then we set the patch name to be wall. You can give the name anything. You can give your name to this wall as well. It is up to the naming. So we have three parameters here, or three patches here, where we apply the boundary conditions. Okay, so this will be moving wall, fixed wall, and front and back. Okay, so the moving wall is again a wall type boundary condition. So the type of this moving wall will be wall. Okay, I could have given patch here as well, patch, or let us say you don't know anything. Okay, uh, which appropriate boundary condition I should apply. So in OpenFOAM, it is called a banana approach. So what you can do is you can add just a variable called banana. So majority of the variables are occupied in OpenFOAM, but this variable is not defined in OpenFOAM particularly. So for that, if you just write banana here and write block mesh again, so it will throw an error. The so like it will be termed as banana. Okay, the patch type will be termed as banana. So let me change it back to the wall. Now coming back to the faces again, that the moving wall, that is the top wall we have extracted. If you see from here, this is the point number 3, point number 2, point number 5, and I guess point number 6. So this is 3, 7, 6 and 2. Okay, 3, 3, 7, 6 and 2. So they have used right hand thumb rule here. Okay, keep your right hand here and check from where your hand starts getting curved. Okay, so likewise they have defined for fixed wall as well. Let me show that to you. Fixed walls, maybe you can take any patches. For example, let us say I want this patch, so you can keep your hand in front of it and you can start naming. So first thing first, you will define this patch only, then you will move with naming of this particular patch, and then you will move with naming of this patch. So likewise you have to define three patches. See, 1, 2 and 3. So three patches are defined here. Okay, if you are going to apply a particular boundary condition, so you can change the particular patch uh, type of patch to patch boundary condition. So you can change wall to patch as well here, but as we are not going in depth, so we can keep it as walls. And if we check 0, 4, 7, 3, so the first block is 0, 4, 7, 3. So they have gone using the and the right hand thumb rule. So this geometry is totally defined using right hand thumb rule only. Okay, so these are the moving wall, the fixed walls, and the front and back. Okay, so let us execute the block mesh command here. If you have done the naming correctly, you won't face any issues and you will be generating some patch names as well. So it has created three patch number 0, patch number 1, and patch number 2. Names of these patches are moving walls, fixed walls, and front and back. Okay. And if you want to visualize it, so to visualize, you have to turn on internal mesh. Okay. So this is our block. And currently I have discretized into 20 parts in X, 20 parts in Y, and one single cell in the Z direction. And if you want to check if I'm doing it in a correct order, so there is also a command of access, data access, where you can check the parameters, access grids. So we are going here, you can see I have defined my coordinates from 0 to 1, but as I have given scale of 0.1 here, hence it has taken everything, it has scaled down everything to 0.1. So if I scale 1, so if I multiply 1 with 0.1, so the answer is 0.1 only. Okay. So in this way we have taken this block. If you want to refine your block, let us say I will refine this in 40, I'll discretize this in 40 times in X. So what I'll do is I have set the discretization 40 times in X axis, and now I'm going to run clock mesh again, and I'll refresh it. So see, the refinement has increased in the X direction, but it has been kept constant or similar in the Y direction. If you want to make a uniform mesh, it is generally recommended to keep these three settings as similar. So let us say, let us give us 40, 40, 40 in X and Y. We'll check. So see, now our mesh is much refined. Okay. And let us say if you want grading in positive X, so I'm giving 0.1 of grading in positive X. Again, these three parameters denote X, Y, Z respectively. So I have given 0.1 grading. Okay, so it has done. Now check for the positive X axis, reload files. Now see, now we have positive grading in the positive x-axis, or we have grading in the positive x-axis. Likewise, if I just change the symbol of this particular, so I have taken now negative 0.1. So what it will happen is, now you may expect it to happen at here. See, so these are some of the changes that you can play with in block mesh, and you can try on your own. So and for next session we are going with the snappy hex mesh. So yeah, thank you. Also in this ppt only, if you are comfortable with the single block, there are multi-block assigned as well. So there is theory of this, so you can check it out, and there are some assignments as well for you. So everything is in this presentation. You can check it out, and in the meantime I can take some questions if there are any. I can see one sir is already answering many of the questions, but if you have any questions you can ask as well. Okay, thank you. I'm changing my visual settings, display settings, so just give me some time. Yes. um Asymmetric mesh, what do you mean? Okay, okay, one sir has responded. Yes, yes, Dr. Ankit. Uh, Mr. Samiullah, what, sir, in positive or negative? So, dimension wise, we are scaling it by 0.1 times. Okay. As of now, it may be grading minus 0.1. and 10. Depends, sir.
Sir, can you again show that how you make that x direction 40 times discretization that process again?
Sure.
Yes,
So, okay, let me change my display settings.
because I have done it in that visual code, but
Mm-hmm.
after that, what to do? What I
Okay.
have done. So that program file I have to save, and again I have to run block mesh or
Huh.
without saving.
Yes. So you have to save every time whenever you make changes in your file. Na?
Uh,
What is your name? Ganesh.
Ganesh.
Sir? Ganesh sir. So you have to save file every time you make changes. Okay.
If
So
not save means if I
huh.
have to give the alter the different name of that file or not.
Mhm.
If I give the
No,
different
no.
name,
You have to keep the name as it is. You don't have to change the name. You have to just use Control S. And in the blocks section, if you can see the third section, blocks, so there is part, there is discretization, 40 in X, 40 in Y, and 1 in Z. So you can keep it like this. So let us say if you want to do 50 cells in X, you want 50 cells in X and 40 cells in Y, you can give the number as it is, 50 in X, 40 in Y, and 1 in Z. Now I have made changes, but I haven't saved it. So in VS Code, there is a way through which you can auto save whatever changes you are doing. Okay. If you have not implemented, you will be seeing a white dot here. Okay. So once you have saved this particular file, then again you have to go on your terminal and just run blockmesh. Okay.
Rest, your screen is not visible. Please share the screen.
Okay.
sir, it is not happening. It is
Yes.
not
Yeah.
updating for me, sir.
Okay. Wait. Let me share my screen. I'll show it to you. Sorry. So if you see my screen,
Yes.
so in the blocks section, okay, in the blocks section, you have your first parameter as hex.
Yes.
Okay. And your second parameter is the discretization of cells that you want in X, Y, and Z respectively. Okay. So you can define number of cells that you want in X, Y, and Z. Let us say if you want 50 cells, now I have made changes. Let us do it 60 cells. So I have made changes 60 cells. I'll save it. Again, if you are using VS Code for the first time, in front of this block mesh dictionary, you will see a white dot that will indicate that you haven't saved this file as of now. Okay, so you have to save this file. There are some settings in VS Code. Using that, you can auto save whatever changes you are doing to your file, so you don't have to manually do it again and again. Okay. So I have changed it 60 in X, 40 in Y, and 1 in Z. I'll save it. It is auto saved for my case. I'll just run blockmesh and then I'll update my file. So I'll open paraview. I'll go in paraview. I'll do open foam.foam file. It is the same file only. So I'll just select this and reload file. Okay. So now I have 60 cells in X, 40 cells in Y, and single cell in Z. As I'm not solving anything in Z axis, so I have kept it as single cell. Okay. So the earlier session or the morning session that we did on lid driven cavity, it was a 2D simulation. Okay. You can change this part to 2D as well. So it was a 2D simulation, whereas your cells in the Z direction were not utilized.
Sir, I just want to see the discretization over a paraview. Can you show me where is the option? Can you tell me?
So see, in this upper ribbon, na, Mr. Ganeshji,
Yes.
so you can change it to surface, but if you want to visualize your mesh, there is a drop down menu. You have to select this and change that particular setting to surface with edges. Okay. So you have surface, you have to change with surface with edges. Okay. Once surface with edges is done, you can visualize your mesh. Are you able to see it?
Yes, but it is a 2020 combination.
Yes. So you can make changes there, save it, run blockmesh again, and check out. Okay, okay, Raj. So I'll explain this in the Snappy Hexmesh session. Uh, what is your error, Mr. Kalyan? Can you tell me?
Hello. We are getting error like that. It's showing that the permission is not showing.
Okay, permission. So for that, you have to maybe give the permission. You can try using the command chmod plus X.
Yeah, I
And
tried it, but
Mhm.
it's not.
Okay. I'm not quite sure then why it may be happening. Maybe can you just share your screenshot? So, Mr. Raj, I will demonstrate how you can use a .stl file and proceed with Snappy Xmesh. Majority of the questions have been answered by Manjil sir and Ivan sir.
Paris, can you do one thing?
Hmm?
So the grading part, no, can you try adding a negative sign to the
Yes,
grading? And yeah, so just
yes,
show them exactly if you add a negative
okay.
sign, what exactly happens.
Hmm.
Parisji, just a minute. I'm sharing you my
Yes.
screen. I'm
Okay.
facing one error.
Okay.
Actually, I'm sharing my screen actually.
I can see Mr. Kalyan's screen.
Sir, is my screen is visible?
Yes, yes.
Sir, my screen is visible.
Yes, yes, yes.
Sir, here you may see here I have
Hmm.
made here 40-40.
Hmm.
But in the discretization,
Hmm.
this is showing 2020.
So you have
And
to save this.
what you are saying, sir,
Sir, you have to save this file first. Okay.
where?
Once
Okay,
once done,
okay.
uh, once that is done, so you can use the same file. So what was the name of your .foam file?
It was a cavity.com.
So click on cavity.foam, right click it.
Okay.
No, no, not like this.
Uh-huh, uh-huh.
And reload files. Ask it to reload files.
Reload files.
So if you have saved the file and run blockmesh again on the terminal, uh, then this
Here is
should come.
here it is the okay.
Run. Okay, you have run it multiple times. Okay. Okay, so Ganesh sir, do one thing. Run blockmesh here in front of me. I will
Okay,
see.
here
Blockmesh. Hit enter. Okay, now do ls.
yes.
Uh, okay, so this is the mornings. Yeah, it's fine. Okay, it is cavity.foam. So from paraview, can you open cavity.foam?
Yeah, it is here.
No, can you open it again?
Parafoam. Okay.
Yes.
Parafoam.
Parafoam will not work for 2412, sir. So you have to manually open it.
Manually, I have to open it. Okay.
From paraview, like how you were doing previously.
Parafoam. Okay.
Hmm. Hmm. Open this.
Here, but mesh size is 40. Taking the no, it is
So
taking time.
yes, I mean it depends on your RAM as well, Ganesh sir. As you know, you might be running multiple things on your background. That might be also a reason it is taking some time. So can you just delete all these .foam files first? You can open it here only.
Here,
Right.
delete.
Delete. Yes.
Delete.
Hmm. Delete. And go in the upper section of file. Open. and cavity.foam 2412. Okay, press apply. Now, uh, now just visualize the surface with edges.
It's 20 by 20.
Okay, so this is ParaView 5.11. It is your native Linux installation, right?
Yes.
Can you open ParaView manually by searching in the chat box?
Shall I
In
close
the
this?
you can close this.
This paragraph.
Yes, yes.
I closed it.
Hmm.
Paragraph 6.1.
Yes.
Yeah, it is open.
Yes, it is open. Yes. Close this. Yes. Now go in file, open, and use the. Now you have to copy the location. So go in your run directory and copy the address as I have shown.
Means here. Cavity file.
No, no, not here, not here, not here. This is your tutorials case.
Okay.
We have to copy it from the run folder. So either do explorer.exe here.
Explorer.
Ex no, no, spelling of explorer is wrong.
No,
R-E-R,
Explorer.
X,
Ah.
R-E-R, E-X-E.
Explorer dot exe.
Space bar, dot, hit enter.
Okay.
Now from the upper section,
Zero.
not here, not here. From the upper address, can you see Ubuntu home? No, just double click this.
Okay.
Okay, it's not showing ParaView. Okay, close it and just and try copying the address above. Can you copy the address? Not here, sir.
Yeah.
Yes, from go to the right side of the cavity part. Go even right. More right, more right. A little bit right.
Okay.
Just do Control C here.
Control
C. Open your ParaView 6.1. Now go in File.
Multiple paragraphs are open. Here.
And in the name section, in downward, if you can see name,
Yes.
do Control V here and tell him to navigate. Open the cavity.foam. Okay, and press apply. Check surface with edges.
It's 20 by 20. Now in this program, I have to make 40. Now it is saving. Save.
So, sir, you are making changes in your download section. You are not making changes in your run directory. If you can see properly,
Okay. Okay. So
I can see you have to open the run directory and make changes there, so that you can visualize. I can see your location is in downloads.
How we can see? Okay. User in downloads. Okay. Got it, sir.
Because of that, it was not being shown. If you make changes in your run directory, it will be visible.
Got it, sir. Thank you.
Yes, thank you.
Can I share it?
Yes, Mr. Kalyan.
Yeah, this is the
Zone identifier, do ls here first. Okay, now do block mesh. Press enter. Okay, polymesh did not allow. Okay. So what you can do is type here TUT, type on the terminal TUT. This is for everyone who is having OpenFOAM 9 and OpenFOAM 12 or the foundation version. Okay. Press enter, sir. Now go type CD icofoam, press tab, press tab. Okay, so can yes, hit enter. Okay, do ls here. Now go in incompressible, CD incompressible, CD. Yes. Now go in CD icofoam. Icofoam. No, I small. Again, you can write here CD cavity only. CD cavity and cavity here again. So CD cavity. Now do explorer.exe. aria.exe space dot enter. Okay. Okay. So what you can do, Mr. Kalyan sir, you can go one step back, maybe in the cavity folder again, and directly copy this cavity case. So right click on this. Right click on this. And on your terminal, again go on your terminal. Just write RUL. N, run. Press enter. Now do explorer.exe again. Dot. Yes, press enter. Paste that file here. You can delete this file first. Delete this first and paste other one. Replace. Okay, so it is asking for permission every time. Skip it once. And now go in your terminal. Now go in your terminal. Terminal. Go in the do CD cavity. And do block mesh now. Press enter. Okay, so it is asking for a parent directory. I will check your error out and I will email you. Okay.
Okay.
So this should generally not happen. It is something related to permissions. So I have to check which permissions you have to allow in your system so that you can do it.
Okay, shall I wait for after 5:30?
Sorry?
Can I wait after 5:30 after the
Sure. I mean, yeah. Yes. Ma'am, and even sir, are we having a break for 5 minutes or should we start with Snappy Xmesh as well?
I think we can start because it will take a good 40 minutes. And I
Good
think after
time.
that, then we can take question answers in the end.
Sure. So just allow me 2 minutes. I'll be back.
Yeah. Until Paris comes back, I think everyone can take a 5-minute break.
Can you share the schedule for tomorrow?
So the schedule is shared in the email. So there in the email itself, the schedule is there. So within that, each day's schedule is there. There's one only sheet.
Okay, I'll get that. Thank you.
Yes. So until Paris comes back, how many people over here have used any other CAD software to create some geometries? Any CAD. So you can use FreeCAD, uh, ANSYS Fusion, ANSYS Fluent if you have, or even AnyDesk, Salom. Okay. And what about Blender? Has anyone used Blender before? SolidWorks. Okay, that is also good. CATIA is also good. Okay. Okay. So whenever you create the geometry, uh, at least when it's a precision object, so you require it for some engineering object. So for that, you must have used CATIA or SolidWorks, right? So in that, how many of you have at least if you're doing engineering objects, then you must have heard about FEA, FEM, FVM in this case. Now since we are using CFD and we're using OpenFOAM, so that's all FVM based, but FEM based, finite element method. So how many of you all have heard of that? Okay. Yes. Okay. Yeah. So whenever you create a geometry, it's always better to have a clean geometry. That someone had already asked about creating STL files in this case. So whenever you create an STL file, how can you create a proper closed STL? So now when you'll see when Paris will demonstrate about when you demonstrate snappy hex mesh, so in that you will see something known as STL. So when you create an object in SolidWorks, CATIA, or any other software that you have, you will export it out. So when you export it, you have multiple options. So there are the most widely used ones are .stl files, .obj files, and there are also additional ones like .drx and another one. So once he starts demonstrating, you'll see that you can use different types of these to generate your mesh in Snappy Hex for OpenFOAM. So yeah.
Yeah.
Okay, Paris.
Yes. Should I share my screen?
Yes, Paris. So I was just explaining about the STL part. So what all types are there, and many people over here have used CAD software. So I think that would be very good for the understanding.
Yes.
Yep.
Hopefully the screen is visible as well.
Yes.
Yes. Hello everyone. Again, good evening. So again, in the shared Google Drive, there is another folder called Snappy X Mesh. You can open it. There is my presentation. There is case study by Shravani, and there is this airfoil 2D SHM Snappy X Mesh zip file. Okay, this is a demonstration session so that you don't have to follow along everything, because it is quite complicated and it will take some time. So just bear with me, and you can just listen to me what I'm trying to do or what I'm executing. The team is here to help everyone on the chat box on YouTube as well. So if you have any doubts, you can post it on the comments. After my session, I'll be also there to help you out with your queries. So we can start then. Okay. So welcome everyone for the FTP demo session on Snappy X Mesh, meshing using Snappy X Mesh. Now I'll skip this part, majority of the part, as you know. And again, what is meshing? So it is a simpler process of dividing a continuous geometry into smaller collection of elements or simpler elements. So let us say there is a bicycle, and if you want to do an aerodynamic study of that bicycle, or what should be the optimum position for that bicycle so that he can achieve his maximum speed, so for that we can conduct external aerodynamic simulation, and these are some three positions he can sit on, and these are the CFD mesh that we have to generate for doing the external aerodynamics. Okay, so what is Snappy Hex Mesh? So Snappy Hex Mesh is again an OpenFOAM utility. It comes by default once you install OpenFOAM, available in both ESI as well as Foundation version. It is used to generate high quality mesh for complicated geometries. As we have seen in the previous session, block mesh was used for simpler geometries. Snappy Hex Mesh is used for a little complicated geometries. And by complicated geometries, I mean really complicated geometries we can do until and unless there's dynamic meshing or boundary layer formation. Snappy hex mesh gets you covered at all the level. Okay. This utility helps us to generate 3D meshes. That means that we need to create 3D mesh first, and then we have to convert it into 2D. If we are building it from scratch, if we have a geometry ready, so we can directly use 3D mesh, and using a utility called extrude mesh tick, we can directly extrude it. Okay. And it is an iterative process, meaning it takes some time. Maybe it will take around 50 to 60 seconds for simpler geometries, but depending upon your complexity, your meshing can even take 2 to 3 hours. My I have personally spent almost 2 hours for meshing only one single geometry, as mesh is the fundamental level of carrying out a good CFD simulation. And again, same for block mesh. The mesh generated using Snappy X Mesh can be seen or can be stored in the constant polymesh folder. Okay, so let us understand how Snappy Hex Mesh work. Okay, so first thing is we need an background mesh. So background mesh can come from either block mesh or any external measure that of your interest you want. From this we get the background mesh, and from the CAD model we get the geometry.stl file. I'll show you how you have to use it, how you can implement. I'll show everything. Okay, so you have your background mesh, you have your geometry, the STL file. Now what we are doing is we are clubbing background mesh with the STL file using Snappy Hex Mesh. And once this is merged, these two things are merged, we get OpenFOAM readable mesh. Okay. So first thing is the background mesh. It is generated by a block mesh or an external mesher. And you have your geometry. It is created by external CAD modeling software, or you can create using any other tool as well. You get background mesh, geometry STL, merge it using Snappy X Mesh, you get an OpenFOAM readable mesh. Okay. So the workflow or the process of Snappy X Mesh is divided into three parts. We'll understand what are those. The process starts with creation of a background mesh that we discussed in the previous slide. Generally, we use block mesh utility for that, and it generates pure hexahedral cells that define the overall domain. In this case, we are going to deal with an external aerodynamics geometry. Hence, we want a good amount of background mesh for our background, so that we can add refinement in our body. So our body in this case is an airfoil. Okay. Along with the creation of geometry such as airfoil or bluff body or complex structure, generally STL format, that is stereolithography format, is used for importing your cases to uh, the OpenFOAM readable environment. Once this is done, both the background mesh and the geometry that is you have created using CAD are processed through Snappy Hex Mesh. So don't think like I have created my geometry, now I'll mesh it using Snappy Hex Mesh only. You have to do block mesh, you have to create a background mesh around your geometries, you have to define the patches, and then you can move along. Okay. So there are three main parameters or criteria that are required for generating the background mesh. So for as if we are using block mesh, so uh, all the three criterias are almost fulfilled, so we don't have to worry. Until and unless we are going for an external CAD measure, we have to make sure that aspect ratio is almost around to 1, because we want pure hexahedral boxes, and there must be no cell edge intersection. Okay, so we have seen the discretization of cells, so we don't need any cell edge intersection in between them for the background mesh. Okay. So if you're using block mesh for the background mesh, it has got you covered. You don't have to worry about anything. So this is the block mesh theory from on a basic level. So it consists of 5 to 6 blocks. We have discussed about them right now only. And now coming to the Snappy Hex Mesh workflow. So the Snappy Hex Mesh workflow would look like castellated mesh control. Then we have snap controls, and then we have add layers. Okay. There is also a section of mesh quality controls, but it can be added as a new file as well. Okay, so this is one command. Okay, so like I can show you. If you just write tut, and if you want to see okay how tutorials are in this section, if you have any tutorials related to snappy hex mesh, so you can just write snappy hex mesh and hit a dot. So see, there are multiple tutorials that have been used using snappy hex mesh. It will show you the case as well. So in incompressible over simple form, this is an overset case. For aerofoil, they have used snappy hex mesh. For incompressible solver, pimple foam, RAS turbulence model, uh, they are using wing motion for wing motion uh, application. And likewise, there are multiple case studies in OpenFOAM or tutorials, you can say, that are using snappy hex mesh. Okay, so this is one command to help you search out for whatever thing you want. So there might be some issues. Let us say if you face any if you encounter any errors related to OpenFOAM, so what you can do is you can just write grep-r and you can paste your error in this inverted commas here. You can paste your error here, and along with this space bar and a dot, and hit enter. Okay, so now I wanted to search for snappy xmesh, so I just write snappy xmesh. If you want to check any overset case or any airfoil case or Lagrangian particle multi-phase, you can just do that and check it out. Okay, so this is up to you if you want to explore more. In both the OpenFOAM versions, it is available. The more you move towards the newer version, more case files you should be expecting. Okay, so this is the general workflow in Snappy Hex Mesh. So first part is your castellated mesh control, second part is your snap controls, and third part is your layer addition. So yeah, if you remember in the morning section, I showed you a heat transfer case study I did. So this was the body. I created it in a external CAD modeling software. And this was the background mesh that I generated using block mesh. And then out of that block mesh, Snappy X Mesh helped me out to create a refined mesh around my body. So this is the mesh of that room. So I have a heat, uh, lateral air vent, and through this circular section, I'm injecting air into my room. So this room is quite hot. Now I want to cool it. So for that study, I meshed my geometry using Snappy X Mesh. I created this geometry in CATIA, imported it as an STL in OpenFOAM, meshed it using Snappy, and with the help of a solver in OpenFOAM, density-driven flows, I completed the case study. So let us understand what is the general workflow. Okay, so first thing, as I've repeated multiple times, you have to create a background mesh. It is generally done by block mesh, and it should cover your entire domain. Here also you can see my entire body or the domain of interest, computational domain, it is submerged around my block mesh. Okay, so you have to make sure that it covers your entire domain. So this is the background mesh, and we have an airfoil around it. Okay, so it is covering the entire domain. Now refining the background mesh. Okay, so we have cell splitting in the area of interest near the airfoil. It is done using castellated mesh control that I have told is the first step of Snappy X Mesh. And the splitting is done according to the edges of the surface. So if there is a very curved surface, so there is a feature angle that you have to give, and according to that it gets cut out. And the geometry edges are also determined the surface features direct. Again, it is a dictionary available in the system folder in constant. I'll show you what is that.
Okay,
And
please 1 second. I'll just announce that the attendance link has been put in the chat
sure,
box.
sure.
So we can take a break for say 30 seconds or 60 seconds and then
Sure.
get back.
Yes,
The
yes,
same
yes.
link is also there in the YouTube. So our
Sure,
studio
sure.
team is putting the attendance sheet on YouTube as well. So please make sure that you mark yourselves present, because we will award the certificates based on the attendance only. So please make sure that you mark yourselves present. We'll be back in maybe 1 minute.
Okay. So, like, is everyone done? Can we start? Okay. Okay, then. Sure, sure. Uh, Sharing my screen then. Yes. Uh, it is visible, right?
Yes, Paris.
Yes. Thank you. So, we have seen key. Now we have to refine the background mesh. It is done using surface feature strict. Uh, Again, there is another dictionary called surface feature extract that is available in your system folder. I'll show it to you. And then how refinement works in snappy hex meshes. So let us say this is your base cell or your cell number 0, which has zero refinement. So if you apply a refinement of level 1, then your base cell will be divided into 4 parts. Okay. And if you apply refinement of level 2, then all these 4 parts will be again subdivided into 4 parts. And likewise, this refinement goes on. Keep in mind, a refined mesh does not always says that it will not take good time. Generally, when we add refinement, the meshing takes a good amount of time. Then removal of cells. So now, as we are merging two cells, background mesh and our um, STL, so we have to cut some cells in the background. So the unwanted regions are removed, and other cells are specified, or that they are stored using a location and mesh keyword. I would like to stress on this factor that this is the most important parameter in your whole snappy hex mesh dictionary, because if this the point in mesh is not defined properly, then you might be spending hours and hours finding out where the error is, and the error would be in location and mesh. Majority of the times I have worked with the people, and even myself as well. I make mistakes in this particular part only, so please keep in mind to set this point properly. Okay. And the location where cell value is greater than 50% in the volume are kept. And always, if we are doing an external aerodynamic case, so we have to specify a point here, so inside the computational domain. And let us say if we are doing an internal flow case, then we have to do it inside the pipe. Okay. And the fifth step is snap mesh to the surface. So the unwanted mesh was completely removed, and this is done using snap controls. And again, it helps us to adjust a good quality mesh. Now then we have add layers. So boundary layer theory is very important in our CFD. So if you are doing an external aerodynamic case, for that you will need an boundary layers. So you can do boundary layers very accurately using Snappy X Mesh. It works well for level 4 or 5. However, it fails if you start adding on more and more number of layers. Okay. uh, as this is saying ki smooth irregular cells are added along the boundary, and it is adjusted by add layer controls, which is the third parameter. So this is the overall geometry background that we are going to see. So this is the computational domain, and we have so before starting for very complicated geometries, we can go with some simple geometries like airfoil. So here we have a 2D airfoil. It is NACA 0012. I'll show it to you. So this is your background mesh using block mesh, and it is the airfoil. So we have generated the airfoil using your airfoil tools. And I mean, you can do that according to your convenience as well. Uh, Let me show you how it looks like. So let us say, so this would be the structure once you open. This would be the structure once you open your case file. Now I have a tool called Mesh Lab, so it is used to refine your mesh, and it will help you to reduce the issues related to boundary layer. But let us say if you are using FreeCAD, so you can open FreeCAD. Okay, and see, I have it open with me. So this is the part that I have imported. Okay, so you can visualize it using any CAD software. So this is the part that we are interested in. So what you have to do is while you are going to make, or you are going to mesh your geometry in the constant folder, make sure there is a folder called try surface. Okay, now we have made it, we have created it for everyone, but if it is not there, please make sure you make it. Okay, so now let me go to my environment. Now I'll switch it to OpenFOAM 9. So this case study, and I hope Shravani's case studies are all in OpenFOAM 9. Okay, so I am sourcing OpenFOAM 9. Now uh, I'll just go in airfoil 2D SHM. Yes, so yeah, I've created some extra things here as well. So wait, let me do foam clean tutorials. Okay, so it's cleaning the case as of now. Once it is done, I'll show you. Okay. Yeah. Rather than wasting time, I'll just directly show you what you have to do. So in your constant folder, you will be having a try surface folder. Please do not worry about the folder called polymesh and extend feature edge mesh. Those will be subsequently created. Okay. So in your try surface, what you have to do is go to your aerofoil.stl, copy this, copy it, go in constant folder, go and try surface and paste it. Okay, now I have it here, so I don't have to do it again, but paste it here. There will be no airfoil.emesh. Delete it. Okay, so you won't be having anything, just a try surface with your airfoil.stl added. Okay, once this is done, then your one part is done. Now you have to open your surface features dict. In OpenFOAM 24.12, it is surface feature extract. In OpenFOAM 9, it is surface feature dict. Okay, so what are the surfaces that we want to import? It is nothing but the airfoil. So you can name the geometry here. Okay, you have to name the geometry and the STL, and we have to include an angle. So as I have shown you here, that it is based on angle. The edges are cut based on an angle, so we have to define an angle here. And subset features, so we generally don't make any changes here initially. Once we are thorough with OpenFOAM environment and Snappy Xmesh, we make changes here. Okay, so surface features dict is completed. Now what we are going to do is we are just going to execute surface features. Okay, so surface features is executed without any error. Um, it has ended, and it has written everything. Also, please note down that it has written surface feature edge mesh to constant try surface airfoil.emesh. Okay, so if someone might be wondering ki, uh, how the emesh file came, so it came because of airfoil.emesh. Okay, just 1 minute, give me 1 minute. Yes, sorry. Yes, sorry. Sharing my screen now. So yeah, we have executed surface features command successfully. Now we have to do block mesh. So there are some changes in the block mesh. I'll show you what are the changes here. So we have done nothing, but we have changed the dimension of the geometry. The every concept, it is similar. We have made no changes in the concepts. The only change is the point and the coordinates of the background mesh that we have used. Also, if you can notably see, we have made changes in the cells that we have in uh, X and Y for having a better mesh. And as I'll be running more, I'll be heavy on RAM, so we are keeping it simple. And again, we have here named the patches. So there is inlet, outlet, top and bottom, front patch, and back patch. Okay, so this would be patch. You can define it empty afterwards. Okay, so this is done 50 21, and this is grading. It is giving, it is uh, multi grading we have applied. Okay, now we have to do block mesh here first. Okay, so block mesh is also successful. It has not thrown any error. So it is block mesh is also saying it has given for 5 patches: inlet, outlet, front, back, top, bottom. Okay, now comes the main and important file, Snappy Xmesh. Now if you see, it is almost around 182 lines. Okay, The SnappyX mesh is almost around 182 lines, but please do not worry. You have to just we have to go step by step. So as I've said, that these three features are there in SnappyX mesh: castellated mesh control, snap controls, and add layers. These three parameters are there only. Okay. So firstly, we have to define all geometry. Please do not worry, we have given comments for every command here. So if you go down, if I'm skipping any, or if I'm skipping any part, so please do not worry, we have given every comment for why we are using this particular value, so that you can check it out laterwards, as we have very less time now. Okay. So first thing first, we have to define the geometry. We have to define the name of the geometry that we are going to use. So it is airfoil. Please keep in mind for future use as well from SnappyX Mesh, it will be called as airfoil. So whatever you are naming it here, please make sure to name it properly. Okay. And what is the type? It is tri-surface mesh. So it is placed in the tri-surface folder. Okay. Tri-surface e-mesh. Okay. Hence we have generated a e-mesh. And which is the file? It is airfoil.stl. And there is also some extensions, that which sort of extensions are allowed. So you can use stl, stlb, obg, vtk, ftr, ac, ass, smesh, try, or dx. So these are the extensions that are allowed. Okay. Right now we have stl, and I preferably, or I personally use stl extensions only. Also, if I want to generate, like I can show you, if I want to generate a refinement box around my airfoil. Okay, so if you see, this is the airfoil, this is the total whole domain, but I'm not bothered about how mesh will be in this region, or let us say how mesh will be in the upper region. I'm more focused, or I'm more concerned about how mesh will look like in this region. So I have to apply appropriate layers. I have to choose suitable layers, as well as I have to refine mesh in this section. So for this, we are giving a refinement box. And here we are doing nothing but adding just a small box of mesh which will be refined. Okay. So we have added a refinement box. So again, it can be user specified. You can use it rectangularly, or you can use it in square, or it's up to you. And we have to give the minimum and maximum coordinates of the points. So let's say it's at +2 till +4. So my minimum coordinates in x will be 4, and let us say I want it from here, so it will be 2. So my initial will be -4 here, 2 here. And as we are not solving anything, so we'll take completely in z direction. Okay. So these are some changes here. So this is nothing but the domain of interest of region for which we want the refinement box. Then this is castellated mesh controls. So I mean, it is pretty much self-explanatory if you read the comments that we have given and which setting does what. So let us say maximum load cells. So this tells us key what is the maximum number of cells allowed per processor. This is again for parallel. We have given in brackets parallel for the commands that we are using for parallel processing. Okay. So this is pretty much self-explanatory. So I'm skipping these 4 commands. Then these are the features that we have. Let us say I want to mesh my airfoil. I want to add refinement to it. So I want a level 4 refinement. So if you remember, I have shown it here, that how refinement is added. So we are doing nothing but this in this particular region. And again, they are asking which surfaces do we want to add refinement. So we want to refine the airfoil surface. Okay. With the level of 6,6, 6 in +x, 6 in +y. Refinement level is minimum and maximum. Okay. And patch info, our airfoil is as well. No other type is allowed. And resolve angle is it controls the local curvature, or let us say if you are working with complicated edge refinements, like one airfoil is S1 223, so it gives an trailing edge error using SnappyX mesh. So for that, we have to be very specific with this resolve feature angle. Okay, and then refinement regions. So we have defined only one region in the upper section, that is the refinement box. So we have added the refinement for it. The mode is inside, and level 2 refinement. Location on location in mesh, it's very very important, very, you can write it somewhere as well, it's very important. So now we have given it 3.9 in 3.99 in positive x, 3.0.99 in y, and 0 in z direction, meaning that this point will fall in my background mesh, but it is not intersecting the airfoil. Okay, so once this is done, now we are going to snap controls. So it is the part where we snap the geometry to the mesh. So like how many smoothing iterations we want. So for this we have given 2, and here is the tolerance limit that we can set, and n solver iter, so number of mesh displacement for relaxation iteration. So you can test it out with these settings. Let us say if you are facing some errors with snappyx mesh now, so the snap controls is something, n solve iter or n relax iter or tolerance, you can increase or decrease it based on the error. Okay, so it's quite helpful, but you have to know what is for what. So if you open a snappyx mesh file typically, so there will be lot of comments, but they are not pretty, how do I tell, ki they are not very explanatory. So we have tried our best to sum up everything into this. Ivan sir has made this file, so we have tried to sum up every command that we are going to use and what does it stand for. Okay, so out of two parts are done. For now, let us keep it as false. uh, we can keep it as false to switch off. So currently I'm not adding any layers, just starting with snappy hex mesh. I can just write snappy hex mesh overwrite. Why overwrite? So I want to erase everything that was previously. So it might happen that if you are working on a project, you might have forgotten key if I have created a new mesh or not. So overwrite will erase every previous mesh and it will start over again. Okay, so it will take around 50 seconds for meshing, and then I'll show it to you. Again, see, it is checking for the point this in the region that are specified. One is the background mesh and the airfoil, and keeping all cells in region 0. So this is the point containing this, and it will remove the regions surrounding the airfoil. So it's quite fast, hence it has been done very quickly. You have to just wait for some time. Okay, so it shows us some stats that finished meshing without any errors, finished meshing in so and so time, and it has ended. Also, it gives a stat that does it has any non-orthogonality faces with degree. Like if your non-orthogonal angle is above 70 degrees, then we have to make some changes in your mesh. If it has any pyramid volume, then you have to make changes accordingly. Like, so in our case, we are satisfying almost everything. So it's a very decent mesh. I wouldn't say it's a very good mesh, but it's a very decent mesh for demonstration. So what we can do is, now I can visualize it to you. So I'll open ParaView. And I'll open this. It will take some time. Okay, so now initially if I just run block mesh, I won't see the airfoil here. If you can see the airfoil in this section, if I just run block mesh, I won't be seeing any airfoil in this region. Okay, I'll just reload the files. Okay, so now the airfoil is gone. Now we have to snap using snappy hex mesh. We have to snap that particular airfoil or merge that particular airfoil into this region. I'll show it to you. So airfoil is here. I'll reduce the opacity. So see, these are two different quantities as of now. Okay, the airfoil is a lot bigger than this, but using snappy hex mesh, what we are doing is we are merging these two. We are merging these geometries for our use. So again, snappy hex mesh override. It will take hardly around 50 seconds, and then we can see. In the meantime, what I'll do is I'll turn on the axis grid and do it to 2D. So if you see the location in mesh, it was 3.9 in positive x, 0.99 in positive y, and 0 in z. So if you see here, so 3.99 is something around here, just closer to 4. 0.99 in positive y, so it's almost around here, and in z region is like almost here. So we are not intersecting with the body, so it won't cause any issue. Okay, so this is the thing we have to keep in mind, or else we face a lot of issues. And now I'll just reload this file. I'll increase the opacity. I'll set it to 1 and surface with edges. I'll close this. Now if you see, the airfoil has been cut, and we have a horizontal refinement region around our airfoil, and it is pretty much good. However, there are some changes that we have to do. First thing is we have to just make it true. We want to add layers here. Okay, and we'll go down. There is a add layer control. So here layers are there, and for which patch do you want layers? So we want it for the airfoil patch. And how many layers do we want? So we want 2 layers, and these are the settings that are available on the internet as well. They have given it what they do, what are they used for, and mesh quality controls, everything is available. So you can run snappy hex mesh again. Now this time it will take some time, but maybe around 58 seconds or something, and then it will be done. Okay, and if you are still not sure about this part now, uh, the location in mesh, so what I suggest is you can go for a filter called point source. So there is a filter called point source in paraview. Okay, you have to hit enter, and you have to give the coordinates of that particular point. So let us say I'm using 3.99 in x, so 3.99 x, 0.99 in y, and 0 in z. Okay, so we have to make sure this. So if you can see, this part is like uh, in the region that, see, it is here, it is shown in plus. Okay, so just please make sure that you get the location in mesh correctly, or else again there are multiple errors are associated. It might happen that your geometry is not getting clipped. So one fundamental cause of this error is the location in mesh, hence I'm stressing out more on this. Now you can see a lot of my RAM has been consumed as I have multiple tabs open up. The meshing is done, took around 50 seconds. Let me try reloading this. Okay, it's not responding. Let us wait for some time. Okay. As I have zoomed out a lot, zoomed in a lot, hence we are crashing here. Just wait, or I'll just close paraview from bottom. Okay, let us see. So give me just 2 minutes, man. Review is not working. Actually, I have consumed a lot of RAM. Hence, meanwhile, if you have any questions, you can ask here. I'll try to answer as much as possible.
Hello, sir.
Yes, yes, Mr. Ganesh, sir.
Sir, I can't locate that Aerofoil file in my OpenFOAM dictionary. Can you help me in this regard?
So, Ganesh, sir, we have shared an airfoil 2D SHM here. Okay.
For
So
SSD?
if you
I
on
have
the
downloaded it. I have
huh,
downloaded it, but how
huh.
I can bring this into the OpenFOAM
So
environment?
you have to paste that file to your this paste this into your control dictionary.
Can you show me once?
Yes, yes,
Help me in this. I'm sharing
yes,
my screen.
yes. No, no, no. Don't share your screen. I'll share my screen and I'll tell you. See, you have to be in your run directory first. Then you will be having airfoil 2D SHM. Okay. Then you will be having airfoil.stl here. So you have to copy this.
The screen is not visible.
Is my screen not visible?
Yeah, it is not visible.
Mm,
Paris, it's visible.
yes, I mean, maybe Ganesh sir, there is an issue with the internet from your end.
It is visible.
Okay, thank you, Matthew. So, like, what you have to do is you have to copy this particular file. You have to go
Just
here.
give me, sir, a minute. I'll just give me a minute.
Sure, sure. In the meantime, I'll take uh,
Yes, yes. You may
another
take me.
question. You can, if there are any other questions, you can ask. Um, Let me reduce my screen. Okay, yeah, that's better. Yes. Mm. So see here. So first thing is, key we have first thing is we have created a background mesh. Second thing is we have created a region of refinement around this body. Also, the third thing is we have also tried to add layers here. If you are able to see, there is a transition here. So we have added layers in between here as well. As of now, we have tested it. It the layer addition works fine till layer number 5 or layer number 6, but once you go beyond this, it starts failing. The layers are not added properly, and this is a very symmetrical airfoil, so it does not give you any issues related to trailing edge meshing. But if you are using some different airfoils like I used for S1223, so it gave me a very hard time resolving the trailing edge mesh error. Okay, so this is one thing you have to uh, keep in mind. Yes, and please ask questions if
Sir, now you can
uh,
share me.
yes, yes. So I am still sharing my screen. Okay.
Okay. Now
Is it visible?
I have downloaded that
Mm-hmm.
folder. Now,
So so you have an aerofoil.stl here. Okay.
yes, yes.
So you have to copy this.
Okay.
You have to copy this.
Mhm.
Go in your constant folder
Oh,
and paste it here.
1 minute. Uh,
Okay. Done.
okay. I have pasted
Hmm.
in the constant folder. Okay.
Hmm.
Done.
After this, you have to run surface features on your terminal. So you have to run let me show you. Surface features. You have to run it in your terminal.
Command not found, it is saying.
So it will be surface feature extract for 2412.
Uh, uh, can you give me that name in comment box so I can paste it
Yes,
over?
yes, 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 yes. Surface feature extract. Yes. Mr. Jenu, I mean,
Fatal error. It is fatal error.
yes, yes, fatal form error. As this case study is particularly for OpenFOAM 9, we have to port it for OpenFOAM 2412 as well. So you can try running it in OpenFOAM 9 if you have it. Or if you don't have any case studies, no. So what I'll do is I have a flow over a cylinder case file. I'll upload that in the Google Drive. It works for 2412. So you
Yeah,
can
sure,
download
sure.
either of one. And if you check the PPT now, uh, Mr. Ganesh sir, so there is list of commands that is given. Okay. So if you want to run it using serial, then which command you have to use. If you want to run it using parallel, which command you have to use. Okay.
Okay.
So you can try it on using your end. So this is for the parallel part. I'm not going to explain parallel today as it will be way too much, and it is given here okay, which commands we have to run. Okay.
Okay.
So irrespective of the case, I'll just upload the case into this drive flow over cylinder. Maybe you can have that and
Sir, and also, yes.
yes.
Yesterday we were facing that OpenFOAM 9 installation issue.
Yes. I have it in mind. Yes, I have your issue, Mr. Ganesh sir. Please allow us some time.
Yeah.
I'll get back with the response. Also, Mr. Gino, actually the thing is, uh, I am exploring MeshLab currently for my dynamic meshing simulation. So and this will be a bit advanced for this, so I won't be explaining it here.
MeshLab is a pure paid software.
No, it's free software, sir. Majority of the software that I use are mostly free. For CAD modeling, I use FreeCAD. It is free and open source. For meshing, I either use CF Mesh, SnappyX Mesh. Both of them are, I mean, both of them does their part. So both are free.
So in
You
the
don't have to.
in the MeshLab you are doing meshing and then it is
Hmm.
importing it to OpenFOAM.
Yes. So yes, I'm exporting .msh and making changes there.
Okay, okay. So I have to do the complete meshing in MeshLab. Then I
No,
have to
no, no,
import.
sir. No, sir. No, sir. No, sir. MeshLab I have installed for my dynamic mesh simulation. It is nothing to do with today's session. As I have installed it, so by default my MeshLab was opening.
Okay.
Yes. Mr. Belcom, you have raised your hand. Do you have any questions?
Yes, I have a question. The
Yes.
location in mesh, you can
Mm-hmm.
you can present it in paraview
Hmm.
compared with the
Yes.
aerofoil PNSTL to
Yes.
see it, and
Huh.
uh, and I have another question. If you can do for 3D
What
3D
3D geometry you're saying?
yeah yeah
So
if you
meshing
can
of a
yes
3D geometry, if you are asking.
yes yeah.
Okay. Yes. So first thing is, uh,
Thank
I'll
you.
yes, I'll share my screen. So, for location in mesh now, what you can do is you will change this part to surface first. Okay. Initially, you won't be seeing this airfoil, so you have to consider the background mesh only and reduce the opacity to let us say 0.25. Okay. Now this opacity is very low, so you can see the point where it is. So here you have to go in filters and go for search, and search for point source. Okay, and hit enter. And here by default the point is in this location, but let us say 3.99 is one point, 0.99 is another point. So see, Mr. Belkan, if you are able to see it, the point is here. It is in the body, it is in the domain, but it is not intersecting with the airfoil.
This is
So you can plot this like this. And yes, for 3D meshing, just allow me 1 minute. Let me open my test cases. I'll show you how you can do that.
Paris, in the airfoil case only, there is a 3D to 2D mesh converter. So,
Acha, so
yeah.
so they are asking to convert it from 2D to 3D.
No, I think Mr. Belakim's thing is that he wants to, I think, do a 3D mesh. But see, when you're working with
yes, yes.
when you're working with Snappy, by default it creates 3D meshes only. So the airfoil also. So Paris, can you just zoom in closer to the airfoil to show that it's actually a 3D mesh? You have, and if you're running a 2D simulation, you'll have to convert that 3D mesh to a 2D mesh. So that is one thing that you have to keep in mind. So that's why whenever you're doing snappy hex, I think Paris missed that out. He said when you create your block mesh, if you notice that in the cavity case for front and back we had kept it as empty because we were solving for a 2D case. But with snappy hex you cannot leave it empty. You name the front and back as a wall or a patch, and later on you convert that patch into an empty face. So that is why you have an additional file called extrude mesh. Yes, you have the extrude mesh dict. So that is where you will convert your front and back to a 2D case, or if you're going to convert it to empty in this case.
I have some points. Exactly, I want to see how to write snappy hex mesh and do a good mesh in 3D, not to transfer 2D to 3D. My name is Belkacem.
Yes, yes, yes.
Thank you.
Yes. So let us say this is a test case. So I was working on the machine. So what you can do is you can update the this, what you can say is you can update your block mesh dictionary. So there are some ways to update it. You can update your block mesh, and with the help of automation you can do it very quickly. So you make your geometry in the CAD model. uh, Once the CAD is ready, then you can port it to the tri-surface area. So like if you can see, I made this geometry in the this was just a test case. So I made this geometry in FreeCAD, and I imported the patches. uh, so like I imported in the case, wait, let me see, constant, yeah. So I imported inlet, outlet and walls. Okay, if you can see here, there are inlet, outlet and walls. I imported these parameters, I pasted them in constant dot try surface. Okay, I pasted them here, and after that I created a background mesh that covered entire of this domain. Okay, once this is done, then you have to start working on snappy hex mesh. You have to, so like in this case I just mentioned airfoil, but in that case you have to mention inlet, outlet and walls as well, so that you get a good quality mesh. So I won't say this is a good quality mesh, but as I was testing it out, so it did its part. So like if you can see, if we are considering this as outlet, so the number of cells at the outlet are not sufficient enough. Okay, so we have to refine the outlet patch, but this will come once you are quite experienced, or if you are experienced with OpenFOAM. Okay, so that is the thing. And for the modified block mesh dictionary, I have to check if I have it. I'll share that with you. And so this is again a wind around buildings test case. Again, I can show you the this case file for the heating and HVAC system that I did. So again, I did the inlet, outlet, uh, heat source. I applied everything, and So like Snappy Xmesh is very good if you are not into, generating any this uh, trailing edge or meshing. Very, it is very good for meshing complicated bodies. You can see that it has generated a very good mesh. So it did its part. Again, I was learning in that phase. So again, the number of cells at the outlet are not sufficient, but inlet they are quite enough. This was the room, this was the inlet duct, it was going, the room walls were heated, and I was injecting a coolant here. So this was the case. But again, you have to make this geometry in any CAD modeling software, import this wall, inlet, outlet, room walls, and on the tri surface, create a background mesh and start meshing using Snappy X Mesh. So yes, the the learning curve is quite, I mean, decent. You have to spend a good amount of time, maybe 4 weeks, to master it properly without any errors. Hopefully, this addresses your question. Also, Mr. Belkem, if I found the modified block mesh dictionary, I'll email it to you. Okay.
Okay, thank you. I will send you my email.
Thank you. Sure. Yes, Mr. Samuel, you have any questions?
Yes, I want to ask about the location mesh. You have selected the location mesh 3.99 and
Mhm.
0.99 and 0.
0, yes.
Okay. So can be a location mesh can be a 3.99 and 0.01 and 0.
Yes. Yes, why not? Only thing is the point, it should not coincide with the airfoil, as we are
Okay.
doing the external aerodynamic case study. So wherever your airfoil is present, now, Mr. Samiullah, in that
Yes.
region we are avoiding our point. Okay.
Okay.
So
Okay.
whatever the coordinates that you mentioned, those are also completely fine.
Okay. Okay. Thank you.
Yes, thank you. Yes, Mr. Pratik. Uh, Mr. Pratik, you have raised your hand. Do you have any doubts? Mm, okay. Anyone else has any doubts? I'm not. Acha, acha, okay. Uh, can the team help them in this, or maybe I can say no. I cannot.
Pratik, can you type your query in the chat?
You can type your query in the chat. Yes. Uh, Other than Mr. Pratik, does anyone has any doubts related to the case studies that we have done from morning till evening? I know we have skipped some parts in Snappy Xmesh, but there are some tutorials available from FOSSEE CFD on YouTube as well. You can check that out after today's session. So there I have covered meshing on a cylinder with adding boundary layers and how we can run it using parallel as well. Any questions? You can maybe unmute yourself, or you can put that in the chat box as well.
Yeah. Deepa, could you please give permissions to the participants to so that they can unmute themselves and ask questions?
It's already given.
Okay, somebody is writing that I am not able to unmute myself. Pratik Reddy.
Maybe so they have their
Okay.
side. There is problem in their side.
Okay, okay. No problem. So he has written his question.
I'm trying to simulate an F1 rear wing and I have a small features below the end plate. I have reached around 2 million cells, which is the cell limit in the dictionary. Should I now introduce a refinement box? Yes, Mr. Pratik, you can add the refinement region. It is much helpful. Also, we have a case study on F1 car as well. So, if you want, maybe I have the case files. I can share that with you. So we have done meshing and everything was done. So there were around 29 mesh iterations for that. It's a very huge mesh, but yes, we have successfully done. Other than Mr. Pratik, does anyone has any question?
Yes, Gino. So
Yes.
the F1 case that Paris was talking about now, it is listed in the FOSSEE repository. It was previously for I think OpenFOAM 6 or 7, and now it has been upgraded to I think OpenFOAM
2412.
2412. Yes.
Yes.
Yeah. So the upgraded cases will be available on GitHub. So we are working on publishing that as well. So when all of those are available, you can download the older cases which were on older OpenFOAM versions on which are upgraded to the newer cases. So that will be available soon. And if you require any case specifically, you can always email us. We have those cases which are upgraded as well. It's just not publicly available. But if you require or you need it, we can always email you back with those case files.
Thank you. Thank you, Mr. Gino. Okay. I'm not able to trace the local directory where tutorial files are saved. It is not also in C drive. Can you show the location? Okay. So, Mr. Okay, sharing my screen. Uh, Mr. Shubham Das, uh, sorry, Shubham Deka. Hopefully, I'm pronouncing your name in a better way. Ivan sir works on acoustics, so you can directly get in touch with him. He will help you a lot in it. So for the query of Mr. Ankit, so either what you can do is use your PowerShell and you can open PowerShell. You can initiate WSL. As I don't have it like now, so I'll just directly show you using Ubuntu 22. Now, depending on the versions that you have, firstly you have to source them. So if you have set up the alias, so I'll just write OF 2412 and now I'll just write foam. Okay, so if I have installed everything correctly, then I'll get an location where my OpenFOAM 2412 is installed. Okay, still if you don't know, what you can do is you can do explorer.exe dot. Okay, I'm facing some errors here. Fine, so I'll just open it. So this is your home. If you have 2412 or any other versions, then what you can do is you can go in the folder called USR and then go in library, and then there will be a folder called OpenFOAM. So where is my OpenFOAM is there. So here, so in user library OpenFOAM, OpenFOAM 2412 is available. So this will satisfy if your installation is done correctly. For the foundation version, you have to go in the folder called OPT. So for 2412 we went into user. For the foundation version, we have to go into OPT. So here I have OpenFOAM 11 installed with me right now. Hope that addresses your query. Okay, wait.
Yeah, Mr. Pratik, regarding your refinement box, what you can do is, so say you have your airfoil, you have for airfan car. So say it's closer or it's in the center of your entire domain. So you can add a refinement box that is closer to your actual wing, and downstream you can keep it a little bit longer so that you can capture those vortex shading much better. But at some point you will have to, you cannot just refine the entire strip all the way till the outlet, because that will take a lot of computational time. So you'll have to determine that on your own, whether up to what distance you want to capture these vortices. Because see, a vortex, once it's leaving the airfoil, it will, if you want it refined, you can, and if you only want to visualize that, then it makes sense. But other than that, if you want to do some post processing on the airfoil itself, having a finer mesh just on the airfoil is much better than refining that entire downstream area, because that will again take computational time and a lot of resources. So just keep that in mind when you're modeling something like that. So downstream, especially with vortex shading, you will have a refined mesh, but gradually as you reach the outlet, it will reduce, or it will become much more coarser. Yeah.
Mr. Virendra, you have given your email. So, like, do you want the acoustics libraries? For that, you have given your email, or do you want the um, uh, modified block mesh and snappy xmesh files? Any more questions? Also, Mr. Ankit Rao, if you face any issues, you can directly email us at contact CFD, and we'll get back to you. We'll be in touch to resolve your issues. Yes, you can. You have our email, right? Or should I wait? I'll just paste the email again here. So the team is quite active here as well. Yes, yes, Mr. Kalyan. So you have this email, Mr. Ankit. You can email us here. We'll get back to you. Yes, Mr. Kalyan. You can post your query in the chat box. I'm there.
Sir, feedback.
Feedback. Feedback, I guess, will be shared at the end of this FTP, if I'm not wrong. Mr. Kalyan.
Feedback will be shared
Yes.
On the last day, 5th of June,
Yes.
at the
Yes.
end of the session.
Hmm.
Attendance. Okay, I'll just post it once again.
Mr. Kalyan, is your issue related to installation? Or
the installation is over, but
Mhm.
the issue is been coming, right? I cannot able to work on that cavity.
The permissions, right?
Yeah, yeah.
Mm-hmm. Mr. Kalyan, if you don't mind, maybe we can meet after this meeting, maybe.
Yes, yes. So at what time after the
Uh, just drop your email ID in the chat box. I'll get in touch with you.
Okay.
Okay. Thank you, Mr. Kalyan. Any other questions than this? No, it's not the third attendance. We have attendance based on the slot. The first
No,
yes.
this is the attendance for the second half of the day. So we will be posting attendance sheet twice a day. Once the first one will be during the first half of the day for the first session, and the second attendance sheet will be to record your presence in the second half of the day. Okay, and we will not repeat any attendance sheets for any of the sessions. Like, it is live. Whoever is present online and paying attention will be marked present and will be awarded certificates on the basis of the attendance marking.
Just a minute. There are questions on YouTube as well. Let me check. Yes, yes, Mr. Insa Mamul. I cannot see the chat in the YouTube, so maybe we can take the screenshot and we can mail the questions, queries. Yes, so I can see this. Can you detail the region of refinement? So, Mr. Uh, Mr. Bharat, so we have defined a region where, like around the airfoil, I want to capture the wakes. So apart from the airfoil, we don't have much more changes to do. So we have just added a box around that airfoil. Okay. Uh, so you can check that out how we have created the box around that particular airfoil, and you can check it out. If you face any issues, you can write to us. uh, we'll get back to you. Okay, okay, okay. Yeah, mesh, the variation in mesh was because of the uh, changes in the refinement region and the background mesh that we are using. So if your background mesh is coarse and your refinement region is quite refined, so it may seem like there is much more refinement around the airfoil. Uh, okay, this is done. To check mesh quality, as we have said, as Ivan sir has also said, we can use check mesh utility. It is just another like block mesh. If you do block mesh and wait, I can show that. Sharing my screen. So if you want to check the mesh, how good your mesh is, now I have to go to F2412. So let us say any, let us go to the cavity case. So this was the case. So after running block mesh, if you want to check your mesh, so what you can do is, this is only for 2412. You can add a command called check mesh. So it will give out you some stats of your mesh. Okay, how good your mesh is. That is directly been addressed in OpenFOAM 9. Okay, but if you want more versions, or if you want to see how non-orthogonality or skewness is affecting your mesh, so you can write check mesh, write all fields. Okay, okay, so it is done. It has written everything to this to the .foam file. Now we have to open paraview and we can see it. Okay, we can see the mesh parameters as well, skewness, aspect ratio visually. So this feature is generally helpful again, like in dynamic meshing, because there are some errors that we face during dynamic meshing. So yeah. Cavity. Yes. Yes. So see here cell arrays are visible. You can check that out. I mean, you can press select them and you can check those out. Okay. So here it will be displayed. To refresh it, my RAM is not working right now. But yes, using this feature, you can visualize the mesh quality. Okay. Yes. Okay. So Pranay has answered. Okay. Yes, Mr. Arpit Divedi. Do you have any questions?
Yeah, can you hear me?
Yes, yes, sir. I can hear you.
Yeah, I had just one query regarding the installation of OpenFOAM. So I
Mm-hmm.
had installed OpenFOAM version 9, but when I was trying to install this 2412 version,
Mm-hmm.
I think I might have done something wrong, or I'm not sure. But the last command where like you have to put alias of that part, I was not able to complete it. So like while installing, do we have to like install that in the separate folder, or like, because I was doing it in the same manner
Yes.
as it is
Don't
what
have to install it. You don't have to install it in any other folder.
okay.
On Mr. Arpit Divedi, what you can do is you can,
Mhm.
as Mr. Kallan sir has also done, you can
Mhm.
send me your email. I'll get in touch with you if that is okay.
Yeah, sure. So should I write in the chat box here?
Yes, yes, yes.
Okay.
Maybe, ma'am, if there are no queries, then we can call it off for this day.
Yes, yes, sure.
Okay.
So tomorrow morning also please try to join a bit early. We will be starting the session at 10:30. So probably around 10:15 please try to join, because we have a limited capacity for the Google Meet, and then otherwise we'll have to join through YouTube. Okay, I hope you found the sessions useful for today, and I really hope tomorrow's session will be equally interesting and informative. Okay, so thanks to you, and thanks to everybody for joining, and we will see you tomorrow again. We'll meet tomorrow. Thank you. Thanks, Paris, for the sessions. Okay. Thank you so much for that.
Thank you.
Thank you.
Thank you. Thank you so much. Means a lot.
Yeah, really means a lot. Thanks. So, hoping to meet all of you tomorrow. Bye bye. Have a great day.